Hello all. Once again, welcome on behalf of SYMPHY team, and we will be starting in 1 minute. So, HOD cell will inaugurate the session. So, after 1 minute, he will start. Over to you, sir.
Mukesh, I think we can start now.
Yes, Suma, I think we can start.
Yes, sir, you can start.
No, Mukesh, you first start, and then I will give the welcome remarks. Mukesh, you first make some welcome remarks.
Yes, sir. Yes, sir. Hello. So, thank you all for joining SYMPHY 2021. We welcome you once again on behalf of SYMPHY 2021, and this is the annual symposium organized by RSAP. And now I would like to request the HOD sir to inaugurate the session. Over to you, sir. Thank you.
Okay, yeah. Thank you, Mukesh. As most of you know, the PhD students, the Research Scholars Association of Physics, have taken this initiative, I believe almost 15 years ago, to start a annual symposium in physics. And it serves a twofold purpose. One, of course, is to invite eminent physicists to come and visit our department and familiarize the students with the cutting-edge research going on, mostly in India, but sometimes abroad also, in various different fields of physics. And I think even more important component of SYMPHY are the presentations by juniors, both PhD students and postdocs, about the work that they are doing, so that people in the department and institute in general, they know about it. And in fact, this is what I tell all students when they come to IIT. They are going to learn much more by talking to their fellow students rather than from their teachers. And in particular, SYMPHY is a sort of provides a formal platform from which especially the PhD students in different fields, they can acquaint with each other's work. So it's a very good initiative. And so when the first idea was floated, I believe in 2006 or 7, the department supported the idea enthusiastically. And in fact, SYMPHY has grown and attracted quite a bit of attention from the researchers in India. A lot of well-known people have made the effort to come to Bombay and give talks in SYMPHY. Because of the pandemic, of course, we are not able to meet directly, but last year, the Secretary of RSAP, Sanjay Bachar, took the initiative and organized an online SYMPHY, and I'm glad to see that his successor Mukesh Singh is continuing and has put together a very good program. And I must especially thank Professor Raghunath Challakot, who has advised the students in various organizational aspects and helped them in putting together this program. And Mukesh and the team of student volunteers with him, they have worked very hard in setting up this program. And I hope all of you will have 2 days of enjoyable time listening to the presentations, listening to the colloquia of the expert speakers and also the presentations of the students. Thank you all for joining for this program. And now I request Professor Raghunath Challakot to say a few words about this year's SYMPHY.
Thank you, Uma. So welcome all of you again, once again, for this SYMPHY 2021 in virtual mode. So as you know, because of this pandemic situation, we are unable to conduct this SYMPHY in the usual form where everybody assembles in one place. But while this produces this challenge in organization, we also get an opportunity to invite people all over the world to come and join this interaction without worrying too much about this logistical constraints. And so since the pandemic has started, this online platform has become a norm, and more or less everybody is acquainted with this. They're comfortable with it. So I think Mukesh and the fellow organizers have successfully, able to bring a list of eminent scientists working in various areas to participate in this online colloquium. So this colloquium will be running for 2 days, Saturday and Sunday. And we have roughly 4 sessions every day. And you can all see the schedule. It has also been shared with you. And in each session, we will have one invited talk for 45 minutes and followed by presentations by students and postdocs. And in the evening, there will be, in both days, there will be a plenary session, which will be running for 1 hour. And today, the first plenary session will be, we'll have Professor B.S. Satyaprakash, who is working in astrophysics. And tomorrow evening, we'll have Professor Bulbul Chakravarti, who is working in statistical physics and soft matter. So I wish all of you a wonderful, a vibrant discussions and like a very good learning experience from this symposium. And I think the first session will be on quantum information. And over to Mukesh and the chair of that session to conduct this. Thank you very much.
Okay, actually, there is still a bit of time, Mukesh, till 9:30. So these 3-4 minutes maybe you can spend by introducing your fellow members of the organizing team. Yeah, you can also briefly turn on your camera when Mukesh introduces you, so that people can see who you are.
Okay, sir.
Yeah.
So in the SYMPHY team, we have, so I am the president of RSAP, and then we have the chair, Vice President Anuj Kumar Singh.
Yeah. Yeah, Anuj Kumar. Anuj Kumar, sorry. Yeah, hi. Thank you for all the effort you have put in. Okay. And next.
And then treasurer Kishore.
Kishore.
Hi, sir. Good morning.
Yeah, hi.
Good morning to everyone.
Good morning. Yeah, thank you for the effort you put in for SYMPHY.
Then we have the cultural secretary, Deepmala Mohinta.
Deepmala, you are here. I see your name. Yeah, hi. And thank you for the effort you have put in for SYMPHY.
And now Rehan is also working with us in SYMPHY team. So
Okay.
over to you, Rehan.
Hello, Rehan, and thank you for all your work. And by the way, all are PhD students, or there are some MSc students also?
All are PhD students.
All are PhD students. Okay, and thank you. And in fact, as these are some of the advantages of studying IIT, so that you have these collaborations as to develop both in physics as well as in solving issues which are related to groups. And I hope all of you had a good time. Of course, there were probably difficult times where you shouted at each other, but overall, be proud that you have eventually put together a very good program. Okay, thank you all.
Yes, sir. Thank you.
And okay, I think we can start with the quantum information theory session now.
Okay, shall we start? Okay, so I take silence as yes.
Yeah, sorry, I said yes, but my mic was muted. So, please, yeah, go on.
So I see that Vijay has joined us, right? Hi, Vijay. Hi. So fantastic. So welcome everyone. It's my pleasure to basically be the chair for this first session of SYMPHY, which has quantum information as its theme. So we have Vijay, who will present to us the first talk, the invited talk, and then there are 4 contributed talks as well by PhDs and postdocs from our department. So it's my pleasure to introduce all of them to you. So Professor Vijay is, of course, a good friend of many of us in the department, and is currently in Tata Institute of Fundamental Research in Bombay, just across town from us. He pursued his PhD in Yale in 2008 and did a postdoc at UC Berkeley with Irfan Siddiqui's group till 2012, and now heads the Quantum Control and Measurement Lab at Tata Institute. And so he's going to tell us about superconducting qubits, and take it away, Vijay.
Thanks a lot, Sai, for the introduction, and thank you to IIT Bombay and the SYMPHY team for inviting me to this symposium. I think I gave a talk maybe 4 or 5 years ago in an earlier version of this event as well. That was, of course, in person, and looks like we're going to be doing this online thing for quite a while. So let me get started and share my screen here. Am I audible clearly?
Yes.
Okay, great. Okay, and I hope the slides are now visible.
Yes.
Okay, great. Yeah, so let me get started. I hope to tell you, in briefly how one goes about building a quantum computer, or more precisely, what are the elements in terms of the different components that are needed and the kind of problems one has to solve in building a quantum computer. As I mentioned, my work at both Yale and Berkeley was connected to superconducting qubits, so that's my area of expertise. Though these general, the techniques I will be talking about, those specific to superconducting qubits, it sort of can be extended that something similar with a different choice of hardware and methods can be applied to other kinds of hardware platforms. As I'm sure all of you know, that there are several different ways one can actually build this quantum computer, and we still don't really know which one is the correct, or if there is even one correct choice or best choice. There are a few contenders, and some leading the race, and some very new but showing a lot of promise. But the general requirements, the pieces, the problems that have been solved are more or less similar, with some having certain advantages in certain aspects. So I will hope to tell you a little bit about that, and also briefly touch upon some of the things we are doing in our group using these superconducting quantum devices. So this slide here is to basically emphasize that when you are doing computation and when you have basically manipulating information, you need some physical device on which this information can be encoded and then manipulated. And of course, in classical or conventional digital technology, we have many different ways we can do that. And all of them essentially store the same information, just in different physical ways. So which physical property represents the bit state 0 or 1 changes. But otherwise, the information content is the same. Now, when one moves from the classical world into the quantum world, you need a different type of physical system, which now requires an additional feature, which is the idea of quantum superposition. So if one sort of takes a very simplistic example of, say, the hydrogen atom with a proton and a single electron, of course, this picture of orbitals, as we all know, is not really accurate. Slightly more accurate version is that there are these clouds which represent the orbitals. But you could choose, for example, the electron's energy or the particular orbital the electron is occupying as a marker for the state you are intending to store. So you could choose the sort of, for example, the lowest energy state of the electron as the state 0, Now I've written it as a ket0 to highlight the fact that this is now a quantum state, and say the next excited state as state 1. And as we know that these orbitals are solutions of the Schrodinger's wave equation, so linear combinations of these solutions are also valid solutions. And this is the new part when it comes to the quantum world, that if we now use these two states as the states of a storage unit, then it is possible to basically create superposition states, which are combinations of these. And of course, in sort of general language, we like to say that a quantum bit is both 0 and 1 at the same time. Depending on who you are, you might like that description or not, but essentially, mathematically, the statement is very precise. It's nothing but a linear superposition of the two states of a quantum system. And with superpositions, the phases are also important. So both 0 plus 1 and 0 minus 1 are valid states. And the phases also play an important role because now you have the possibility of things interfering with each other. Okay, so the general principle is that now you're using a physical system, which is a quantum two-level system. One can represent the most general superposition of a quantum two-level system in this kind of parametrization using two angles, theta and phi. That allows you to represent this on a sphere. It's easy for convenient for visualizations, where the north and the south poles represent what we call the eigenstates. These are sort of the classical equivalent of the when comparing to the classical bit, and then all other states on the surface of the sphere is a valid superposition with the particular value of theta and phi. So, and then if you have something in the middle, these are all superposition states. And essentially, one of the things which comes up here is that what does it mean in terms of information storage capacity? And there's often a misconception here that because of the infinite possibilities, it looks like you can store an infinite amount of information. But here comes the second aspect, or sort of weird, or now no longer weird, but still surprising aspect of quantum mechanics is that when you try to detect this state, you still only get two values, which is 0 or 1. And if you have a state like alpha 0 plus beta 1, the probability of getting the answer 0 when you actually detect the state is proportional to mod alpha square and probability mod beta square for getting the answer 1. And this, you cannot directly measure the alphas and betas just with a single copy of this bit. And this is the collapse of the wave function, that even though you can encode with infinite possibilities, you can take a single qubit and prepare it in an infinite number of different ways. When you recover information from it, you only get one bit of information. So that's why this is still called a quantum bit and not something different. Effectively, it's still one bit of information you can recover, but this ability of having infinite possibilities, and that these are all essentially wave functions with different phases, is where you get the flexibility or the new capabilities to do something different with quantum computing. All right. So, in a general idea now, you extend this to multiple qubits. A single qubit is not enough to do much in terms of quantum computing. If you now extend this idea that if you had n classical bits, then you can only program it or store one of the 2 to the n possible states. But if you had n qubits, you can actually prepare it in a state which involves a superposition of all of the 2 to the n possibilities, right? So the 2 to the n is essentially the number of different combinations. You can prepare the zeros and ones. And the algorithm can, in principle, operate on all of these states simultaneously. So it's this step in the middle which takes this collection of qubits and then basically takes them through a sequence of manipulation. And now this phase space over which you can manipulate these states is huge. It's basically it grows exponentially with the size of n, and you can have constructive and destructive interferences going on, and entanglement and superposition all playing the role together. And then at the end, once you're done, you measure all the qubits which are present in your quantum computer, and hopefully the sequence of zeros and ones tells you something useful about the problem you have solved. And again, just repeating the same thing, you only get n bits of information with an n qubit quantum computer, and you have to exploit this parallelism and interference in this in this part in order to achieve any real advantage using these systems. Okay. So the problem, of course, is that these kind of physical systems which one uses to store are not stable. It sounds very strange, but that's actually the reality of these physical systems. So by not stable, what it means is that, let's say you heard a very nice song on your friend's computer, and you say, hey, let me copy this file. And you put your USB drive and you copied it, and you went home to your, you went to your room and you plugged it in, and basically the data is not there. Now that was still probably a few minutes of time between when you copied and when the data showed up. With qubits, that time scale can be nanoseconds, microseconds, or milliseconds. Essentially, they just don't retain that information. And one of the two main processes which happens is that if you prepare a qubit in an excited state, it typically just wants to come back to the ground state. And this happens over a certain time scale, and we call this relaxation, which is like we call T1, comes from the NMR language. It's a T1 time. And then there's also another kind of important noise which one has to worry about, is that when you create a superposition state, in terms of the block sphere, the direction in which is pointing is connected to the phase of the superposition. And that phase can also get randomized because of the noise. So you can see that essentially storing information here is basically putting the state on a particular point on this block sphere. And then anything, which is not done by you and happens randomly, which is changing that position, is bad, because essentially you've lost what you originally put in there. And these processes happen in all qubits and to different extents. And that's one of the challenges people have been fighting, but there's been a lot of improvement. And luckily, it turns out that there's actually a solution where even if you're never able to stop this process completely, you can still actually build a useful quantum computer using something called quantum error correction, which I won't really be able to go into any kind of discussion today. But essentially, this involves using multiple copies of these qubits in order to represent one effective qubit. And it turns out that if you do it in the correct way, even though individual qubits might be undergoing these kind of processes, collectively, they still are able to preserve the information which one has stored. And that was a big discovery, a theoretical discovery, which then basically allowed people confidence that, okay, this can actually happen. Otherwise, it looked like this was never going to work. And now proof of principle experiments have shown that the idea of quantum error correction is actually robust, though a truly error-corrected quantum processor is still some time away. And that's one of the big goals in the near future. So to summarize, what does one need to build a quantum computer? Well, one needs some physical system where you're able to encode these two levels and create superpositions, so they can create these arbitrary states easily. You also need the ability to measure the state at the end of the day very precisely. This is actually not such an easy thing, because these systems are very fragile. And in fact, a big part of my PhD and postdoctoral work was focusing on the quantum measurement problem and how to do it very efficiently and with high fidelity. And then finally, you need these qubits to be able to interact with each other. As I said earlier, just one qubit is not enough. And also n qubits which are not interacting is also not nearly enough to do anything useful. You need these qubits to interact. And this is actually how you do gates. Like just in classical Boolean logic, you have two inputs coming into an AND gate and an output. Similarly, you need at least two qubits to interact together to be able to create something more like some non-standard or more interesting quantum states, which is things like entangled states. You need some kind of interaction between them. And you put all of this together, and you have to fight this decoherence issues, and also to do this for a sufficiently large number of qubits so that you start to have some advantage. So that's sort of a summary of the basic requirements of what you need. And then one moves on to the choice of, okay, which physical system is good. And there are several candidates. I've shown three here. You can trap ions in electric and magnetic fields and use lasers to manipulate them and use the electronic states to store the quantum states. Or you can confine an electron in a 2D electron gas using gate electrodes, and then use the spin of that electron pointing up and down against the magnetic field, which have different energies now, as your quantum bit. Or you can use an electrical circuit like a superconducting circuit, which is basically what I'll be talking about today and what is my own area of expertise. And, still all of them, you can choose two states and create and call those your qubits, state 0 and 1. And there's a whole bunch of others, which I just wanted to mention, using photons, using nitrogen vacancy centers and topological qubits. But currently, sort of these are the three platforms which are maybe leading the race, though photons are making a big comeback in the last few years. So let's now look at superconducting circuit-based qubits. And the simplest way to describe one of the designs, which is the most popular one, is that it's nothing but an electrical pendulum. So a pendulum, is essentially an oscillator, which means it can carry out periodic motion, and one can construct an electrical version of that oscillator by essentially building, what we call an LC circuit. And here's an image of a device. You can see the size scale; it's almost a millimeter size, and then right in the middle, there is this structure which we call a SQUID, or a superconducting quantum interference device. And this is basically gives rise to an effective inductance, and these two big pads give rise to an effective capacitance. So it's like an electrical oscillator, but this inductance is nonlinear because of these two devices here, where there is an overlap between two metal films, which is aluminum. It's a superconductor that behaves like a Josephson junction, and that Josephson junction has an inductance which depends on the amount of current you are flowing through it. And so that's the circuit diagram of that. And essentially, the qubits are nothing. The qubit states are just the oscillation states of this system. So the state 0, which is the ground state of the system, is the state with the oscillator with 0 extra quanta. Of course, there's always 0-point fluctuation, so that's the half quanta you might have heard about. And then with 1 excess quanta in the system, that's the first excited state. And this is one of the most popular and simplest designs of superconducting qubits. It's actually been given the name the transmon qubit, but it's a weakly nonlinear oscillator. And the potential diagram of energy diagram is shown here. It's a cosine potential. It comes from the fact that the restoring force in a pendulum is sinusoidal. So it's a cosine potential in which it's oscillating. So the electrical version has the same thing. And because of the nonlinearity of the potential, the levels are not equally spaced, the quantized levels. Like you might have studied the harmonic oscillator, which has equally spaced levels. Here, the levels are unequally spaced, which means the transition frequency between the ground and the first excited state is now different than all the other transitions. And that allows you to isolate the two lowest levels. So it's actually a quantum multi-level system, but you can choose the two lowest levels as now your qubit. And that allows you to address them because the frequencies are no longer the same. Typical values are shown here for the inductances and the capacitances, and that gives rise to a resonant frequency in the microwave range of around 5 gigahertz. In temperature units, using this relationship between kT and h bar omega, that's about 250 millikelvin. It's a very small energy. So these are microwave frequency oscillations. The quanta energy is very small. And because of that, you have to go to very, very low temperatures of around 10 millikelvin, so that thermal energy doesn't excite the system, right? So you don't want this thing to be populated with thermal energy. You want to precisely control the state of the system. So you go to very low temperatures. And this is achieved using a commercial instrument called a dilution refrigerator. And these oscillators, need to have very low dissipation, essentially the equivalent of not having friction, so that they keep oscillating. And that's the equivalent of, what does it mean to have a good coherence, right? You set the system into oscillation, it should keep oscillating for as long as possible. And that's the same idea as staying in the excited state in the quantum description. So the superconducting circuitry both give rise to the nonlinear inductance, which is completely non-dissipative, at least in theory, and allows you to create very low loss electrical oscillators, which can survive for a long time and gives you good coherences. So, coupling of these systems together, as I mentioned, is important. And since these are sort of two electrical oscillators, you can just connect them, say, with a capacitor, and this becomes like a coupled oscillator problem now. And I'm sure some of you might have done these coupled oscillator experiments in your undergraduate lab, where you set one of them in motion and then slowly the energy goes back and forth. So similar physics can be used here to actually create these 2-qubit gates or entangling operations. And this coupling can be a simple capacitor, or it can also be done using like a microwave resonator, which is shown here as the bus. It's often called the bus cavity. Or it can be done using a more sophisticated circuit, which actually allows you to turn that coupling on and off. So these are called tunable couplers. These are called fixed couplers. And both of these approaches are being used. Very roughly speaking, you might have heard the two big companies in superconducting qubits, IBM and Google. IBM uses the one on the left and Google uses the one on the right, typically for their main experiments. And they both have their own pros and cons, depending on what you're trying to do. All right, so you can now put this together. Here are just some examples of chips with many qubits. Here's a very old chip from University of California, Santa Barbara, showing 9 qubits. So all of these pluses basically represent the transmon qubits in a linear array. Here's a IBM system with 4 qubits in a sort of a 2D grid. Here's a larger one with 16 qubits in again, a 2-dimensional grid. And all of these are put inside these dilution refrigerators I mentioned. And it's a lot of wiring and shielding and filtering that's required to get it all to work. And of course, in the last couple of years, like very compact chip-like, really professional chip-like looking things have come up. So there is an image of a bristlecone processor. You might have heard about the Sycamore processor from Google from a couple of years back. And so these things are really heating up. You can put these things together in compact integrated circuits and carry out operations between them. How does one actually now control these states? Essentially with a microwave pulse. So you send a microwave pulse of a certain amplitude and phase and time at this transition frequency, and that's all you need to control. And if you do this experiment where you vary the length of this pulse and then measure, you get these oscillations. These are called Rabi oscillations. And essentially from this, you can calibrate, where your ground state is, where your excited state is, and then you can choose which superposition you want to create by just stopping the pulse at the right time. So this is how one does that. And this allows you to rotate around this block sphere in different directions by choosing the different phases of your drive. And this is how you do single qubit control in these superconducting qubit systems. And in order to create these pulses, you use standard modulation and demodulation techniques. Essentially, you want to create some general a to the AT into sine omega t plus phi t. Well, all of these are functions of time that can be broken down into these 2 quadratures, things which are proportional to sine omega of t and cos omega of t. And these can be implemented by using a microwave generator to produce the sine and cosine, sine omega t, an arbitrary waveform generator to get these modulations I of t and q of t, and combining them with this device, which is again a nonlinear device called a mixer. It's a very standard commercial device you can get. And then you can get a pulse of the right amplitude and phase modulation profile. So this is how one actually creates the setup. The idea here is to show you the different components which actually go in putting together an experiment or a quantum processor. And similarly, one can also use the same setup in reverse to demodulate the signals when you're detecting the quantum state, right? So here's sort of a snapshot of a typical wiring, which might be needed for just doing a few qubits. You have a whole bunch of arbitrary waveform generators creating the various pulses, which are getting combined, and they go into the device, and they come back from the device, they get demodulated, and then go into a digitizer, which is then read out by a computer. Here's all of these sort of put together on a rack with various instruments sort of shown here. That's all the control from the room temperature side. This is the picture of the dilution refrigerator in our group. And you can see there are these different plates, all of them at different temperatures. The final experiment actually goes to this bottom plate. So anything which is screwed to that bottom plate gets to the lowest temperature of about 10 millikelvin. And you have to put a lot of wiring to get the signals in and out, and this has to be done very carefully. So you need these specialized cryogenic wiring. You need specialized filters to kill all the noise which is there just from the fact that things are hot. So black body radiation coming from 4 Kelvin is very detrimental to your devices because the photons have high enough energy that they can actually destroy superconductivity in your device. So one has to very carefully package them, put them in various kinds of shields so that you're protecting them, and also create special filters so that these noise don't even come down through your wiring. And this is really one of the challenges in superconducting or in any quantum experiments, that the quantum systems like to be left alone in order to show their true quantum properties. But if you want to really manipulate and detect them, you have to connect wires to them or some kind of probe. And this kind of conflicting requirements is really one of the hallmark challenges, and people have come up with clever ways of doing it so that you disturb it in the minimal possible fashion you can. And then of course you have to design these chips which can be of different natures, and then they all go here. We also design specialized superconducting device-based amplifiers, because the detection also happens with very small level of signals, and that requires very specialized amplification methods so that you don't contaminate the signal with too much noise. So that's what happens on the cryogenic side. And here's the same wiring. Again, the goal here is to show you the amount of different components which goes in just to manipulate 1 qubit. So here, the device is somewhere down here. You have input wires, which lots of attenuation for filtering. It goes and gets routed to the device, and then it comes back out. It goes to a second device for amplification, and then finally goes up the chain, gets amplified more before it comes to room temperature and gets detected. And along these lines, both on the input, the outputs, as I mentioned, there are attenuators, reflective filters, lossy filters, circulators and isolators, which allow signals to propagate in a preferential direction, cryogenic amplifiers, flux lines to control the device's properties. And all of these are done with coaxial cables. So this is just 1 qubit's worth of wiring, sort of a typical setup. And if you want to do a more complicated experiment, say a 4 qubit experiment, which we are sort of preparing for in our group, this is essentially duplicated 4 times. Of course, there are many techniques now to minimize some of these components by combining the features in a single line using things like frequency multiplexing and things like that. But this is really to give you a flavor of the complexity and the amount of resources which go in to doing these experiments, right? So when all of this is done, at the end of the day, you're trying to run some kind of a protocol or an algorithm on this. What does this algorithm look like? So here's sort of this is really a cartoon version of a quantum circuit diagram, where there are different kinds of gates, and it could be single qubit gates or 2 qubit gates. And when you translate this into what actually happens in the experiment, each gate, like each box here, is basically a microwave pulse with a specific set of characteristics. So what's actually happening in the experiment, at least in superconducting qubit systems, is that a whole bunch of microwave pulses at different frequencies and different time and amplitude profiles are going into the system, and then they come back, and then they have to be detected. So that's essentially, in a nutshell, what happens in an experiment. So you have to do various calibration experiments to figure out exactly the correct microwave pulse for doing, say, a bit flip gate or a phase gate or a Hadamard gate, and how to do the measurement. All of these things have to be calibrated, and then they have to descend in sequence depending on the particular algorithm you are implementing, right? And these calibrations can also drift with time, so you have to periodically keep correcting them so that you don't accumulate these errors as you go along. So some examples very quickly. Again, I'm sure many of you have heard about this. Multiplying big numbers, prime numbers, and it is easy, but if you want to do the reverse process, it's mathematically very hard. It grows exponentially with the size of the digits. And this is actually at the heart of encrypting data called the RSA encryption. And then 94 showed that if one had a quantum computer, then this problem actually becomes, instead of scaling exponentially, it scales polynomially, so it can actually be solved. So, you might have heard these numbers, like for a 1,000-digit number, a classical conventional computer would need something like 10 to the 24 years versus 20 seconds on a quantum computer. I mean, these are all very approximate guesses, but you can see the order of magnitude difference in these things. Right, so this is one of the big developments, I would say, in the algorithm world, which really made people get serious about building these machines and sort of kickstarted the race to build the hardware. There's a very nice YouTube video where Peter Shor talks about how the Shor's algorithm was invented, if you're interested in those kind of things. One can use these quantum systems. In fact, one of the early applications, which was suggested way back by Feynman, is to actually model quantum systems. So this exponential growth of the Hilbert space, which gives the power to the quantum computing, is actually the reason why it's very hard to do quantum calculations on a classical computer, because the amount of resources you need grows up exponentially the moment the problem becomes even slightly complicated. So a very important application is to use quantum computers to actually solve quantum mechanical problems, which might be of interest in various, chemistry, medicine, and all kinds of various things. And so people have tried this. These are all very simple examples of small molecules computing the energy, the bond energy, and the ground state of these molecules. And these are done using techniques called variation quantum eigensolver. And this work I'm showing here was done at IBM, but now other groups have also repeated it. There have been other experiments which are sort of more connected to biology, where one's talking about sort of how photosynthesis is such an efficient process, where an excitation of the light gets converted into other kinds of excitation inside the the chlorophyll molecule. So this again work was done using superconducting qubits in the group at ETH. And they basically created a model for photosynthesis, but scaled down all the parameters by a factor of 10 to the 5. And here they actually showed that the environmental noise, which we usually think of as a bad thing, here actually plays an important role in making this process efficient. So this is another example of things they have done. And there's a whole bunch. Like essentially you realize that any calculation involving quantum mechanics can be done more efficiently, at least once you build a proper machine. And that just opens up endless possibilities. And some of these are listed here, and many more are yet to be discovered. And in fact, this is a very active area where we need a lot of development to actually come up with different problems, because there's no simple rule book which says that, okay, every problem becomes better on a quantum computer. It's not true. Problems of modeling do become better in general, but in terms of things which are not directly related to quantum mechanics, for example, optimization, the traveling salesman problem and things like that, there also quantum computers are supposed to do much better. And there's a lot of work going on and figuring out where else. And these machines are now becoming a reality. So the race for developing more useful and especially now commercially viable applications are being looked into, right? So in the last few minutes, I just want to quickly tell you a little bit about a few projects which we're doing in our group. Mostly our work has been related to small number of qubits. So one of the things, first things we developed some years back now was a completely rethink of how multi-qubit systems are put together. So remember I told you this transmon qubit is basically a single oscillator. So here we built a more complicated circuit involving several Josephson junctions and several capacitors. And this composite circuit is now is basically composed of several different oscillating modes. 3 to be precise. And in this particular case, you get 3 different qubits because you get 3 different oscillating modes at different frequencies. The frequencies are chosen by carefully controlling the capacitance in the various locations. And here's a picture of the device. You can see it just looks slightly more complicated than the single qubit device. And that's indeed true. And yet you can get a 3-qubit system out of this. And we were able to do a series of experiments on this and showed that, yes, it indeed works. It offers some advantages because now you have a composite 3-qubit systems, not 3 separate systems, which have to be plugged together. And we showed for certain algorithms, this actually does better than the standard case. And we are now trying to extend these to larger systems by combining blocks of these 3 qubits together using other systems so that we can build larger processors. And essentially you have a 8-level, the 3 qubits, you have 2 to the 3, 8 levels Hilbert space. And that's sort of the energy level diagram of how these levels line up. And there are 12 different transitions one has to control now, essentially 12 different frequencies of microwaves. And that allows you full universal control over this 3-qubit Hilbert space. Basically, essentially means you can implement any operation on this very, very efficiently, right? as you've seen in the previous pictures of the processes, the layout of the qubits is almost always on a two-dimensional plane, and that has some restrictions on how one can connect. So here the red dots are the qubits, and these these green and yellow squiggly lines are sort of showing how the qubits are connected, so that every time there is a connection here, which means you can do a 2-qubit gate between the two connected qubits. So you can see that, for example, 5 is connected to 6 and 13, but 5 is not connected to 14. So if you want to do a gate between 5 and 14, you have to sort of go in 2 steps, either via 13 or via 6. And that increases the number of operations, and in general results in an inefficiency when you're trying to translate an algorithm, because the algorithm might require some operation to be done between, say, 5 and 14. And without just physically putting connections between every pair of qubits, so 5 and 14 might be easy topologically because there's a diagonal space available here. But then what about 14 and 7? Now you have to do crossovers and things like that, and that can give rise to a lot of crosstalk. So we came up with a sort of a new design where instead of a 2D grid, square grid like this, we put it around a circular grid. And this is just one continuous piece of a transmission line, basically like the squiggly thing, but now it's a longer and a continuous one. And we just place the qubits around it in this sort of regularly arranged fashion. And what that gives us is this kind of a connectivity. So here, every solid connection is showing a qubit which is actually connected. So even though this qubit here is not directly connected, there's no, it's not connected via its own special line, but there is always a path between each 2 qubits that allows you to create these kind of connections. And we showed that in a setup with 12 qubits around a ring, every qubit is connected to at least 9 other qubits, and it's not connected to 2. And that tends to happen because of destructive interference. Turns out if the qubits are at 120 degrees, this path and the path going the other way are exactly 180 degrees apart. And that gives rise to destructive interference, and hence they're not coupled. So we did these experiments. So here's actually the device. This is done in what we call a 3D circuit QED geometry, where instead of actually designing the microwave circuit on chip, we actually machine it in a piece of aluminum. This square is a couple of inches on its edge. That's the size scale. And then the qubits are all placed as individual chips along this thing. So the central ring is this special coupler, and these things which are spokes which are sticking out, these are all the measurement resonators which are used for detecting the quantum state. And we showed that if we look at these couplings, they match the prediction fairly well, and we expect the kind of connectivity we have. And now we are working on actually taking this kind of architecture to build a real processor. In the first experiment, we only showed that the coupling exists. We did not actually do quantum gates. Now we're working on actually building a processor using this. So that's basically what I wanted to tell you today. There's a lot of opportunities and challenges in this field. We need lots of different kinds of scientists and engineers. For example, we need theoretical physicists to work on new device design and analyze noise sources and figure out how to suppress them. We need experimental physicists and engineers to solve architectural problems on how to connect these things together and make them larger so that they're actually useful and find scalable solutions. We need computer scientists to invent new algorithms, which can, especially those which can run on the kind of hardware which is available today, which is a relatively small number of qubits, and qubits which are still prone to errors. We also need to work across community with chemists and biologists to figure out what kind of problems these kind of machines can really be useful for, with more relevant applications in other fields of science as well. And then, of course, get it all to work. So it's really a highly interdisciplinary field, and we need collaborations between lots of people. To end, I just wanted to flash these important results which have come up in the last 2 years. You might have heard these terms: quantum supremacy, quantum advantage, and now new quantum primacy. The supremacy word has been frowned upon, so it's no longer used. But about 2 years ago, Google showed with a 53 qubit system, for the first time, they claim is that they can show that for a certain computation, this computer does better than any other computer which is available in the world today, which means even the most powerful supercomputer cannot do this as efficiently as this. Of course, there were some controversies and some discussions on whether this is this 200 second versus 10,000 years is indeed correct or not. But this was a first important step. And then soon after that, in a photonic quantum processor from China, for a slightly different problem, they showed that there's actually a speed up factor of about 10 to the 14. This is even more enormous. And then just this in this year, there have been two new results, again now from China, both one in superconducting processor, which is now using 56 qubits, and it's supposed to be handling a task which is two to three orders of magnitude more complicated than the one done by Google a couple of years back. And now they say that it's 1.2 hours versus 8 years. That's the advantage between using a quantum computer and the most powerful supercomputer. And then an enhanced version of the photonic experiment, which is, has more number of photons involved. And they even claim that this one actually can be used for practical applications. All the other examples are sort of toy problems or specially designed problems to demonstrate the capabilities of a quantum processor. But here they actually claim that this is can actually be used for practical applications involving quantum chemistry. And these papers just came out a couple of months back. So the race is really heating up. All these experiments, there'll be many more such experiments which sort of really demonstrate that yes, these quantum machines, quantum computers can really do better. So let me end the talk at this time by just putting my summary slide here. I just want to say that this idea is very powerful, but this is, even though it seems like a lot has happened, this is really the beginning. We have to really figure out how to do this in a practical way, and there are lots of opportunities here, including in India with the government spending or planning to spend a lot of money on this area of research in the coming years. So thank you, and I'll take some questions.
Thank you very much, Vijay. Wonderful talk. So we have 5 minutes for questions. So I definitely encourage people who have questions to please indicate by raising your hand in the Zoom. Just unmute yourself and ask. That's as well a possibility. So while people decide, Vijay, I just wanted to ask, so you showed this IBM versus Google, the two choices of couplings, either constant or variable coupling. Is this something, does that design choice bring with it specific noise issues? Like why would one side choose one and the other? Like, can you speak to the logic of both groups?
Exactly. So it's really, if one thinks about it in a more fundamental way, keeping aside practical problems, you would imagine that you actually want a system which has controllable coupling. And that's essentially because you are, if there are any interactions which are left on, then they can give rise to unwanted evolutions. And that becomes more and more complicated as more qubits are put together. But any such control means an additional wire going down all the way to the device. So, in the early days, this was sort of frowned upon that, okay, let's try to minimize as much as possible so that we don't suffer from decoherence. But over time, as people figured out how to do it better, it was seen that the advantages sort of outweigh the things. But I don't remember the exact numbers, but I think all the devices with tunable couplers still have lower coherence than the ones without tunable couplers, though it could be for completely different reasons. I have not looked into this. Of course, you can't get those kind of details from the authors themselves, especially from companies. But it also then restricts the kind of entangling operations you can and cannot do. Once you have a controllable coupling, you can actually do the gates in several different ways. When the qubits are not tunable, then the fixed frequency architecture restricts you. And that also means that you have constraints on how the choice of the qubit frequencies are chosen. Because remember that, as I said, that this is like a coupled oscillator. If they're on resonance, then they're always interacting with each other. Mm-hmm. So in fact, the way it works with the fixed coupling architecture is that the frequencies are chosen to be different. And that's how you turn off the coupling. So when you don't do anything, they are off resonance oscillators. But there is still always a physical connection, and it's this remnant connection which gives rise to errors. And in fact, that's the reason why IBM has gone away in recent years from connecting too many qubits together, even though I sort of made a big deal that connecting qubits is important for more efficient, but they realize that the price they're paying for that is not is sort of overcome by having a sparsely connected qubit network, but then it allows them to improve the quality of the individual 2-qubit gates. So overall, things get better, but that's not really I think a solution for the long term. You will have to solve the connectivity problem. And that's more easier with the controllable coupling, because you can really just turn it off. So then you don't worry about the qubits just sitting there. But yes, it's this possibility of more wires bringing in more noise. And also that also means that more complexity of wiring coming down your cryogenic apparatus.
I see. Very, so any more quick questions?
Can I ask a...
Please, Raghu, yes.
Yeah. So what I understand is for solving any problems, you will have to build this algorithm so that you can map your mathematical problem to the qubit-based system, right? So is there any fundamental reason to assume that this qubit-based algorithm will always do better than this, binary algorithm, irrespective of the problem that we are working with? Or is there any type of problem where the binary system would do better than the qubit-based system?
Oh, yeah. So I had briefly mentioned this, that there is no such general rule. In fact, for many problems, the quantum version of the problem might not either exist or not be better at all. I mean, today, because these quantum versions or these quantum hardware are full of errors, whereas your classical hardware is completely, almost error-free. For most cases, you can just use your classical hardware. The trick is that you really need to have problems which can exploit this ability of access to this very large Hilbert space. Okay, so you have to distinguish now two classes of problems. Any problem involving modeling a quantum system itself, I think in general, you can say that on a good quantum computer, it will be better. It's basically the difference between requiring a physical system. Let's say you're analyzing a problem which requires you to n qubits to sort of model it properly. In a quantum computer, you will need roughly n qubits, maybe a little bit of overhead once you bring in the error correction. But on a classical computer, you need 2 to the n kind of resources. And that's why you just cannot simulate, for example, 53, 55, 56 qubit numbers is roughly the threshold where the complexity and the amount of resources, basically, you just cannot do it on even the most powerful supercomputers anymore. That's why these numbers are around 50 are being used. So for modeling in general, yes, but for other problems, we don't know. There is no people, I think people in computer science who are trying to figure out if there's a general class of problems which will always do better in a quantum computer. But in general, this is not true. It will always be for specialized problems. And we have to figure out more and more ways of, and more places where it can actually offer a benefit. Another general principle that is used is problems which involve exploring multiple paths and trying to figure out which one is the best. They can potentially work better on a quantum computer just because of this sort of parallelism which is present because of the superposition capabilities, that the quantum system can sort of check many different possibilities together and sort of cancel out the bad ones and keep the most efficient one ahead. But I'm giving a very hand-waving argument here, but that's sort of the kind of problems one. And so traveling salesman problem, optimization problems are examples of these kind of things. And people are figuring out algorithms to do that.
Thank you.
Okay, thanks a lot, Vijay. I think let's all thank Vijay for this wonderful talk. And I'll request our next speaker, Parvinder, to set up. So we have four more talks to go, and Parvinder is the first speaker in this session. So let me briefly introduce Parvinder. Parvinder is got his master's from Punjab University and has been with our department for the last 3 years. And he's working in my group, as you can see from the slide. So Parvinder today is going to talk about seeding crystallization. Take it away, Parvinder.
Yeah, thanks for the introduction. Am I audible?
Yes.
Okay, so I will start now. So hello everyone. I am Parvinder Solanki and today I am going to talk about our latest preprint, seeding crystallization in time. So let me begin with the introduction to the seeding. So what is seeding? We all might have done this experiment in high school chemistry lab where we took a crystallizing solution and then put a seed or a crystal into it, and then we can see the crystal grows into the solution. Now we are asking the question, can you observe same kind of shading effect in the time crystals or not? I will be explaining time crystals in the upcoming slide. For now, just assume that system A is in the time crystal phase and B and C are in the melted phase, just like the crystallizing solution. And if we make them interact, can we observe shading for B and C? So the answer to this question is yes. And I will be explaining in the upcoming slide why. And so let me begin with the introduction to the time crystals. So time crystals are non-equilibrium phase of matter with broken time translation symmetry. Depending on which kind of symmetry it break, there are two variety of time crystal that exist. The first one is the discrete time crystal. So it breaks the discrete time translation symmetry, and the Hamiltonian of the system is periodic in time t for such system, but the state is a periodic in multiple integer of time t. And so I will be just talking about the continuous time crystal for the rest of the talk. So let me explain continuous time crystal now. So these are typically exist in open quantum system, and the master equation is of kind rho dot is equal to L rho, where L is the generator of the dynamics and is independent of time. But the state of the system is oscillating with some time period t, and it breaks the continuous time translation symmetry in the thermodynamic limit. So let me explain. It was first introduced to the boundary time crystal, where there are two parts of the system. There is a boundary. There is a bulk of the system where there are some spin exist in bulk of the system, and there are some spins which are on the boundary of the system, and they're interacting via this Hamiltonian V. And everything, these two Hamiltonian and this interaction term, everything is time independent. But in the thermodynamic limit, we can see that the boundary spins start oscillating in time and breaks the continuous time translation symmetry. So how do we observe the symmetry breaking? So we look at an order parameter O, which is like magnetization for this boundary time crystal. And we see that the system have persistent oscillation in thermodynamic limit. So you can see that when the number is finite, the oscillations are kind of transient, and in tending to infinity limit, we see the oscillations are persistent. So the boundary time crystal, the dynamics is given by the master equation of this kind, where the LCTC is the generator of the dynamics and is a variable of two, and is a function of two variables, omega and kappa, where the first term is the coherent drive, which is having strength omega, and the second one is the interaction due to the environment, and it's a dissipative term and have a strength of kappa. And depending on the ratio of omega and kappa, we can have different phases of the system. So the first one is where omega by kappa is greater than 1, then the system exhibit in time crystal phase, and this is the diagram corresponding to that. If the ratio is smaller than 1, that means the system is more dissipative than coherent drive, then we can see that the system exists in time invariant phase, and we call it a melted phase. And the system is not oscillating in time at all for those kind of, for omega by kappa smaller than 1. Now going to the point, how do we get the steady state for such a system? So the steady state solution is given by the later time dynamics of the system. And if you look at the vectorized form of the density matrix, then this is the kind of the solution we get. Now, depending on so this LCTC is a kind of non-Hermitian matrix, and it have the following, this kind of eigenvalue spectra. So the eigenvalues are complex conjugate eigenvalues, and the real part of the eigenvalues is smaller than or equal to 0. It is to preserve the positivity of the density matrix during the evolution. And now if you plug in this value of LCTC into this equation here, then we basically can get this kind of solution. So we see that here spirals and decays. So if eigenvectors have a eigenvalue with negative real part, it will just dissipate out. So the only steady state that are corresponding to, which are interesting to us, are the one where both of them, real and imaginary part, goes to 0. These are the steady state. And the second one is where there is like the eigenvalue is purely imaginary and the real part goes to 0. So the system just keep oscillating. So we are interested in this oscillating coherences, and let us see how this goes into the definition of the time crystals. So the time crystal are characterized by the non-zero imaginary part. So this corresponds to the oscillating coherences, and real part going to 0 only in the thermodynamic limit for omega by kappa greater than equal to 1. So for omega by kappa smaller than equal to 1, for any value of number of, like for any size of the system, we can never get this going to 0. And for a ratio greater than 1, if the number is finite, then the real part is still negative, but it goes to 0 only in the thermodynamic limit. And we hit oscillating coherences and we get the time crystal phase. So basically, in short, what we can say is, if you look at this axis, which is driving strength by kappa, and so if we start going from 0 to 1, the system exists in melted phase, and if it is above than 1, then we got in the time crystal phase. Now what we did, we took n such coupled time crystals, and where the first term is the dynamics of the such uncoupled crystals, and the second term is the coupling term. So we consider two different coupling, both coherent and dissipative kind of one. So the coherent coupling is where the spin is exchanged between various subsystems, and the dissipative is where the subsystem goes to the collective dissipation of the due to the environment. It's surprising to see that even for the dissipative coupling, which adds more dissipation to the system, we can observe shading effect. And the same result follows for the coherent one, but we will be just talking about the dissipative coupling here. So let me just show you the mean field analysis in thermodynamic limit. So we get this nonlinear differential equations, and these follows our, like this gives us the result for the thermodynamic limit argument. Now let me begin with that there is a system A, which is in the time crystal phase, and we call it seed, and there is a system B, which is in the melted phase, and it will not be oscillating since the ratio is smaller than 1. And we couple them via the dissipative coupling of some finite strength. So it can be seen here that for the thermodynamic limit, which is the black curve, the system start oscillating with the persistence oscillations, and the seeding is observed for the system B. And if you look at the mean field and the Fourier transform of the mean field oscillations, we see that system A and B both are oscillating at the same frequency. And now if you look at the eigenvalue spectra of the generator of the dynamics, LCTC, then we see that the eigenvalue, the dominant eigenvalue, settles down to the approximate value 0.89. So this is for the finite value of n, and now we do a functional fitting and look for the n tending to infinity, and it hits almost the same value of the frequency, which is 0.89, which was the 0.9 in the thermodynamic mean field analysis. And now if we couple them more strongly, like if we increase this coupling strength between them, then what happens after some time, both of them melt down due to the strong coupling. And this is shown by the eigenvalue spectra, where gamma is almost equal to gamma critical. We call that value to be critical value, gamma critical value. And this eigenvalue spectra shows that for such a case, the real part of the eigenvalue settles down to some negative part, and we will not see crystalline phase for such a critical value. Let me show you how do we get that kind of critical value. So we look at the fixed point for the mean field equations, and this is one of the fixed point where the system and where the m dot equation goes to 0. And for such a fixed point, this fixed point is not always a physical fixed point of the system. It's not a physical state of the system always. For this fixed point to be physical state of the system, the value of spin along y axis need to be smaller than equal to 1, since the dynamics conserves the total spin of the system. So the maximum value it can have is 1. For if we plug in this rule into the equation number 1, then we got a critical value for gamma. Now the point is that if the value of gamma is smaller than this critical value, then this fixed point is not a physical state of the system, and system can never go to it. But as soon as we reach this value, or we go above this value, the system settles down to this fixed point, which is a hyperbolic fixed point, and the oscillations dies out. So basically, in this figure here, we shows you that we show you, now we take, instead of 2, we take several different number of ensemble of subsystem. And we shows that for every kind of, you can take several melted phase and just put a crystal into it, just put a single seed into it. And we can see that for all the melted crystal, we can observe the seeding effect. And now if you look at the second diagram here, so the y-axis is the observed frequency for any subsystem for a given ensemble of the subsystem. So we see that they are oscillating with a finite frequency up to a finite coupling strength, but after just the critical coupling strength, they melts down and there is no oscillations, and we go into the unbroken phase. So again, going to the simple fact that if there is this x-axis is the coupling strength, If we start coupling them, if it is greater than 0, then we can observe shading effect. With the increase in strength, we can observe the increase in the amplitude of the oscillation. But after coupling, critical coupling strength, everything melts down. Even the shading crystal also melts down along with that. And now at the end, we take 2 such time crystals, which are also now both of them are in the time crystal phase, but they have different oscillation, their intrinsic oscillation frequencies. And we try to study the synchronization of 2 such time crystals, and by this value gamma. So the x-axis is the difference between the natural frequencies of oscillation. I just call it detuning between the natural frequencies, and y-axis is the critical, y-axis is the coupling strength between such oscillators. And this heat map is for the observed value of detuning between 2 such systems. If they are oscillating with the same frequency in the observed frequencies, then this value is 0. Otherwise, it's a finite value. Now, now it's surprising to see that when the systems are not identical, like they are far detuned from each other, then we require a very, very small coupling strength to get them synchronized. On the other hand, when they are very identical to each other and the detuning is really small, we require really high value of coupling strength to get them synchronized. So if we look along this black dotted line, so it can be just we can just observe 3 phases here. The first one is when there is a finite detuning. There is up to some finite value. Both of them are oscillating, but they are oscillating with the different frequencies, and they are in the unsynchronized region here. And as soon as we cross this finite value of coupling strength, we got into the synchronization phase, which is up to some value here. And if we go above the critical coupling strength, then again, everything's melt down. So in conclusion, I would just like to say that we observe shading effect for the continuous time crystal for both coherent and dissipative kind of coupling. And then we observe that for very, very strong coupled system, the entire ensemble of the time crystal melts down, even the seed also melts down with them. And in the end, it's observed for the very first time that the highly detuned systems require very less coupling strength and vice versa. So thanks a lot.
Okay, thank you, Parvinder. We have maybe time for one super quick question. So if anyone has a question, please just unmute yourself and proceed.
Hi, Parvinder, Kishore here. So I have a question in the slide number 13. Yeah, in these pictures, you explained all 3 phenomena, unbroken, synchronized, so by looking the color contrast. But I'm a little confused how you distinguish the unbroken and synchronized part, because both the color is, for me,
Right.
is looking the same. So I just want a clarification, just for the curiosity to know how you distinguish these things.
Sure. So you can see this white dotted line, right? So
Yeah,
we
yeah.
have given you this critical value of coupling strength. So if we go above that critical value of coupling strength, everything melts down, and you are right. Actually, both of the oscillations dies out, though the difference is also going to be 0. So that's why this is of the same color with when they are exactly matched with each other, when they're non-zero, right? So we distinguish these 2 phases by this critical value of coupling strength, which we obtained in this equation here. So above this, nothing is oscillating, that's why it's 0. But below this, they are oscillating with the same frequency, and that's why it's 0. They're like omega is equal to omega. And we distinguish it between them by using the critical value that we obtained by equation number 2 here.
Okay, I got the point. Yeah,
Okay.
thanks.
Thank you, Parvinder. So let's thank Parvinder for this nice talk, and let's move on to our next speaker. So I request Siddharth to set up while I briefly introduce Siddharth. So Siddharth is our next speaker, Siddharth Rastogi. He's currently a PhD student with Professors Shuddho Mahapatra from our department and Kasturi Saha from the electrical engineering department. And he got a BTech, MTech in engineering physics from IIT Agartala, and has been working with Shuddho and Kasturi for about a year now. Take it away, Siddharth.
Okay, so thanks for the introduction. Hi, everyone. I am assuming my screen is visible. Hello?
Yes, Siddharth. Yes, and we can hear you.
Okay, so hi, everyone. My name is Siddharth Rastogi, and I am from CRNTS department. And my topic of today's talk is fabrication of quantum rods towards realization of a spin quantum computing architecture. Okay, so here is the outline of the talk. First, I will start out with a introduction to the spin qubit. Then I will describe what is the spin quantum computing architecture. And in this architecture, you will see that the important component is the quantum dots, which is to confine the single electron. So I will describe what are the process steps in fabrication of quantum dots. And as you will see, for realization of such a quantum dots, we need the patterning of what is known as surface gates. So at the end, I will show you the progress that we had made in this direction. So first thing come first, what is the electron spin qubit? So let us consider a 3D confined electron in a single silicon crystal. Well, we apply a magnetic field, then this orbital ground state of this electron will split up into spin up and spin down state. That is known as Zeeman splitting. So essentially, what we have created here, what is so-called quantum two-level system. One can assign cat 0 to the one level, and the other level one can assign to the cat 1. So the general state of the electron can be represented in terms of psi, which is the linear superposition of these two basis states. In particular, for our case, spin up and spin down state. That is allowed by the superposition principle. And that is the definition of the quantum bit or qubit. And for the spin case, spin qubit. So unlike the classical bit, which can exist in a state 0 and 1, qubit can exist any superposition states of the 0 and 1, or in particular, any superposition of the spin up and spin down state. So that's all about the electron spin qubit. I will not go any further detail in today's talk, but what concerns us today in this talk, how do we create this 3D confinement potential? So in the remaining of my talk, I will focus on this confinement potential, or what we popularly called as quantum dots. So from here, let us see how we make the quantum dots. So to make the quantum dots, first thing that, to make the quantum dot, let me explain the simple device that is known to most of you, that is metal oxide field effect transistor. So in fact, this is a 3-terminal device with a source, drain, and the gate. So if we didn't apply any bias to the gate terminal, then there is no current through the device. And because this is a there is a p-type silicon in between source and the drain. Now let us find this answer in terms of the conduction band profile diagram along this direction. You can clearly see even in the band diagram, there is a barrier in between source and the drain. So that's why there is no current. Now the question, how we overcome this barrier, or how we overcome this barrier such that there is a current flow through the device. Well, if this is a p-type silicon material, you apply the gate terminal to the positive bias. And that's how you form the channel. And how this thing reflects in terms of the conduction band profile, you can clearly see after applying this potential, this conduction band suppresses this Fermi energy level, and that's how you set up the current in the device. And this channel can be viewed as a 2D electron gas, because the electrons or the carriers in this channel are free to move parallel to the interface, whereas it is confined perpendicular to the interface in which we had applied the fields. So that is what is known as 2D electron gas. Now let us see how we make the quantum dots. So again, look at this MOSFET. To make the quantum dot, we split this metallic gate or fragment this metallic gates into multiple gates. That is maroon one and the green one. And we apply a positive and the negative bias in an alternating manner. So if you are seeing from the analogy, wherever we had applied the positive gas, we retain the 2D electron gas or the channel. Wherever we had applied this negative bias, we deplete the channel, selectively deplete the channel. If you look at the thing in terms of energy band profile diagram, or if you want to compare with the previous one, you can clearly see wherever I had applied this negative bias, the potential goes up. Whereas wherever I had applied this positive bias, this potential goes down. So essentially, in a nutshell, what we had done further confinement within this channel. And this is how we create the quantum dot, which is to confine the single electron. So now we know how the quantum dot actually forms. So let us see what are the process steps involved in making such a device. So from a schematic, it is clear the most challenging part to making such a device is to fabricate or to make these surface gates, which is of the order of sub 50 nanometer surface gates. And what is needed for 3D confinement potential? To appreciate this thing fully, I am showing you here the top view of the device, a real SEM images that is taken from the Professor Peta Group Princeton. As you can clearly see from the scale bar, that the feature from the surface as narrow as 50 nanometer. So I preserve the color code. The maroon one here is the accumulation gate, which is responsible for the formation of 2D electron gas. And the green one is the depletion gate, which is responsible to selectively deplete this channel. And in this design, there is one extra gate.
Siddharth, couple of minutes, sir.
Okay. So in this design, you can clearly see there is a one special type of gate that is known as confinement gate, which I will tell you in the next slide. In fact, these three layers are separated by a good insulator in between them. If you are seeing from the schematic, since we wanted to give different polarity between these two gates, so we have a good insulator between gate layers. And as usual in the design, ion implantation for making this source and the drain. So toward this goal, that is optimizing the surface gate, we first develop a computer-aided design for that, as you are seeing here, to exactly replicate the same images that you are seeing on the top. The only difference is that it is symmetric about this horizontal axis. Means we have the dots on the top axis as well as the bottom axis. As it is this design we are trying to optimize at the moment. But we are still in an optimizing phase of insulator between gate layers and the ion implantation for ohmic contacts. But for the rest of my talk, I will focus on this fabrication of sub 50 nanometer surface gates. So let us see within this architecture how the quantum dot actually form. So to form the quantum dot, we first fabricate the confinement gate. So confinement gate is the electrostatic shielding layer. In fact, this is a 3-layer devices. So electrostatic shielding layer and gives you the electrostatic shielding, which is coming from the subsequent layers. So first we bring the confinement gate, then we bring in the accumulation gate, then we bring in the depletion gate. And of course, there is a good insulation in between all of them. Again, we did this same thing. we give the positive bias to the accumulation gate. When we apply the positive bias to the accumulation gate, it just forms the 2D channel or 2D electron gate underneath these gates. If we apply a negative bias to the depletion gate, which is selectively deplete this channel underneath of these gates. And that's how we again get the same potential profile or to trap the electron. And if you check the potential profile, one of the top part, it exactly looks like this same. Now, let me show you the fabrication of 50 nanometer surface gates. So this is the process flow of surface gate fabrication. So we started out with a silicon substrate. Then we do the resist spinning, in particular first layer PMMA. Then we do the resist spinning, second layer PMMA, and then we bake it. For us, it turns out 180 degrees centigrade for 2 minutes. Then we do the patterning with electron beam lithography, very sophisticated technique to write down the feature less than 200 or 300 nanometer. Then we do the development in MIVK IPA for 20 seconds. After that, it just sort of opens the profile in the resist. Then we do the metal deposition using a sputter tool. And after the liftoff, whatever pattern you had want to generate is completely transferred on the surface of the silicon wafer. So that's how the process flow of surface gates fabrication goes. Now that you have understood the process flow, these are the two designs that we have chosen for the optimization purpose. If you recall from the previous slide, the left one is the confinement gate, whereas the right one is the depletion gate. So we carried out our optimization on these two kind of gate structure. Just you give an overview of the entire effort, we choose 4 different doses. And for each of these doses, we make 5 copies of pattern. So we optimize the development time and finally concluded this 460 dose and 20 second works for us in those runs. So of course, this will took us 3 months of optimization and roughly 300 devices to conclude this. So let me show you the best result that we had optimized. So let me start it out with the depletion gate. You can see the successive zoom in images as you go along the diagonal. Just you give the idea about the how well lithographic process work for us. I will show you the dimensions here. So it is in the CAD file, it is intended to make 50 nanometer, whereas we get 25 nanometer. And this gap, horizontal gap, is 60 nanometer, and intended to make 60 nanometer, whereas we get around 70 nanometer. And the lead, the one of the depletion gate, is intended to make 70 nanometer, whereas we get 78 nanometer. So this is most likely due to the proximity effect in the electron beam lithography that we never beat this, but one can readjust this file according to this parameter that we get. So again, the best result that we had obtained in terms of confinement gate or fabrication of confinement gate, here is the dimension that is not more important for us. The gap that we intended is 70 nanometer, whereas we get 30 nanometer. This is again most likely due to the proximity effect. So at last, in a nutshell, we believe that we had optimized the most critical step of this quantum computing architecture. Thank you.
Thank you, Siddharth. Very nice talk. So do we have a quick question?
Yeah, Sai, I can just ask something very quickly. Yeah,
Sure.
Siddharth?
Yes.
Yeah, could you just tell me how can you ensure that you just have a single electron trapped in one of these places?
Yeah. So
मैं घंटों तक कर सकती हूँ है इतना पोटेंशियल है yes
so see this single electron trapping will depend upon this dimension of surface gates as far as okay, so this single electron trapping is depending upon this dimension of surface gates. So what you will do, you will narrow these dimensions such that even in the if you look at from the one dimension confinement potential, if you narrow the width, then the energy of this spectrum goes n square pi square h cut square divided by 2s m a square. So if you narrow the width, then the delta E goes then the delta E delta E gives you the much larger separation, and that's how you so it will depends upon the basically the dimension of this this surface gates as far as I know, and we need to perform the simulation to check this.
Okay, thanks. Yeah.
Okay, thank you, Siddharth. Let's all thank Siddharth for that very nice talk. And could I request Manoj to set up while I introduce Manoj? So we have two more talks in this session. So our next speaker is Dr. Manoj Arvind from Professor Puneet's group. He previously IISER Mohali with Professor Sudeshna Sinha and has been a postdoc, an institute postdoc for a little over a year. So today Manoj will talk about synchronization. Take it away, Manoj.
Yes, thank you, Professor Sai. I thank the organizers for the opportunity. Now, varying from the previous talks, my talk is purely classical, both in the physics and in the computation that we're trying to establish. The current talk is about a recent work where we use the interplay between noise and nonlinearity in dynamical systems to achieve gates, logic gates that work with the help of noise. So before I kind of deep dive into exactly what we've done, I'll touch upon what are logic gates. A logic gate is a physical device that implements a Boolean function. And a Boolean function is a logical operation that is performed on one or more binary inputs that produces a single binary output. For example, let us look at the AND gate over here. An AND gate takes two binary inputs and gives an output 1 only when the input A and B are both 1. So in a similar fashion, there are 6 two-input logic gates that exist, and this work is where we show how we can make all 6 of these from a single physical device using how noise and nonlinearity interplay with each other. So the core system that we're going to be working with throughout is a simple bistable system. A bistable system is a dynamical system that has 2 stable states. Here we are working with dynamical systems that have 2 fixed points, which is like the simplest case you can have, and which is simply achieved by taking a bistable potential as shown. And the governing equations are simply x dot equals minus dv by dx, which gives you a system that has 2 fixed points. Specifically, what we are interested is how such a bistable system interacts with a noise that is added into the system. The noise being added here is a Gaussian noise and with a noise strength of T. So to sort of get a feel for the kind of dynamics that such a system would exhibit, I would add a small amount of noise to such a system and show you the time trails of how the system evolves. What we see is that since it's a simple bistable system, it's trapped in one of the wells here. Here the system is trapped at plus 0.5, and because of the small amount of noise, there are mild jiggles within that potential well. And as I increase the amount of noise in the system, the jiggles within the well become larger. And beyond a threshold amount of noise, the noise itself facilitates the transition between the two potential wells. It provokes these transitions. And for a very high amount of noise, these transitions are too frequent. So frequent that the bistability itself seems to have, in some sense, seems to be non-existent. But what we are interested in is this middle realm of noises, where the noise somehow aids in making these transitions between the potential wells, while the bistability of the system itself is retained. And as we can see, all activity in such a noise-driven bistable system can simply be viewed as noise-induced transitions between the potential wells. So the question that one was interested in is, given these middle realms of noise, is there a possibility that noise will enhance a sub-threshold signal, a very small signal that itself cannot facilitate a transition between the wells, but because of the presence of this optimal amount of noise, can these transitions happen? And that very idea is called stochastic resonance, where we take the exact same system and we add a small subthreshold signal to it. And as you can see, this subthreshold signal is not enough to cause the transition between the two potential wells, and when the noise is very low in the system. And when the noise is high, there is literally no correlation between the output of the system and the input signal. Whereas when you have this middle realm of noise, there is very high correlation between what the system does and the kind of sub-threshold input signal that you feed into the system. So now, given that we know that we can detect sub-threshold input signals using this interplay between noise and bistability, the simple question arises is, can you process these input signals in some sense? And the most fundamental thing that you can do with two input signals, two binary input signals, is, can you make a logic gate of it? And the answer is yes, and we're going to show how. So the question we are asking is, we take two such bistable systems and you couple them, and we see, can the collective response of these two coupled bistable systems give some kind of a logical output of the two signals. To do this, what we do is we take two such bistable systems and we couple them either through an attractive interaction or a repulsive interaction. And we both of them are fed Gaussian white noises, which are uncorrelated to each other. So all correlations between the two systems come purely through the coupling term. We apply a constant bias to the system that can just tilt the well to potential wells to one side or the other. And both of the systems are fed with two sub-threshold input signals. Our aim, or what we'd expect, is the output of these two systems somehow embed the logical output of the two input signals. To see how exactly this works, I'll show you one time series of the system, where in the first two panels show the inputs, the binary inputs that are being fed into the system itself, and the third panel, green, shows the expected AND logic output for these input signals. What we have in orange and blue are the outputs of the two bistable systems that we have. And if we look carefully, what we see is that whenever the expected AND logic is 1, the two subsystems are in different potential wells, or they are away from each other, anti-synchronized to each other. And whenever the expected logic is 0, they are in the same potential well, where they are synchronized to each other. So we come to this conclusion that the synchronization state of the coupled system in this construct that we've built intentionally encodes the binary output of the specific logic gate that we've designed it to operate as. And the convention that we adopt is the same. Well, synchronized state means 0, and an anti-synchronized state means a 1. To also show that this works experimentally, we construct a very simple electronic circuit on breadboards, and we test the idea out. And as you can see on the right from the oscilloscope time trails from the circuit, that the voltage response is also pretty identically mimic the results that we get from simulation. And we see that whenever there is an AND logic is pretty faithfully reproduced. So now what we've done here is we've shown that this works for one specific set of parameters. We've shown one noise strength, one coupling strength. For some bias, there's AND logic happening somehow. Now we explore. We would like to explore the full parameter space to see where all what logic occurs. To do this, we construct a simple measure of reliability where we drive the system with a large set of inputs, and we just keep measuring the outputs and see when all do you robustly get the desired gate that you would like. So the fraction of right answers essentially gives you fraction of times the system consistently throws the right answer, gives you a measure of reliability. And we plot this measure of reliability over the two parameters of the system, which is the strength of the coupling and the amount of noise in the system. And we see this large region of yellow, which is almost a probability of 1. So we get robust logic operations for this large region in parameter space. And the interesting bit is if we use the form of the coupling, whether it's attractive or repulsive, and we use the bias, which is the asymmetrizing factor in the equation, we can obtain all 6 fundamental logic gates, input logic gates from one physical unit itself. And this is what is shown in this set of probability plots that I've given here. And we also went on to measure this experimentally from the circuits that we constructed. So what you see here are essentially 2D cross sections of all these heat maps that you see in the previous page. And we clearly see again a maximization of probability of logic. So which means we get robust logic whenever we are in this area, even in the proof of principle experimental setup that we had built. So to sort of summarize the set of results that are here, we get robust logic operations for optimal values of noise strength and coupling strength. We can use the bias and the coupling form as morphing controls to produce all 6 logic operations from a single unit. And we use a stringent measure of reliability to make sure that the logic gate works well. This current paper has been accepted for publication in Physical Review E and is currently in press. And I'm open for any questions. Thank you.
Thank you, Manoj. Fantastic. We actually have a couple of minutes for questions. So are there any questions? So while we're waiting, Manoj, let me ask a question. So Manoj, typically in physical systems, the noise strength is not the same, no? Like it kind of oscillates up and down typically. So this threshold that you're talking about, the threshold amount of noise for stochastic resonance, for instance, how does it, what's the physical logic of it? Is it that there are some systems where I'm just raw level is constant in its amplitude as well, in its strength as well?
So what we are doing is a pure simulation construct, and what we are putting forward is a proof of principle. But to implement this in real systems in a probability circuit in production, we would probably have to study the background noise involved in the system and tailor it to specifically that need. But what we've done is simply shown that such a thing is possible. As you're saying, I'm sure the strength of the noise itself might vary in real systems, and you might have to work around it or engineer your way around that constraint.
Sure. Any other questions? Okay, if not, let's thank Manoj.
Sai, I'll just ask.
Himadri, go ahead.
Yeah, Manoj, you were showing those plots where you have those probabilities equal to 1. Like, yeah, could you just explain? I just missed a little bit of in between. Like, what are these plots exactly?
Sure. What I had shown in the previous slide is I've shown that our system works as intended, as specific logic gates for specific values of system parameters. And what we would like to see is, so the system parameters are noise strength and coupling strength. That's about it. So we are just exploring the parameter space of noise strength and coupling strength and seeing where robust logic operation occurs. Because if the noise is too high, then it disrupts all intended design. And there is a specific range of coupling strengths where this interaction between the two subsystems is possible. So we are finding out the optimal range of range in parameters where robust logic occurs. And what I've shown in all other, so what I've also shown is that if you change the form of coupling from the attractive, you go to repulsive coupling, and by changing an asymmetrizing bias, by making it either negative or zero, you obtain different logic. You obtain all 6 2-input logics that you can get from this system. So this imparts reconfigurability.
Yeah. Thank you. I'd actually lost connection at this point. So yeah, thank you. And thank you for the nice talk. Yeah.
Thank you.
Thank you, Manoj. So let's thank Manoj for that nice talk. And so let's move on to our next speaker. So can I request Shiva to set up while I introduce the speaker? So our next speaker is Dr. Shiva Dikshit. Again, she's a postdoc in Professor Puneet's group for a little less than a year. And she obtained her PhD from Central University of Rajasthan with Professor Manish Shrimali. So Shiva, please take it away.
Yeah, am I audible?
Yes.
Okay. Thank you, Professor Sai, for introducing me. Okay, so before I start, I would like to thank the organizer for giving me this opportunity to present my work. So title of today's talk will be Regulating Dynamics Through Intermittent Interaction. And the outline will be like this. I will talk about the dynamical system, some brief introduction with examples, interaction and emergent patterns that arises because of the interaction in between these systems. Then I will discuss the control mechanism, which is known as the spatial dynamic interaction and temporal dynamic interaction, followed by results and discussion. Then I will conclude my talk. So dynamical system is any system that changes in time. Systems are never isolated. They always interact with each other. Some of the important phenomena that arises because of the interaction are the synchronization, where the incoherent dynamics of the system becomes coherent. The famous example of the synchronization is the clapping of audience. Like in a hall, initially clapping was not synchronized, but as the time passes, the frequency of the clapping increases and it becomes synchronized. Another fascinating behavior is the suppression of oscillations, where the oscillations of the system are suppressed such that the dynamics settle down to a fixed point. If anyone wants to know more about these interesting phenomena, one can refer the synchronization Peikoski book as well as these two physics reports. So yeah. Okay, people have studied the interaction so far, but they have considered the continuous interaction where the cost of control is high. So the idea was that if the desired output is same, why to apply interaction continuous? Because it's a continuous exchange of the information. So there are many systems too, like over time, we all know human context change because of the individual lost old acquaintances and acquire new ones because of the many reasons, like movements between home and workplace. Another example is like in ecology, migration and cross-predation is dynamic, where sometime migration dominates as well as another time cross-predation dominates. Another is a well-known example is like Wi-Fi. We all know whenever we are in a certain proximity range, our devices are connected to the Wi-Fi, and as we are away from that range, we are not able to connect with the devices. So motivated by these some examples, we have taken this intermittent interaction. So our technique is very generic. We have checked in many systems, but experimentally we checked in the Chua circuit. Chua circuit is a simple nonlinear circuit that exhibits chaos. We coupled the y variable of the system, and here this is the bifurcation diagram. This is the bifurcation diagram. So what is the bifurcation diagram? Is a summary where just by tuning the parameter, we are able to see the qualitative change in a system. Here, this blue inset is the double scroll chaotic attractor. And as we are increasing this R, which is the variable resistance parameter, we are able to see the change in the dynamics of the system, like periodic as well as fixed point. And red inset is the fixed point case. In our work, we have taken two cases, double scroll chaotic attractor case and the fixed point case. But because of the time constraint, I will present here only the first case. If someone wants to know more about the second case, I'm free to discuss. Okay, so what is intermittent interaction? There are two schemes. First one is the spatial dynamic interaction and another one is the temporal dynamic interaction. In first one, the position of the state variable is going to decide where the interaction is on and off. Like in this figure, left hand side, as this dotted line is the threshold, and as we are increasing the threshold, the interaction we are increasing the on interaction region. So while in another case, which is known as the temporal dynamic interaction, interaction is on and off periodical. So the basic difference in between both these schemes is that in first case, the position of the state variable is going to decide where interaction is on and off, while in second case, interaction is on and off according to the time. So yeah, this is the experimental setup that we used. We have taken two Chua circuit, and in this interaction control unit, we have make that the control part, which is the SD like spatial dynamic part and temporal dynamic part, and accordingly we did this experiment. So the result part, I will discuss the first case where h is the function of time, and we have taken the double scroll chaotic case. Here and left hand side, we have plotted the parameter space between coupling strength and tau. Tau is the interaction active time. So as one can see, we are decreasing the interaction active time. We are able to see the transition from oscillatory to steady state. Here OS is the oscillatory state and SS is the steady state. And I have plotted the bifurcation diagram at this discrete epsilon value 0.5. And here one can see that as we are increasing the interaction active time, we are able to see the transition like from fixed point to single scroll chaotic to periodic to double scroll chaotic. And right hand side are the result of experimental results. And as we are in experiment, as we are decreasing the duty cycle, we are able to see the same transition as we are getting in the numerical results, like the transition from double scroll to single scroll to fixed point. Next case is the spatial dynamic interaction case. Again, the parameters are same, just by we have changed the scheme. Here, delta is the interaction active state space region. And as we are decreasing the delta or we are decreasing the threshold, we are able to see the transition from oscillatory state to bistable to steady state. Here, bistable means the coexistent state of two stable states. In our case, two stable states are oscillatory state and steady state. We have plotted the bifurcation diagram at this discrete epsilon value, and we are exactly able to see just by tuning this delta, like interaction active state, we are able to see this period doubling scenario here, like fixed point to bistable to periodic to single scroll to double scroll. And in experiment 2, as we are decreasing the threshold, which is known as delta, we are able to see the same transition from double scroll to bistable to fixed point. Okay, so if I summarize today's talk, I can say that we have studied both numerically and experimentally this intermittent interaction, and we are just by tuning this interaction active state space and interaction active time, we are able to see this transition from double scroll to single scroll to periodic to fixed point and vice versa. So, okay. So I would like to acknowledge some important person in this work. My colleague, Dr. Manoj Arvind from IIT Bombay, my postdoc supervisor, Professor Puneet Parmananda from IIT Bombay, and entire NLD lab, Department of Physics, IIT Bombay. Thank you so much for your patience, and I'm open for the questions.
Thank you, Shiva, for that wonderful talk. So are there any questions? So let me ask a quick question, Shiva. So one of the kind of classic examples of this kind of, intermittent interaction where well, you can tell me if this is a wrong example, but what comes to mind is kick tops, right? So where you basically just periodically kick a system. So for a little while, basically, it's just evolving under free evolution, and then you get a kick. So is this kind of a system also amenable to this discussion, or is it a different story? Because we know what happens to the kick top. So I was trying to connect it to kind of a, or is it only basically where you have the variables interacting with each other in a temporal fashion?
True. So yeah, it's a very interesting direction to think about it. But I'm not very sure it is going to apply there. I will think about it. Yeah.
Yeah, I'm not sure the question is entirely valid as well. Yeah, okay, very good. Other questions? Okay, if there are no more questions, let's thank Shiva again for this wonderful talk, and let's also thank all of the speakers in this session. So right now we move on to the next talk, and so I revert back to the organizers. Thank you very much, everyone.
Hello. So I would like to thank Professor Sai and Professor Himadri for chairing and evaluating the session. And our next speaker will be Professor Aninda Sinha. And I would like to invite Professor Rama Devi ma'am to chair the session. Over to you, ma'am. Thanks.
Yeah. Can you all hear me?
Yes, ma'am. You are audible.
Hi, Ananda. So I think time is like really tight, so we will start off. So just to highlight, he's a professor in IISc Center for High Energy Physics in IISc, and he has got a lot of awards. To name a few of them, I think ICTP Prize, Swarna Jayanti, Bhatnagar. So maybe I'm missing many more. But let's hear from him an important topic, QFT without Feynman diagrams. And let's start off your talk, Aninda.
Thank you very much, Rama. So can you see my screen, and yes, can you see my pointer? Yes. Very importantly. Okay. Thank you very much for the invitation. It's very nice to be in your presence. I will tell you about quantum field theory without Feynman diagram. So this is a contrarian viewpoint to what you must have heard in your quantum field theory courses that you take conventionally. One of the things that we are interested as theoretical physicists, especially when we are particle physicists, is to calculate the probability amplitude for a process that is on the left, where you have two incoming particles. They could be any incoming particles. They could be photons, they could be gravitons, they could be electrons, standard things, and two outgoing particles. So my time flows to the right. And what I've depicted here is what is called the tree-level Feynman diagram for 2-to-2 scattering. 2-to-2 means that two incoming particles and two outgoing particles. Now, when you draw a diagram like this, this presupposes a knowledge of the spectrum of particles, because one thing is that, of course, when you're scattering things in a lab, then you must be making these particles somehow, and then you must be detecting these outgoing particles. And also to model what you are measuring in experiments, you also require to know what are these virtual exchanges. Now, all that is good, but if the spectrum of the real world is pretty complicated, so for example, suppose the spectrum of the real world looks like this. So you have some low mass particle that you can directly measure or directly detect in experiments. And then there is some gap, and then there is maybe a tower of infinite tower of maybe higher spin massive particles, which are too massive and you cannot directly detect. Then this framework here that that I'm talking about is not adequate to capture or to fully tell you about what the true probability amplitude is. So if you're interested in talking about observables, so the observables means that you know what you're scattering and what you're measuring in detectors, then we need a framework where you do not have to worry about what particle is getting exchanged. And the framework should be versatile enough to account for gravity. So this is something that, of course, standard quantum field theory finds it difficult. As soon as you incorporate loops, you encounter problems. And definitely at the bare minimum level, whatever framework you're talking about should constrain the theory space. It should not be as if, there is an infinite class of theories, so presumably your framework does not have any predictive power. So it should be constraining enough so that you can make predictions. So the framework that I'm going to talk about is called the bootstrap, and is going to be the focus of my talk. And so let me begin by telling you what the meaning of bootstrap is, because you might think that it has something to do with your shoelaces. It's not quite there. I mean, the way that the word bootstrap is used is it's used as an adjective. It is used in the spirit that you rely entirely on your own effort and resources, and it should be self-generating or self-sustaining. So that is what bootstrap in this context means. And my talk is based on these series of papers that I've written with my collaborators over the last 6 years or so. So with my graduate students and also my collaborator in ICT, Rajesh Gobakumar. And I should highlight these blue people here are undergraduates, very smart undergraduates in IISc who helped me set up the S-Matrix Bootstrap program, which I'm going to briefly talk about later on in my talk. So there have been a lot of important contributors, and without graduate students and without the hard work of undergraduates and also master's thesis students, it wouldn't have been possible. So let me begin by telling you about why we need quantum fields. I mean, this is something that maybe it's not very well appreciated, but the reason why we need quantum fields is because the classical picture contradicts special theory of relativity. So if you want to describe, say, the force between the Earth and the Sun, we learn in school that there is some equation that looks like this, 1 over r square, and similarly for the Coulomb force, there is a similar 1 over r square equation. But the problem with this description is that the force appears to be instantaneous, and you know that this is not possible. It contradicts Einstein's special relativity. And one cure, the standard cure for this is that you speak in terms of fields. So in the context of quantum mechanics, this was cured in the cure for this problem was found in the 1930s via the Dirac equation, which was the correct relativistic description of the electron. Now, historically, of course, when you learn quantum mechanics for the first time, this is not how you learn it. You begin by saying that you presumably talk about the Planck's radiation formula, and then you go on to learning the Bohr model and then Schrodinger's equation. And typically in the first course in quantum mechanics, or maybe even the second course in quantum mechanics, you don't hear the word quantum field. But historically, and it is quite interesting to note that Schrodinger, he actually, when he was trying to write down a wave equation, he wanted to write down a wave equation that was compatible with relativity. And he came up with what is, in modern day, we call the Klein-Gordon equation. And now the Klein-Gordon equation is not the correct description of the hydrogen atom, the energy levels of the hydrogen atom, because the Klein-Gordon equation describes a spin zero particle, whereas the correct description should have involved a spin half particle. So he abandoned this Klein-Gordon equation, and then he wrote down a non-relativistic equation, which is now we identify as the Schrodinger equation. But the relativistic version of this was written down by Dirac in 1927. And this had lots of ramifications. For starters, it predicted antiparticles. So as soon as you predict antiparticles, you have to take into account particle creation annihilation, because a particle and antiparticle can annihilate into a photon, virtual photon, and then so your framework has to take into account these kind of processes. And so this was the birth of quantum field theory. So this is Dirac here, young Dirac, and he's going to play a very crucial role in my talk. Now, of course, now you're all aware of various famous fields. Arguably the most famous field that all of us know is the electromagnetic field, and this is a very often asked question, that you derive a wave equation like that, starting with source-free Maxwell's equations in PhD interview exams. This picture of the field, of course, is compatible with special theory of relativity. So then you also have the gravitational field, and from the particle physics viewpoint, there are a plethora of fields, one for each fundamental particle that we know, for example, the Higgs field. Now, the quantum of each field corresponds to a particle. So this could be a photon, graviton, electron, and so on. And technically, if you have what is called Poincare invariance, so this is a combination of Lorentz invariance and space-time translation symmetries, then what we identify as particles are supposed to be the unitary irreducible representations of the Poincare group. And this is what is called Wigner's classification theorem. So for instance, one particle states are labeled like this. So there is the momentum, the 4 momentum, and then there are extra quantum numbers. So for example, this could be the helicity for massless particles, or the J3 component of the angular momentum generators for massive particles. And multi-particle states are tensor products of these. In the standard model, which describes particle physics, we write a field for each fundamental particle that we know of, but of course we cannot take into account gravitons. And in the modern day, we know that there is internal structure. So how do we know what to call a fundamental particle? So we do high energy experiments. So we do deep inelastic scattering experiments, which, for example, told us that the proton has a substructure. And that is how we kind of know what is fundamental and what may be composite. Now, unfortunately, this is not how the story of quantum field theory evolved. And historically, this is not. It was not as if there was a smooth flow chart and people knew logically that they wanted to go from this step to this step. And in fact, the situation was so murky that the founding fathers of quantum field theory were ready to ditch quantum field theory and try to come up with a new framework. And it is only the younger generation here, ironically, played the role of the conservative, played a conservative role and took the framework forward. So what was the problem? So the problem is you encounter ultraviolet divergences. So a simple example of an ultraviolet divergence is if you have a propagator. In this particular case, it's some massless limit of some propagator that I've indicated here. And you can easily see that this integral has to diverge because there are more powers in the numerator of Q than in the denominator. And the calculation for such things are going to be infinite. And in fact, one would have thought that, okay, but if you are seeing infinities, maybe it's pointless to carry this framework forward. But of course, that is not how it worked. People knew how to remove these infinities and came up with very, very powerful predictions, which led to an impressive match between theory and experiment. So for example, this is the anomalous magnetic moment for the electron. And that matches with experimental result up to some humongous precision, up to 10 decimal places or so. So up till here. And even the one loop calculation for the anomalous magnetic moment of the electron, which for which you require to calculate this Feynman diagram, it agrees to 5 decimal places. So people knew how to remove these infinities, and we know how to deal with this in modern day through a framework called renormalization. And so historically, quantum field theory began to be developed by shoving infinities under the carpet, but in a physical way. It's not as if that we decided to just get one infinity and subtract off the infinity and just focus on the finite. That does not make any sense, mathematical sense. And there was further impetus because in the 1970s, quantum theory of strong interactions, which is called quantum chromodynamics, I noticed that there are two talks after mine which are related to this, was developed. And there was electroweak unification, the vector bosons were predicted. So there was a lot of success in this framework. And of course, it's absolutely very, very impressive that with 19 parameters or so, the standard model can predict millions of experimental results. You just open the PDG and you will see that there are a humongous number of results which the standard model can predict. But of course, this is impressive enough. But as I told you that there are drawbacks. So there's ample evidence that this framework cannot be the final theory. I don't think anybody actually thinks that this is going to be the final theory. For starters, we cannot include gravity. And also there are many calculations. So for example, when you're scattering gluons, these calculations appear to be unnecessarily hard. So when you do a second course in quantum field theory, we encounter a procedure which is called the Fourier-Popov procedure. Now I've always found that very, very contorted and roundabout. And I'm sure many of you also have felt the same way. Now, as I told you, Dirac is going to play an important role in my talk. And he was the founding father of quantum field theory. So what would Dirac say? Now, Dirac was a very interesting man. And he has a very, very nice biography written by Graham Fermello, which is called The Strangest Man. And here in this biography, you learn a lot about Dirac's personality. He was quite a weird man. But you also get an indication of how strongly against he was, how against renormalization Dirac was. And in fact, if you don't want to read this biography, there is a YouTube interview that Dirac, sorry, it's not a YouTube interview, it's some interview that you can find on YouTube that Dirac gave to Hund. So of the Hund's rule for multiple, what's it called, Hund's rule for multiplicity that we learn in chemistry. That Hund. Around 17 minutes into the interview, Dirac actually spoke very little. So the entire interview is probably 20-21 minutes long. And around 17 minutes into the interview, he launches into a tirade against the existing framework of quantum field theory. And this is an interview that he gave, I think, maybe a couple of years before he died, probably in 1983 or 1984. And but in this biography, Pierre Ramond, who was one of the original contributors which led to the development of modern string theory, who was in Florida, he wanted to invite Dirac to give a talk. And Dirac, although he spent most of his life in Cambridge, but after retirement, he moved to Florida and he held a professorship there. And when Ramond invited him, he said, no, I have nothing to talk about. My life has been a failure. And this is a person who actually gave the correct relativistic description of the electron. And, coming from him, saying that my life has been a failure, Ramond was absolutely stunned. And Dirac continued to explain, quantum mechanics, once so promising to him, had ended up unable even to give a proper account of something as simple as an electron interacting with a photon. The calculations ended up with meaningless results full of infinities. And then he continued his tirade against quantum field theory and the existing framework. And clearly he was a very, very unhappy man. And I should say here that, okay, this attitude was probably a bit unnecessarily negative, because Ken Wilson's renormalization group does give computational legitimacy to quantum field theory. And Ken Wilson, of course, got the Nobel Prize in 1982. And so it was clear that Dirac had not followed any of these modern developments. But nonetheless, let's understand why Dirac was unhappy. And this is something that you should be familiar with, anybody who's done a first course in quantum field theory. You start off with, say, a scalar field theory. You would write down what is called a renormalized action, where all these parameters here are finite quantities, renormalized quantities. This coupling is also a renormalized quantity. And if you calculated correlation functions or vacuum expectation values, of these renormalized fields, you would get a finite quantity. But that is hiding something, because the second line here are what are called counter terms, and these counter terms hide infinities. These counter terms remove infinities. So for example, suppose you wanted to do a similar Lagrangian for Einstein gravity, you would require an infinite number of these counter terms. And each counter term has an ambiguity that needs a measurement to fix. So for gravity, you will require an infinite number of measurements in this framework. And that's clearly nonsense. So the bottom line is that in the framework that we are accustomed to, you remove infinities. So all calculations are schematically like infinity minus infinity. So you always have a regulator. That regulator is in place till the end of the calculation, and at the end of the calculation, you remove the regulator after you remove infinity. And Dirac's mathematical side abhorred this way of doing things. But of course, we know that this works because we have other ways of producing the same results. And but still, the question still remains: is the fact that we are encountering these kind of infinities indicative of an inherent and intrinsic problem with the framework itself? And the question is that is there a scheme to do calculations in a manifestly finite manner and not in the way of infinity minus infinity? So to satisfy Dirac's mathematical rigor, we would need to invent a method that is manifestly finite without encountering infinities, and is this possible? Now, this is not a new question. This was exactly the reason why some of the founding fathers wanted to do away with the framework of quantum field theory. So in the 1930s, the concept of what is called the S matrix was introduced by John Wheeler. And Heisenberg, in 1943, he wrote an influential paper where he said that we should be talking about observables directly and not in this funny way where we introduce a field, but the field is not directly observable, but the S matrix elements are. And also historically, it's a little funny, curious that in 1943, Heisenberg was supposed to be working on the atom bomb for Germany, for the Nazis, but it seems like he kept himself busy, he kept himself otherwise occupied thinking about foundational issues. And in the 1960s, this program of trying to deal with only observables became known as what is called the S matrix bootstrap program. And Jeffrey Chu, who was in UCLA, was one of the main contributors in the program, a main proponent of this S matrix bootstrap program. Now, this was quite a difficult framework. The bootstrap was a very difficult framework. So, because it relied only on basic principles like Lorentz invariance, unitarity, and analyticity. But on the flip side, we did not have to talk about a perturbative technique. We did not have to pretend that there was a small perturbative coupling and do perturbative calculations. So at least the framework was versatile enough to be non-perturbative. And one of the main things that it used was crossing symmetry. And of course, because of the fact that the aims of the framework was so grand, making progress in the framework was quite tough. So this approach is what is called the S matrix bootstrap. Now, to rely only on basic principles like Lorentz invariance, unitarity, analyticity, and crossing symmetry, and you try to constrain the S matrix elements directly. So let me just very quickly tell you about crossing symmetry. What is crossing symmetry? Suppose you're talking about Bhabha scattering. So this is a very famous picture. This is Bhabha on the right. This is John Wheeler. This is Hideki Yukawa and Einstein. They're taking a stroll in on the campus of IIS Princeton. So Bhabha scattering is named after Bhabha. So this is actually a process where electron, positron, electron goes to positron, electron. So these are the two Feynman diagrams. These are tree-level Feynman diagrams. There is a conservation of momentum at the vertex that gives you a Mandelstam invariant, which is made of the Lorentz square of the conserved momentum. This is conventionally denoted by S. So this is called the S channel. And similarly, there is another process where you have what is called the T channel. This is another conserved momentum on at the vertex, but instead of P1 plus P2 being conserved, it is P1 minus P3 that is being conserved at the vertex. And the Lorentz square is called T. So this is the T channel. There are two channels here. And the probability amplitude for this process is a function of these two, S and T, but also a function of the polarizations of the electrons. So these lambda 1, lambda 2, lambda 3, lambda 4. So lambda 1 and lambda 2 are the polarizations of the incoming electrons, and lambda 3 and lambda 4 are polarizations of the outgoing electrons. So crossing symmetry is the following. So this, I don't know how many of you know, this is molar, and the process electron-electron going to electron-electron is what is called molar scattering in quantum electrodynamics. So this is obtained directly from this Baba scattering in the following way. You cross over particles. So in this particular example, you cross over positrons. So you take this positron, place it on the right, and the rule is that when you take it on the right, you change the nature of the particle. A particle becomes an antiparticle. And similarly, if you take this positron and put it on the left, it becomes an electron. So this gives you another amplitude, which is given here. And what crossing symmetry tells us that these two amplitudes are related to one another. It's not a new amplitude. You don't have to do a new calculation to calculate this process. You can actually get the answer by taking this answer and analytically continuing. So this is the same function. So U is a new Mandelstam variable for the U channel. So the variables get interchanged, but that is what crossing symmetry does. Now this thing is quite non-trivial, because on the complex S-plane, say, there are cuts. There are cuts because of the fact that you can have multi-particles. You can have multi-particle states beyond the threshold. But because of these cuts, the real and imaginary parts now get related. So, and this is actually something that may be familiar to you, because this is something that in electrodynamics is what is called the Kramers-Kronig relation. And in particle physics, this is what is called the dispersion relation. So where the real and imaginary parts get related. So there is a game to be played in complex analysis here, and that is constraining enough. Now, of course, as theoretical physicists, you want to identify situations where you have more symmetries, because more symmetries you feel happier. And when you have more symmetries, you get special classes of theories, which are called conformal field theories. And this is more constraining and leads to a framework which is called the conformal bootstrap. And this was something that was pursued in the 1970s, except for two-dimensional conformal field theories, not much progress was made. But over the last 10 years or so, after the seminal work by Ratajzi, Reachcock, Tony, and Vicky, new numerical and analytical techniques have allowed us to develop this program quite a bit forward. So what is this conformal field theory, bootstrapping conformal field theory? What does this buy you? So this is the phase diagram of various substances. On the left is the phase diagram of water, and there is a famous point here which is called the critical point of water, and this kind of a critical point exists for other materials or other substances as well. For example, carbon dioxide also has a critical point, and at the critical point you have enhanced symmetry. But the goal as theoretical physicists is to predict observables at the critical point, and a framework was given to us by Ken Wilson, who got the Nobel Prize for his renormalization group program. So Ken Wilson developed an approach which is called the epsilon expansion. So he developed this with, well, essentially the first papers were written by him, and then he collaborated with Michael Fisher, and now we use what is called the Wilson-Fisher fixed point to describe these critical points. So Wilson in 1973 calculated a whole bunch of Feynman diagrams. Some of them are here. So this is the standard 5-4 theory, or some minor generalization of the 5-4 theory to n scalars. And he was doing calculations using that. So he calculated a number of loops. He also calculated a 3-loop. And he got critical exponents to describe the critical point of water and generalizations of water. Now, the standard state of the art is many loop Feynman diagrams. So the standard record is 7-loop Feynman diagram. So just imagine that you're a PhD student and your PhD advisor asked you to verify this diagram here. Now, this definitely looks like a very nice cartoon with 2 ears and so on, but you wouldn't want to calculate this for sure. And there are hundreds of diagrams of this kind appearing at 5 loops itself, and lots more that appear at higher loops. And if you were asked to verify this, your reaction would be what I would like to call a conformal scream, because you don't want to do this. You would actually want to do something else, maybe going to investment banking. And but if you knew a little bit about critical phenomena, you would say that we are doing the calculation in a very stupid way, because we are not taking into account the full symmetries. The full symmetries are not the Poincare symmetry. The Poincare generators here are these guys. But the full symmetries also include these new symmetries, which are called special conformal transformation and dilatation. And you want to use that. So you want to enlarge the framework, and you want to do the calculation using this bootstrap philosophy, which says that we don't want to deal with Feynman diagrams, because that makes the calculations murky. It hides these symmetries. And we don't want to deal with regularizations. We don't want to deal with infinities. So we want to sit at the fixed point. So there is some penalty that you paid. I can talk about that later. But you just want to use these symmetries: conformal symmetry, crossing symmetry, and unitarity. And ultimately, when you actually work a bit and develop these equations, the consistency equations actually land up being algebraic equations. And it's just algebraic equations that you can solve using Mathematica. So this is literally something that you get from Mathematica. These are the kind of things that you need to solve. Just plain algebraic equations, maybe quadratic equations. You get a quadratic equation because you're supposed to get two solutions, one corresponding to the Gaussian fixed point and one corresponding to the Wilson-Pritchard fixed point. And indeed, this is what you get using this bootstrap framework. And quite remarkably, this actually agrees with existing Feynman diagram results. So, for example, this framework is known to reproduce whatever Wilson and Когert had calculated in their famous physics reports article. But also, it gives you new results for things that the Feynman diagram approach cannot calculate, which are called results for the OPE coefficients. So these OPE coefficients, OPE stands for operator product expansion. And these OPE coefficients are, roughly speaking, the strength of interactions, so to speak. And because time is short, one of the tools that enables us to make progress is to realize that the Feynman diagram is basically a basis to expand your answer, a basis to expand your amplitude, and maybe it is not the correct basis to use for various processes. So in this particular process where we are trying to calculate critical exponents, it is certainly not the correct basis to use. The correct basis to use are what in modern parlance are called exchange-Wheaton diagrams, and this is something that is borrowed from the ADS-CFT dictionary. So if somebody tells you that the ADS-CFT is useless, it cannot calculate anything, you should take it with a grain of salt. This at least gives you this conceptual insight that that enables you to calculate algebraically without encountering infinities, critical exponents for water. So let me just move over to bootstrapping quantum field theories. So this was what I described so far was bootstrapping conformal field theories, which had these enhanced symmetries. But now I'm going to go back and tell you a bit about what you can do about quantum field theories which do not have these extra symmetries. So so what I'm going to talk about in the next 10 minutes or so is based on work that I did with my undergraduate thesis students, Sanjishnu Bose, Prithvi Sinha and Shashwat Tiwari, and my graduate student Bharti Valda, and a follow-up work with Sanjishnu and Shashwat. So, so what is it that we want to describe? So we want to describe pion scattering. So I have to give you something about the background of light mesons. So when you open the particle data group handbook, you will see that these light mesons, there are lots of light mesons. The most famous ones are pions. So these are these pi 0 and pi plus minus. And as a Bright-Wigner peak, their peaks are located at some real value plus an imaginary value. The imaginary value corresponds to the fact that the pions have finite lifetime and the decay. And in pion scattering, there are lots of other higher spin mesons that show up. The J here corresponds to spin. And there are other higher spin mesons that show up. Rho meson, for example, we know through these kind of measurements. And we know up to, say, J equal to 6 quite reliably. Now, one very interesting fact, which may not be well known to everybody, is that if you plot the spin against mass square, so mass square here corresponds to the real part of this, where the Bright-Wigner peak is located, then you get a straight line. And this is what is called the Chu-Froschi plot. And one of the challenges in the 1960s was to come up with a framework to explain the straight line. The straight line behavior is what is called the Reger behavior. And the attempts to explain this behavior is what gave rise to modern day string theory. So let's examine this process a little bit. So you want to write down the amplitude for this process, pions coming in, pions going out. So this is in the center of mass reference frame. So you have some amplitude, pions are scalar, so it makes your life simpler. If the pions were not scalars, if they were higher spins, then instead of these Legendre polynomials here, you would get what are called Wigner D functions. But nonetheless, these are all well known and you can make progress. So this is what is called a partial wave expansion. It is similar to the partial wave expansion that you have encountered in quantum mechanics. So quantum mechanics also, we do the same thing. We have a potential and we calculate, say, the probability amplitude of scattering in these potentials. It's similar to that. And these coefficients here satisfy unitarity conditions. So this kind of condition has to be satisfied. And the main tool to understand these pion scattering is unitarity and crossing symmetry again. So the unitarity condition is some nonlinear condition which looks like that, one for each intermediate spin. Now, quite remarkably, these conditions can be recast into a semi-definite programming problem. And this semi-definite programming can be solved. Okay, I mean, you require a cluster to solve it. It is difficult to solve on a desktop, but at least you can solve it. And so using this semi-definite programming, you can actually come up with a theory space for interesting amplitudes. So on the y-axis, we have S2, and on the x-axis, we have S0. It's not important for you to know what the S2 and S0 are. These are just some parameters that we dial, which are allowed to be dialed in the framework, and the minimum value that these parameters can take are 0 and 4. These crosses here are what are called chiral perturbation theory points. So you've got a description that you can use a Lagrangian and write down to explain the pion scattering data. And the state of the art is to use what is called two-loop chiral perturbation theory. And so these tree level, one loop and two loop values all cluster around some space, some region in this S2S0 plane. There is another very interesting line that you can write down, which is the old string theory that people used to write down, which is called the Lovelace-Shapiro model. This is a non-unitary model. This is not superstring theory. This is some bosonic version of string theory, which is non-unitary. So that is why these are not really physical theories, but just to benchmark, we can plot where they are. But what is interesting is that using this semi-definite programming, you can constrain the theory space. So any S matrix that is lying inside this blue region is an allowed S matrix in the sense that it is compatible with unitarity and crossing symmetry. And anything that is outside is not allowed. So that gives us a huge class of S matrices. But very interestingly enough, the chiral perturbation theory results lie close to the boundary of this region. So close to some very interesting feature in this region. So now you can say that, okay, you've got this enormous number of S matrices that can lie inside this river, and nature apparently, or QCD at least, apparently is described by this point here. So what is going on? Why this point and not say some point here, or maybe some point here or some point there? So why the standard model? And this is where we are sort of on our own, and we have to come up with some clever ideas, and we need to think about clever selection principles, because as you can realize, the questions that we are trying to address here are very different from the standard questions that you would address if you were given a Lagrangian. So this is not, you don't have a Lagrangian here. You're doing this calculation non-perturbatively. You are just constraining the theory space. So you have to be very creative in the kind of questions that you're asking, and also creative in the tools that you want to use to address these questions. So why the standard model? What is so special about that point? So here we borrow some quantum information ideas. And so one thing is that when we are scattering pions carry what is called isospin. You can calculate entanglement in this isospin variable or isospin parameter. So, like you calculate entanglement in the spin space, you can calculate entanglement in the isospin space. And what is observed is that there is a sharp drop in entanglement near the QCD values, near the standard model value. So it's as if for some reason nature is trying to minimize the amount of entanglement that it produces in the final state particles. So you can play games like this. You have got a plethora of S matrices. We numerically extracted around 200 consistent S matrices and we played around with them. And this is what we find. Now, let me tell you in the last 3-4 minutes, let me tell you about a very interesting, this bit of the story is very close to my heart. It actually connects up the scattering theory that we know and set up in particle physics with 100-year-old maths. So what is that? So first, let me just spend 1 minute explaining a bit about effective field theory. So here we have some particles coming in, some virtual exchanges happening, and particles going out. Now, if this virtual exchange corresponded to a photon or some massless particle, then the propagator for that, purely from Lorentz invariance, would quote unquote go like 1 over k square. Okay, so there is some dressing factor because of spin, but morally it would go like 1 over k square. And then you can do an inverse Fourier transform, and in position space, you can easily see that 1 over k square corresponds to 1 over r. This is a nice calculation to do. In fact, this dk k square comes from the fact that you have this Lorentz invariant measure factor d4k, and that translates into k square dk. And then this k square and this k square cancels out, and then you do a translation of variables kr equal to x, and then you immediately see that there should be 1 over r. The numerical factor you won't be able to fix using this quick argument, but at least 1 over r, the scaling you will be able to fix immediately. Now, this was the 1 over r is long range potential, so it transmits forces over long ranges. And if the particle was massive, instead of getting this long range potential, you would get a Yukawa type potential, which is 1 over r times some exponential suppression. So that massive particles, exchange particles, makes the interactions local because the range of the interaction is confined. And suppose this mass of this exchange particle is very heavy, then and you don't have access to those energy scales. What you would do is you would take this propagator and you would do a Taylor expansion. And when you do the Taylor expansion, you would get a bunch of diagrams which look like these. So these would correspond to some higher dimensional operators that you're adding to the Lagrangian. More and more higher dimensional. So this k square acting on, say, 5 to the 4. This is like 5 to the 4, and so on. And these coefficients here are what are called Wilson coefficients. Now, typically, you really don't have information about what is getting exchanged. So typically what we do in an effective field theory is we let these Wilson coefficients be arbitrary, and then we let phenomenology or experimental measurements tell us what these parameters are. So an example would be that, a non-trivial example would be that if you're doing this calculation with gravitons, these gravitons would generate higher dimensional operators, higher curvature corrections, and this is r to the 4, and why I'm writing r to the 4 is because I'm pretending that I have got 2 gravitons coming in, 2 gravitons going out. It could be something more interesting, something more esoteric, where you could have 2 gravitons coming in and maybe 2 photons going out. Then you'll have something that looks like a curvature times Maxwell field coupling. So you would have those kind of corrections in your theory. See, one question that we would want to address is that these unknowns, these Wilson coefficients, are they constrained? Or in grander words, what is the theory space? So if I plot C1 versus C2, then what is the allowed space? So if I have a situation where maybe you have this blue region, everything is allowed inside the C1, C2 blue region, and the theory that describes nature is sitting at some central point here, then I would say that this is not constraining enough. I wouldn't be able to make any predictions using this framework. On the other hand, if say you have this happy situation where you have a cutout space where the range of C1 and C2 are quite limited, and the theory that describes nature is somewhere here, then I would say that it is constraining enough. There is some predictive value. So using this kind of a this kind of a picture, what you can do is you can go back and look at what is happening at pion scattering from this numerical S matrix bootstrap game that we played. So we have a lot of S matrices, and then you can take a linear combination of these Wilson coefficients that come from these S matrices. And there's a special linear combinations. A is a special parameter. It takes on a finite range of values. It is between -8/9 and 16/9. And this I will tell you in 1 minute, literally 1 minute, why this is true. But basically, you will see that the ratio of these linear combinations are constrained. So the second guy divided by the first guy is between -2 and 2, whereas the third guy divided by the first guy is between 3 and -1. And so anything that you do, unitarity tells you that it has to be between these. So these numbers, -2 and 2 and -3 and 1, 3 and -1, are precisely what follows from what is called the Bieber-Bach conjecture in mathematics. So the Bieber-Bach conjecture in mathematics is about a function. It's a little bit more general than the function that I'm going to describe, but suppose you have a complex function, a function of a single variable z, and it is what is called typically real. Typically real means that it satisfies this condition here, imaginary part of f of z times imaginary part of z is bigger than 0 inside the unit disk. And if you do a Taylor expansion of this function, like so, then these Taylor expansion coefficient, the absolute values, are two-sided bounded. Okay, and these bounds are known. You can also ask a slightly more interesting question is that, okay, I'm saying that they're bounded, so can I know the function which is sitting at the bound or describing the bounds at which extremizes these bounds? So this is a very fascinating area of mathematics. This is Bieber-Bach and this is Rogozhinsky. Bieber-Bach was a Nazi mathematician. He drove away Jewish mathematicians from Germany. Rogozhinsky happened to be one of the Jewish mathematicians that he drove out, but Rogozhinsky was the one who actually proved in 1932 the Bieber-Bach conjecture for these typically real functions. Now, the extremal functions which give you the upper bound are some very nice looking functions, z over z minus 1 square, which are called Kobe functions. Why am I telling you this? Because in the second slide, I told you that I want to see gravity somehow. Now let's see where gravity comes from. So you see, in terms of the Mandelstam variables, you can write down amplitudes, answers for amplitudes, which are local and which allow for simple poles. So in terms of these extremal functions, I have defined this extremal function x as a Kobe function and y is some parameter times this Kobe function. You can actually show that the guy with the pole is simply x squared by y. There's nothing else that is allowed if you use locality and crossing symmetry. This x squared by y, when you rewrite it in terms of standard Mandelstam variables, is nothing but the amplitude for scalar scattering with graviton exchange. And that's quite remarkable. It seems like the theory space, the boundaries of the theory space actually knows about gravity. So gravity emerges from these considerations in this manner. So anyway, so I'm at the end of my talk. I've gone 2 minutes over time, so I apologize for that. The punchline is that these new ideas are proving very useful in rebooting the bootstrap. We have more computational powers. I think we can think in terms of new language. We can borrow, take motivation from quantum information theory ideas and so on. And now we have a framework where we explicitly demonstrated that finite methods do exist. You might have to modify the questions that you're asking. But I do believe that Dirac should have been now happier with his own existence, and he shouldn't have died as such an unhappy man. But there's a lot left to do, and one simply has to be creative and ask a doable and interesting question. And that's the point. It's very easy to ask questions, but it is very easy to ask an interesting and doable question. And the holy grail, of course, is to find the true theory of quantum gravity, which I think is out there and is waiting to be discovered. So let me stop there. Thank you for listening.
Thank you, Anindya, for this really wonderful, pedagogical talk. I'm sure all the students would have learned a lot from your talk. Let me see whether there are questions. If you raise your hands, probably I will be able to see. Any questions? I don't see any raised hands, but I just want to ask.
No, there is one raised hand.
Sorry,
Ujjit, yeah.
That's
yes.
me, Ujjit. Yeah, so I meant to ask, but at the end of the day, you will write So, I mean, two things. One is it is scattering of gravitons, right?
Yeah.
And so you will need to write an effective field theory description, but with confidence that it's going to give finite answers. Is that correct?
Not with confidence, because from the point of view of effective field theory, we would actually say that we are going to be in a weakly coupled effective field theory. So that, right now our understanding is such that when we're describing graviton scattering, if we assume weak coupling, then we can suppress these log S corrections that are going to be there, because if you have massless particles, then your amplitude will have log S's. So right now the technology is such, I'm hoping that we'll be able to understand more in a bit, in some days, is such that we can actually say that if we write down a very general set of higher curvature corrections of this kind, so that here, for example, I've written down a derivative correction, but there are other tensor structures that can appear in these corrections. But we can say with confidence, and the reason why this happens is because the graviton has a helicity. So there are the description of graviton scattering is going to be labeled by the helicity of the incoming gravitons and outgoing gravitons. So these Wilson coefficients that appear at a particular order, some combination of that we can constrain.
Okay. Okay. Yeah. Thanks. That's helpful. Okay.
So, any other question? Otherwise, I wanted to ask something. So let me see whether there are other questions. Okay, so you tried to tell us bootstrap for CFT, and then you moved on to bootstrap for QFT.
Right.
Right. CFT is applicable when you are at the critical point where you can say conformity is there, but in QFT you're only imposing unitarity, and you need a high cluster facility to constrain the theory space.
Yeah. So when I talk about, say, plots of this kind, when I'm generating, say, data that I can now then play around with, then I need a cluster. So this data was generated on a cluster. On the other hand, suppose I'm doing these kind of things where I'm checking whether these kind of bounds on the Wilson coefficients, I don't need a cluster. That I can do by hand.
Okay.
Okay. So there are two different classes of questions in the S-matrix bootstrap. One is you generate data, which satisfy these nonlinear unitarity conditions, mod of FL square less than 1. Or you can actually ask, so for example, you can ask, is C1 positive or negative? So those kind of questions require different tools. So the question of the latter kind does not require a cluster at all. You can do these things by hand on Mathematica.
But you're not imposing any more additional symmetries, right? When you're doing
that's right. Yes. Yeah.
You're just working
We're not imposing
with unitarity and the Poincare.
That's right. Yeah. So we don't impose any additional symmetry. So here I can tell you a little bit more.
I really can understand your connection to the math where, it looked like a Lorentz series to me. How does that help you to fix this ratio as x by y squared was not
very, very good. Okay, yeah. So I can go through this a little bit more. So these are Kobe extremal functions. Okay, so the thing that satisfies the fact that it is n, say, if you Taylor expand this, I think I have it, yeah. So z over z minus 1 square, if you Taylor expand around z equal to 0, has 2, 3, etc., and the coefficient is n. Okay, the Bieber-Bach-Rogowski bound tells us that the upper limit is n. So these kind of functions extremizes gives us the maximum value that this an can take in the Taylor expansion coefficient. Okay. Now we want to construct amplitudes. So now is where we have to relate the Mandelstam variables with this variable z. So I wrote it here. I did not have time to explain or focus on this, but if you focus here, can you see my pointer here on the right? So you can see the dictionary x is st plus su plus tu. So this is a combination of Mandelstam invariants, and y is this stu Mandelstam invariants. Okay. So this is such that when you actually translate the variables, you will see that in order to get a simple pole, you will require x squared by y. So how do we say that y is stu and x squared is st plus su plus tu all squared?
Okay.
Yeah. So that is how I get a simple pole, because if I did not have crossing symmetry tells me that it has to be a combination of x and y, and the only way to get a simple pole is to have stu in the denominator.
Okay.
You could have said that you can have also x in the denominator, but that gets ruled out because I did not explain to you there is something called locality. So when we impose locality, negative powers of x's are ruled out. But negative powers of y are not ruled out. So if you want a simple pose, this is the amplitude that you want to write down.
I see. Okay. So there is some amount of kind of mixing and matching in terms of SNT, finding out what the variables are to relate it to the Kobe variables and so on, right?
Yeah, that's right. I mean, yeah, so it's not a mixing and matching actually. Let me just emphasize, it's a very good question. So let me just spend 1 minute explaining why these are naturals, because it's very fascinating. So this actually arises from writing down what is called a crossing symmetric dispersion relation for 2-to-2 scattering. So this was actually written down by Oberson and Khoury way back in 1972. Okay. And but they didn't, for historical reasons, they didn't pursue it. I mean, till we actually discovered their paper, rediscovered their paper had 9 citations. And these variables are there in that paper. So you see this Zi that I write here is the cube root of unity. And when we have crossing symmetric, you have to have this permutation between ST and U. And so this cube root of unity, what it does is it enables you to do a 120-degree rotation on the Z plane to go from one channel to the other.
Okay.
And that is why you see cube root of unity. It's very fascinating. So this is something that is there in my paper with Ahmadullah Zahid that I wrote last year. Which I referred to in the beginning, yeah. But it's a very nice story, and in fact, if you really want to, then I would say that where is this? This is the paper that you should look at to find out this. Find out this dictionary. Yeah. Yes, it's a fascinating story. I think there is way more to be done here.
Okay. Yeah. So if there are no further questions. Do I see anybody raised hand? I think Urjit still has your raised hand. Is it the old hand or the
old question?
Okay. Okay. So there are no further questions. Let's thank Anindya for this excellent talk. Thank you.
Yeah. Thanks.
So then we move on to the next set of student talks. There are a couple of students who will give a 15-minute presentations who are typically on their, pre-final year or final year students. So let's listen to their talks. Who's the next one? Probably I missed the schedule here of the names.
Yes, I am.
Adipa?
Yes. I'll share the screen.
Yeah.
Can you see it?
Yeah.
Okay.
So Adiba has been working as a PhD student in our department with Sadhana Das and Basanta Nandi. She's been doing an interesting work on heavy quark transport in a viscous QGP, quark gluon plasma. So let's hear from her. So your time is starting now, so you'll get about 15 minutes.
Okay, thank you.
Yeah.
So I'm going to talk about heavy quark transport coefficients in a viscous quark gluon plasma. This work is done in collaboration with this set of people at IIT Gandhinagar, Goa and Bombay. Okay, so heavy quark, like charm and bottom, they are created perturbatively at early times in heavy ion collision experiments. As you can see from this picture, in hard partonic scattering interactions, you have a CC bar or BB bar interactions. And these CC and BB bar, as they go through the medium, they lose energy because of collision with the medium particles as well as radiation from a soft gluon. These heavy quarks are an important probes to study quark gluon plasma because they bring in a completely new energy scales. It's a smart scale into the system, which is having an intrinsic temperature scale. So heavy quark transport coefficients are sensitive to the medium evolution because
hello. Sorry to interrupt. Can you do your presentation in full screen mode?
This is the fullest I can go because yeah.
Okay, sorry.
Is it not fine?
Yeah, if it's not possible, you can continue.
Okay, fine. Sorry, but this is the maximum I can make it full screen. Okay, so the heavy quark transport coefficients are sensitive to the medium evolution, and they tells us about the medium properties. Understanding those transport coefficients are important because they give us indirect understanding about the medium properties. So the two transport coefficients that I talk about is the drag coefficient, which is a resistance in the motion of the heavy quark due to light quarks and anti-quarks and gluons in the medium. And then another is the diffusion coefficient, which has transverse and longitudinal components. I'm going to talk on momentum space only. Okay, so in the formalism, we have start with the Boltzmann equation, and with the approximation of soft scattering, we reduce it to Fokker-Planck equation. This Fokker-Planck equation has the two terms. Really, the leading order term corresponds to the drag coefficient of the leading order corresponds to the drag, which is the thermal average of the momentum transfer of a heavy quark in the initial and the final state. P prime is in the final state of the heavy quark, and in the diffusion is another transport coefficient which is at higher order, which is the square of the momentum transfer. So this diffusion is a tensor which can decompose into the transverse component as well as the longitudinal component. So this work has been done way back, but then what progress have been made is, so this thermal average could be written in a more generic form in terms of the kinematic integrals, the interaction matrix element square, and then you have this is the transport coefficient, this thermal average we have done here. But a few years back, people also looked into the radiation of the heavy quark in terms of the final state. We have a soft gluon in the final state. So this is 2.3 process in an elastic, and this thermal average for radiation could be written in terms of the thermal average of collision and a probability of soft gluon emission. And one particular thing to note here is that we have this term called dead cone factor, which represents the suppression in the radiation of the heavy quark as it goes like inverse mass to the power 4. And then we have also the kinematic constraints from the phase space that the energy of the emitted soft gluon K prime couldn't be larger than the energy of the heavy quark itself. And also the time of formation of the soft gluons should be less than the interaction time scale. Then still now we have looked at the ideal case, but then we can also move away from the ideal case in two ways. First is introducing the thermal medium interaction. This is done using the effective quasi-particle model, and it is parametrization is based on lattice QCD data. Here, the particles have been introduced within the particle dispersion relation in medium interactions, and they're promoted to quasi-particles. So the effective fugacity parameters introduced into distribution function here, and the dispersion relations gets modified by the amount delta omega k, which represents collective excitations of those particles in the temperature derivative of logarithm here. And if you put we can go back to the ideal case just by inserting zk is equal to 1, and this effect of a change in the distribution function also propagates to the dBA mass, and effective strong coupling constant also gets modified, the strong coupling constant into effective coupling constant. The modification number 2, which has been done, is introducing viscous hydrodynamic corrections at leading order, which is shear and bulk viscous corrections to the distribution function by solving the relativistic Boltzmann equation under relaxation time approximation. So the dissipative hydrodynamics include in the energy momentum tensor by introduction of the shear stress tensors, as well as the bulk viscous pressure. So this dissipative effects corresponds to the resistance to the motion, and then this is sigma mu nu is the resistance to flow different layers of the fluid, and this resistance, isotropic resistance to the expansion of the Coulomb plasma. And the distribution function of this quasi-particles, since we carried that formalism of a quasi-particle through EQPM in point number 1, so we have this distribution function gets modified by amount delta Fk, which is the non-equilibrium part of the distribution function, and it's constrained to be very small in comparison to the equilibrium part. The leading order viscous corrections, finally what we got to is the bulk and the shear, which is given here, and we also put in the paper this part. The results, we did the analysis for 3 flavors, massless case, zero chemical potential, and for the charm curve of 1.3 GeV, we saw, so the plots in the upper panel, upper 3 plots are the momentum dependence, and the lower 3 plots are the temperature dependence of the transport coefficients. On the y-axis, we have 3 different transport coefficients, as I mentioned earlier. This is drag, diffusion, transverse, and longitudinal diffusion. And all the transport coefficients have been scaled to the values correspond to the zero viscosity case. So essentially, we're looking at the effect of viscosity on these transport coefficients, and approaching 1 means the effects get all, the effects vanishes at 1. So what we see is that at low momenta, for all transport coefficients, the effects are dominant. And these are even more prominent for the radiative part in comparison to the collision. As we vary the viscosity, shear viscosity over entropy density ratio, we saw this red and black ones are for the radiation, blue and greens are for the collision. The radiative transport coefficients are even more affected in comparison to the collision. Similarly, for the temperature dependence also, we saw the case, but one exception could be this longitudinal diffusion coefficient, which is increasing as we increase the shear viscosity or entropy density ratio, but the other 2 transport coefficients are decreasing. Another thing that we look at is the differential energy loss, which is the product of the heavy quark initial momenta times the drag coefficient. On the left, we see the ratio of the radiative energy loss over collision, and the momentum range. When we look into it, we saw that at low momenta, where the collision part dominates, and at the high momenta, the radiative part dominates. And this effect of viscosity is also more prominent at the low momenta. And looking further into the effect of what happens to the bottom quark, if we place the mass of charm to the bottom quark, then we see a suppression, overall suppression in the energy loss due to radiative processes for the bottom quark. And this can be attributed to the fact that I said the dead cone factor, which goes as inverse mass to the power 4, which suppresses this radiative emission of the soft gluon. And another thing to note that
Adiba, this is Suma Shankar. Sorry, what is the mass of bottom quark you used? And
4.5 GeV.
I mean, what is the difference? I mean, only you brought in bottom quark only in this calculation. What about all your previous calculations? There you didn't consider bottom quark at all?
Previous calculations, you mean this one is only for charm quark?
Then what is the reason for introducing bottom quark in the next set of calculations?
We just want to look at the mass effect, how it is modified, heavy quark. So we looked into the charm quark, but it is also a possibility to look into the bottom quark. So we wanted to look at how the viscous corrections to the transport coefficients.
When the curve labeled charm had only charm quark as the heavy quark produced, and the curve labeled bottom had only bottom quark as the heavy quark produced. Is that correct?
Yes, that's the assumption that can be.
Okay, fine. Go on.
Yes. Okay. So, and these are independently. When we have a bottom quark, we don't consider the charm quark also produced in the light quarks or something. Okay. So this is the radiative effects, radiative process, differential energy loss, and we see a suppression in the bottom quark radiation, as well as the effect of varying the shear viscosity entropy density ratio seems to be milder for bottom quark in comparison to charm. And finally, one bulk viscous corrections that we studied. This is only for one transport coefficient, that is the drag coefficient. And we saw that for momentum dependence on the left, over the entire range, it doesn't show any constant over the entire momentum range, the variation in the bulk viscosity for collision as well as radiation. But on the right, we have the temperature dependence, which shows a prominent dependence of temperature of the transport coefficient on the bulk viscosity at low temperatures, and which approaches the conformal limit, so that all the bulk effects vanishes at high temperatures. Another thing to note is that the collision and the radiation effects are identical in this bulk case. It's something that we have to explore further. Okay, so the conclusion is we studied heavy quark transport coefficients with the collision and radiative processes in viscous QCD medium. We deviate from the ideal case in two ways. First, introduce thermal medium interaction, and second is we introduce the leading order corrections through bulk and shear viscosity. Shear effect seems to be more prominent for slow moving charm quark and low temperatures. And the shear viscosity effects are also more for radiative process in comparison to the collision. Bulk viscous corrections are prominent near the transition temperatures and also identical for both the processes. In future, we are looking forward to introduce the next to leading order corrections, viscous corrections through distribution function, and see the variation of the transport coefficients for heavy quark. Thank you.
Thank you, Adipa.
This is Suma Shankar. I have two questions.
Sure.
One is, are you considering including both charm and bottom together? Because the effect of bottom quark seems to be not about half or so of the effect of charm quark. So
it's less than half.
Yeah, okay, less than half, but not negligible. So it seems that you should consider both together. And that is something to think about. And another thing, you have put the strange quark mass and the chemical potential to be 0. And in a lot of cases, that's not a very good assumption. So have you considered putting a non-zero mass for strange quark and the corresponding chemical potential?
We are currently looking into the analysis where we have massive light quarks or strange quarks into the medium, but this results, this is
so you are looking into that problem.
Yes, yes.
Okay,
because
good.
What we are trying to do is that we are trying to remove this model dependence from here and just go back to the ideal case and see if the masses include the masses for the light quarks, especially the strange quark. This may be more
that will be more realistic.
Realistic to include it, and then see the effect of this massive particles interacting with the heavy quark.
Okay, okay, fine.
Okay. So I think any other questions anyone has? Amongst the students, you have anything to ask? Is there any questions on the YouTube link? Is anyone in the organizing student team is looking into it to ask? Okay, so I assume there are no questions.
Okay.
If you have any questions, you could have raised the hand here if you are in the Zoom meeting. If there are no further questions, let's thank Adiba again for this.
Thank you for your attention.
Let's get to the next speaker. Next speaker is Shushmita.
I am. Yes.
Yeah. Can you flash your first screen? Then that will help me to say a few words. She's also in the 4th year, right? You're also.
No, I am in 3rd year.
3rd year. Sushmita is working in the gravity group. Am I right?
Yes.
Shankar Narayan.
Yes, with Professor Shankar Narayan.
So can you tell us what you're going to? I do have your abstract, but I
yes.
Better to open your first screen.
Yes. Is it? Can I see my screen?
I can't see.
Yeah, we can see your screen, but your talk has not opened up yet.
Oh, okay. I'll try it again.
Yeah, okay. Now we can see the first slide of your talk.
Okay.
You're going to tell us more about this non-minimal coupling of electromagnetic fields from astrophysical observations. So let's listen to a talk. So now the time is 12:27, so you get 15 minutes. So just stick to the time and present your work.
Okay.
Shashmita Jana. Yeah.
Yes. Welcome everyone. So today I'll be discussing about my recent work on constraints on the non-minimal coupling of electromagnetic fields from astrophysical observations. And this work I have done in collaboration with my supervisor, Professor Shankar Narayan. So let's start with the motivations. So the primary motivation behind this work is to look for modifications to theory of general relativity. And still now, all the postulates of GR has been tested in the distance scale, and that distance scale lies between 10 to the power minus 3 centimeter to 1 astronomical unit. And we don't know whether this is, outside this length scale, whether GR is the accurate theory of gravity or not. And that is why people are looking for, people are proposing the different alternative theories of gravity, and they are willing to test these models also along with the GR in this length scale, in very small length scale and in very large distance scales also. So one simpler way to look into modified gravity is by considering the gravitational potential. Here in equation 1, you can see that there is a Yukawa type potential. Yukawa type potential has been added along with the Newtonian gravity. And here this alpha is the relative strength of the Yukawa potential compared to the Newtonian gravity, and this lambda is the length scale where the Yukawa potential becomes relevant. So there are, according to the results, according to different models, there are already some constraints on these parameters. But my work is to see whether these constraints are correct or not in strong gravity regime. And to do so, I have considered interaction between gravitational field and electromagnetic field. And by looking into the effect of gravity on this electromagnetic field, I'll be able to put some constraint on the coupling parameter that will be present in the theory. So I am choosing here electromagnetic field because electromagnetic wave is a very important part in astrophysical observations. And one way to look into this, that in curved spacetime, whenever we, in curved spacetime, when we consider any theory of any field or any matter, we consider the interaction of the field with gravity. And a simpler way to do that is by changing the space-time volume element by multiplying it with square root of minus g, where g is the determinant of the metric, and we change the partial derivative into covariant derivative also. And this type of theories, in this type of theories, the interaction of the field with the gravity is called minimal coupling. But there is one more way to, there is one more robust way to consider the interaction when the gravity becomes very, very, very strong, such as near the compact objects such as black holes or neutron star. Then in that case, we need something more than minimal coupling, and we introduce non-minimal coupling. So here equation 4 is one of the simplest model describing the non-minimal coupling of electromagnetic fields. Here you can see this first term is the Einstein-Maxwell's action, and this term is the non-minimal coupling part, where the Maxwell's field tensor interacts with the Riemann curvature tensor, and this lambda is the coupling parameter of this model. So the basic difference between minimal and non-minimal coupling is that in Kerr space-time, everywhere at a point, we always can construct a local inertial frame. And when we are considering minimal coupling, we can get rid of effect of gravity in those local inertial frames. But when we are considering non-minimal coupling, the effect of gravity does not vanish in the inertial frame. So that is the physical difference between minimal and non-minimal coupling. So however, from this action, we have found this equation of motion. As you can see that this equation of motion is very different than Maxwell's field equation. So in Maxwell's field equation, the right hand side is is zero when there is no source, no charge source. And these terms are direction dependent as well as the space-time dependent also. And the first term can be considered as the kinetic term, and the second term can be interpreted as a mass term. So from this equation of motion, what we can do these followings. So what we have done, we have found a modified dispersion relation. I should mention that in Maxwell's theory, the dispersion relation is p mu equal to 0. And what we have found here, we have found a different modified relation. And with that modified relation, we have calculated the deflection angle of photon that is passing nearby the compact object. So you can see in this figure that there is a black hole and there are a bunch of lights those are passing nearby the black hole and they are getting deflected. So instead of getting one single deflection, we are getting different deflection angles depending on the mode of polarization, and that we have found here also, analytically. And from this polarization dependent deflection angle, we have been able to get a constraint on the coupling constant lambda. So to proceed further, we need to choose a particular black hole metric, and for that we have considered two separate cases. The first one is Sultana-Dyer black hole, that is a time independent black hole, and another one is the the Schwarzschild black hole is the time independent black hole, and Sultana-Dyer black hole is a time dependent black hole, and both these black holes are spherically symmetric. So what we have found that the constraint that I'll show you later, that this constraint on lambda strongly depends on the type of the black hole, whether it is time dependent or time independent in nature. The value, the constraint on lambda, that will change drastically. So there are many similarities between these two type of black holes, Schwarzschild and Sultana-Dyer. Both of them have null geodesy, the same null geodesics and the same horizon radius and innermost stable circular orbit and all. And Sultana-Dyer metric can be, Sultana-Dyer black hole can be thought of as a Schwarzschild black hole that is embedded in the matter-dominated expanding universe. So here in equation 6, I have written down the length element in Sultana-Dyer metric, and here this eta is the conformal time. So from this, what we have found, considering two separate cases, two separate black holes, I have obtained the modified dispersion relation in a locally constructed inertial frame, and then I recalculated those modified dispersion relations in the original non-local non-inertial frames, and from those relations I have found the polarization dependent deflection angles. So as I don't have enough time to discuss these two steps, I will discuss only the results that I have found. So here here I have written the difference between the deflection angles for plus and minus polarization for both the cases. Equation 7 is for Schwarzschild and equation 8 is for Sultana-Dyer black hole. So here this parameter B is important. It can be thought of as not exactly the same, but similar to the inverse of impact parameter, and both these quantities, they depend on this B parameter very differently. So from these relations, we have found the constraint on lambda, and considering a solar mass black hole, for Schwarzschild case, we have found the constraint to be of order 10 to the power 20 centimeters square, but for Sultana-Dyer black hole, this value becomes 10 to the power 10 centimeters square. So as I mentioned earlier also, that the constraint on lambda will strongly depend on the time dependent or time independentness of the black hole. So here I have plotted the results. So this is the difference between the deflection angles for plus and minus polarization. So I have plotted these two separate cases considering two different values of B. And I mention again that B can be thought of as similar to the inverse of impact parameter. So for this first case, when B is of order 10 to the power minus 24, then this difference between the deflection angles for Sultana-Dyer black hole is lesser than the difference between the deflection angles for Schwarzschild black hole. But when B is smaller, B is of order 10 to the power minus 27, that means that when the impact parameter is larger, then the effect of Sultana-Dyer black hole on the photon becomes higher than the effect of the Schwarzschild black hole. So here I should emphasize that the effect of the black holes, effect of a time independent or time dependent black hole on the passing by photon strongly depends on the impact parameter of the photon also. And in the next slide, I have done the same plot considering a different black hole of mass 10 to the power minus 5 into solar mass. The previous one was for a solar mass black hole. And as a conclusion, I will just mention that what I have done so far. So we have found the constraint, that is the key result of this work. The constraint on lambda strongly depends on the type of black hole, the time independent or time independentness of the black hole. And we have seen that the effect of the black hole on the photon, that also strongly depends on the impact parameter of the photon also. So throughout this work, what I have assumed that the black hole to be spherically symmetric and non-rotating, and this work can be further extended considering a rotating time-dependent black hole. Yeah, thank you.
Thank you, Srishmita Jana, for this nice talk. Can you raise hands, the audience who have any questions? Anybody has any questions? I hope I don't see anybody with raised hands. Okay, I have a small question to ask you.
Yes.
So this non-minimal, this is the only possibility of adding a term, or is there many more possibilities you could add?
No, there are many possibilities. So this is a very simple model, and this model was proposed in 1971 by Prasanna. So along with this term, this is only Riemann curvature tensor, but I can add Ricci tensor also and Ricci scalar, and derivative of possibly not derivative, only the Ricci tensor and Ricci scalar also.
Okay.
But those models become very complicated, and when the black hole is time dependent, then the metric becomes non-diagonal also. So in that way, the mathematics become more complicated. That's why we have just fixed the very simple model of this.
So whatever you've done for Schwarzschild and this one Sultana-Dyer, if you also have a charged black hole, is all this all your procedures will go through and you get more or less the same answers, or?
Charged black hole, I mean, I have checked the result for a non-charged curved black hole, and they are giving same results as a Schwarzschild black hole.
Okay. So the charge does not really play any role.
Charge, I mean, charge I did not consider actually. A non-charged black hole I have taken, curved black hole with zero charge, and they are giving same result as a Schwarzschild black hole.
The rotating curved black hole.
Yes, rotating black hole, curved
The
black hole.
spherical symmetry is lost. Even then, you get the same.
Yes, and but it is time independent, static rotate. Yes.
Okay. If there are no further questions, we can thank Sushmita. Anybody has any questions? Okay, thank you, Sushmita, for this excellent talk. And I think we break for lunch now, and then we resume in the afternoon. Can the student organizer take over?
Yes, sorry. Let's thank to speaker, chair, and evaluator for this session. So this is the end of second session, and we will resume with experimental high energy at 2 p.m. So there will be break, and so see you all at 2 p.m. Thank you.
Okay. Thank you all for joining.
Thank you.
And let's meet at 2 p.m.
Yeah.
Welcome again. I would like to request. Hello. Hello. Am I audible? Hello. Okay. Hello all, welcome again. I would like to request Professor Sadhna Das to chair this session. Over to you, ma'am. Thank you.
Thank you. A very good afternoon to all of you, and I welcome you all to the third session of SYMPHY 2021. So this session will be devoted to experimental aspects of high energy physics. And it's a pleasure that we have Dr. Prabhat Pujari from IIT Madras as the guest speaker. So he did his PhD from our department, from Department of Physics, IIT Bombay, and went on to pursue postdoc at Wayne State University. Currently is a faculty at IIT Madras and is working in the CMS experiment at Large Hadron Collider. So he'll be talking on understanding properties of nucleonic fluid. So let us welcome Prabhat Pujari. Prabhat, now it's over to you. So you have, let's say, 45 minutes, including the question and answers. So maybe 5 minutes or 10 minutes before, I'll give you a warning if you're really exceeding the time, okay?
Okay, thank you, Professor Das. So hello and good afternoon to everyone. Can you hear me? Is it stable?
Yes, I can hear you very well.
Okay, thank you. No, it looks like I was getting kicked out a couple of times. So hope it is okay now. Okay, so and thanks to the SYMPHY organizers also for inviting me as a speaker to this symposium. I believe the SYMPHY started from our batch around 2011 or 12. That was the first SYMPHY we had. So it's good to interact with you all through this symposium. Okay, so let's start. So as you can see in my title, I'm going to talk about a phase of matter, a liquid phase of matter basically. So let's ask whether it is going to be like, why it is not changing? Just a minute. Yeah. So whether it is going to be like water, and the answer is no, it's not going to be like water. Then what about honey? Again, I am not going to talk about honey also here. Now, what about beer? It's a good liquid, correct? And we all like it, maybe most of us. But sorry, I am not going to talk this here as well. So what I am going to talk about is something very obscure, something you may not have heard of. So I'm going to talk about a plasma. But that plasma is not the ordinary plasma that you are aware of. So I'm going to talk about quark-gluon plasma. Okay, so that's going to be my topic for today's discussion in this session. Okay, so let's see on a temperature scale, where do we lie today? So as you all know, our three phases of matter that basically we live in, solid, liquid, and gas, we almost lie in the temperature around 1 to 10 to the power 3 Kelvin. So 1 Kelvin is around minus 272 degrees centigrade. For example, if you take the room temperature in Mumbai right now, it's maybe, if I am not wrong, around 300 Kelvin, correct? So we all lie within this region here. Now you see here towards little bit higher side if you go, so you have the sun, which is very hot, extremely hot. And then you have supernova at little bit higher temperature side, explosion of stars. And what about in the low region? In the low region, we have Bose-Einstein condensate, where the matter stops behaving as independent particles and basically collapse into a single quantum state, as we know. And it can be described by a single uniform wave function as well. And similarly, we can have also a fermionic condensate, which is very much similar to BEC, but composed of fermions, ultra cold Fermi gas. So these things are lying in the extremely low temperature, absolute zero or even below extremely low temperature. But then the question is, what are the properties of matter at extremely high temperature? When I'm saying extremely high temperature, I am talking about temperature which is greater than 10 to the power 12 Kelvin. So you can compare the room temperature in Mumbai right now is 300 Kelvin, and we are talking about a temperature scale of about 10 to the power 12 Kelvin. So what is the form of matter that lies at this extremely high temperature? And that is why this new phase of extremely hot and dense matter lies, which is called as the quark-gluon plasma. The temperature is around, if you take an analogy with the sun's core temperature, it is 10 to the power 6 times higher than the temperature of the sun at its core. So it's really huge in that sense. But now you might want to also know, why do we need to study this property of QGP today, correct? This is all our history, correct? But actually, wherever we are today, we can unravel history by going all the way back to the beginning of the universe. And by doing that through science, we can understand the very origin of ourselves. Not just ourselves, we can understand all the matter that we see around us today, correct? And also the sun, the solar system, the entire universe. So that is why we need to study that. That is why we need to go around and check what was there, what was the form of matter at the very beginning of the universe, when the Big Bang, the creation of the universe and the subsequent evolution, the theory is called Big Bang. So at the very few microseconds after the Big Bang, what was the phase of matter that we had? And from there, wherever we are today, we have the evolution. Okay, this is the evolution phase. Now the question is here is, how are we going to create this matter in our lab, correct? Because the problem here is, these quarks and gluons are the fundamental degrees of freedom, and they are always confined inside hadrons. They are always confined inside particles. They are not freely available. Nature does not allow these particles to be freely available. Okay, and this is something called confinement. And as you can see, because of this physics of confinement, what is happening is, if you write down the potential, this confinement potential is a function of the separation distance between quarks. So what we are trying to do here is, for example, these are the, like, can you see my cursor, by the way? Or it's not visible?
Yes, sir, it's visible.
Okay, thank you. So for example, you have protons, or you have a meson, like pion or something like that, and you want to try to pull one quark out of this proton. So when you do that, basically you are supplying some force or energy. Okay, in terms of potential, you can see on the right side the graph. So what happens is, at low temperature, this is a linearly increasing potential. So as you keep increasing the separation distance, the potential will also increase. So basically, in the other way, you would like to say that it's not possible for you to separate this quark. But now when you heat it, not just heat, you have to supply very high heat, sufficient heat, okay? Then what will happen is, actually this potential will become constant at very high temperature. In the case of very high temperature, this potential becomes constant. And now, in fact, what you can do is, or what will happen is, these confined quarks and gluons inside their mother hadrons, they may go for a phase transition. So the individual identity of these particles, the hadrons, will be lost. And the quarks and gluons, as you can see on the bottom cartoon here, those who are lying inside the protons and pions and all these hadrons, now they will freely roam around this nuclear volume here, the entire volume, not just confined inside the nucleon. Nucleon means like the proton or neutron. They can go around. This quark will go to here, this quark will go here, like that. So freely roaming inside this circular region or inside this volume. This is like a nuclear volume. And this phase of matter, where the quarks and gluons are the degrees of freedom, not the mother hadrons, this is what is referred to as quark-gluon plasma. And as I told, what we did As I mentioned here in the last slide, we supply heat. Now this heat, the amount of heat that we supply to make these confined quarks and gluons deconfine is not so trivial to generate. As you can see, this transition temperature where this transition is taking place from deconfinement to confinement to deconfinement, it requires around 150 MeV, mega electron volt, which if you want to convert, it is like 2 into 10 to the power 12 Kelvin. And as you know, there is no heater, there is no, stove or no gas, which you can use to heat this amount of, or generate this amount of heat. So what do we do for that then? What is the, what we have in order to achieve this non-trivial temperature? So we take the help of accelerator and collider. So what do? We collide heavy ions like lead on lead, gold and gold, copper and copper, xenon and xenon, all sorts of heavy ion we collide. And not just collide them like in an ordinary way. We first use this accelerator to accelerate these ions to the speed which is very close to the speed of light. And then we let them collide. So as you can see here, we use these two facilities. One is called relativistic heavy ion collider. This is situated in Brookhaven National Laboratory, New York. And the right side, you see it is the Large Hadron Collider. This is at the SOR, Geneva. So this was the two, so far, the biggest accelerator facility that we have for this kind of general purpose physics. Okay. Now what we do here is we collide, as I mentioned, different type of particle species, starting from smaller one like proton-proton, then we have deuteron-gold or proton-lead, then we have copper-copper, gold-gold, or lead-lead, xenon-xenon. And also, as you can see, the square root of center of mass energy, which is very much directly proportional to the velocity of this beam of particles before collision, is very high. It's starting from low to high, in fact. We can go for very low energy to very high energy, starting from 0.007 TeV to 8 TeV, or even for proton-proton case, 14 TeV, 13 TeV, 14 TeV, tera electron, huge energy from RIG to LHC. So all sorts of different kind of energies, different kind of collision species are available to look at the physics that we are willing to study, correct? And these are our experiment. I am an experimentalist, so without these few slides, my presentation or discussion will be incomplete. So I need to take you at least spend a couple of minutes to discuss all these things. So these are our experiments. With the help of these detectors, we collect all the debris of these collisions that I explained in the last slide. So the first three experiments here, you see, they belong to the LHC, Large Hadron Collider, and the bottom three are from the RIG, the Relativistic Heavy Ion Collider. Okay, so these are the two. And one thing I would like to mention, India is a part of almost all these experiments here, except I think ATLAS. We are still not a part of ATLAS, but apart from that, we are somehow associated with all these four experiments that is mentioned here. Okay. But I am particularly right now working on CMS collaboration. It's called Compact Muon Solenoid. So this detector is a massive device, as you can see, 22 meters long and 15 meters in diameter, and around, I would say, like 15,000 tons of weight, heavy. So it is one of the general purpose detectors at the LHC. And you must be now thinking that it takes equipment like this big to detect particles which are so small that you cannot even see in a microscope, correct? So usually, as you know, it requires sophisticated machine to measure something which you cannot see, and that is what exactly we do. Okay, so as you can see, it is not just one piece of detector, by the way, not just one piece of instrument. So there are various sub-detectors, as you can see, and based on these different types of physics, different types of particles, in fact, we measure, these sub-detectors are required. You cannot just put one detector and try to catch all these debris, all the particles coming out of the collision. You require different types of detectors. For example, particles are there which will take part only in electromagnetic interaction. Particles are there which will take only in weak interaction. So depending on the physics process of the type of particles you need, and also there are charged particles, there are neutral particles. They cannot behave similarly in a magnetic field. As you know, neutral particles cannot have any influence on a magnetic field. So that's why you need to have all these pieces of detectors, combine them together if you want to catch all these particles without losing much more information, which is required for your physics later on. Correct? So with that thing, basically, if I want to divide, what do we exactly do without going into the details of the technicalities of the technologies? I would like to divide them in 4 parts. So we have trigger detectors, basically what they do. When do we have a collision? The trigger detectors tell us when do we have a collision. Then we have tracking detectors. What does this tracking detector do? They will tell us where did this particle go. And then we have particle identification detectors. They will tell you exactly what type of particle it is, whether it is a pion, whether it is a proton, whether it is a electron, the type of particle. That is what the identification detector, those detectors which belong to these identification detectors, they will do this job. And then we have something called calorimeter. As you know from the word calorie, they measure how much energy does the particle have. So if you want to divide all the pieces of detectors into 4 parts, they will belong to either of these 4 categories. So this is what we exactly do. Since we don't have much time, this is what basically to make the long story short. Okay. So yeah, as I mentioned earlier also, so you have different types of particles. You have charged particles, and also you have neutral particles. And then you have different types of also neutral particles. You have particles which will take part in electromagnetic interaction, particles which will take part in weak interaction. And there is muon, for example. Muon, it's the heavy partner of electron, and they take part in weak interaction. The decay process is very slow. So they will not, any of these detectors that you see here, they cannot stop this muon to travel long path. So what we do is we have put a muon chamber, as you can see towards the last end of this detector systems. These red color detectors here, they are basically muon chambers and very hugely packed iron. So because in order to stop this muon, you need that. Okay, it's not like the electron. Electron may lose its energy and they deposit the energy in the calorimeter, or also in tracking you will have a track of this particle. So this is, I mean, the various things that one want to study in this area, in the experimental high energy physics case. Okay, so then in the year 2005, the remarkable new state of matter that I was trying to mention, quark-gluon plasma, got discovered at relativistic heavy ion collision. And I want to read some portion of this press release. This is a press release, as you can see from the Buchanan National Laboratory, what they are saying. They have created a new state of hot, dense matter out of the quarks and gluons that are the basic particles of atomic nuclei. But it is a state quite different and even more remarkable than had been predicted. Okay, and again, they are saying, the scientists say that instead of behaving like a gas of free quarks and gluons, as was expected earlier, the matter created in Rick's heavy ion collisions appear to be more like a liquid. And that is where I am going to focus in the entire talk today. So strongly coupled like a liquid instead of a gas. That is our new phase of matter called quark-gluon plasma is. Now, when I am saying a liquid, immediately I want to mention something, and which is very important, the evidence from collectivity. So please mind my words here, liquid and collectivity. This is going to be my focus in the entire talk now onwards. And that is why I want to emphasize on, okay? So before we start, we need to first discuss what do we mean by collectivity. Most of you know already what is a collectivity. You may be using this phrase every day. It's a group of objects interact with each other and move as a whole. That is in the general sense called collective phenomena, correct? Most of us must have also fascinated by the eye-catching display of this kind of pictures. So as you can see, the school of fish or bird hogs here. So they have either a common velocity or in a unique direction they are all traveling. So this kind of phenomena is called collective phenomena. In the context of our discussion here, I would like to explain this collective phenomena into something else also. So collectivity could be also defined as, for example, objects in the final state far from each other are correlated by a mechanism in the initial state. That is also you can call as collective phenomena. And also another thing, another way you can define collective behavior, it could be many bodies in the final state, and they are product of one single entity in the initial state. That can be also a collective phenomena. Like for example, 5 brothers and sisters staying in Bombay, Calcutta, Chennai, or in US, but they all belong to one family, and that family makes them collective, makes them correlated basically. The next term I am going to use is correlation. Okay, so this is how the collective behavior develops. Something commonality between all these objects that bring them together, that bring them collective in their nature. That type of phenomena we refer to as collective phenomena. And this is going to be very important in our discussion now onwards. So the collective phenomena have been a central theme actually in the research or in the search for strongly correlated and interacting many-body systems. And I would say in nearly all fields of physics, from the astrophysical scale like neutron star to the most fundamental quark-gluon plasma that we are discussing here. And they form the complex frontier in physics, which address the emergence or the emergent phenomena. This is what is very important. However, the key questions here, what is the underlying mechanism to drive the collective behavior? Can it be understood from fundamental forces, if at all? That's the 2 questions we need to address in our contest. Okay. Now, how do we measure this collectivity? That is the very important point, because so far what we discussed is a very general way of discussing or describing collectivity. Now, how do we do that? How do we measure that in our experimental data, using our experimental data? So I'm going to talk about something which is very, very important, and basically one of the, I would rather say, smoking gun signature to discover this, to help in discovering this quark-gluon plasma. And this is what is called as flow. So before that, I just want to tell you what a flow means, like flow of water. If I take a glass of water and pour in a asymmetric flow, what do you expect? The water will start flowing in a direction where it will find a stiffest, pressure gradient or something like that, slope. Exactly, you take this analogy and let's try to understand the flow that I am trying to describe here. So you see here this cartoon on the left side. So these are basically 2 nuclei or 2 ions, whatever. Let's take lead collision or gold ion. So, but the collision is not completely head-on collision. It's a little bit glancing collision. There is some kind of overlapping, but they are not totally overlapping with each other. As you can see, after the collision, this guy will go towards the off or towards this side. The other guy will go towards the other side. And the reason, what the overlap reason, what we refer as, look like an almond shape. This is the part of the geometry that take part in the collision, not the other part. So this part alone. And then we have something called an imaginary or something called a mathematical plane. That is what is referred to here as reaction plane. Now, what do we do to measure this flow is, we measure all the azimuthal angle of the particle produced in this collision. And then not just measure the azimuthal angle, we measure the azimuthal angle with respect to this plane that we have defined here called reaction plane. And we want to study the distribution of the azimuthal angle of the produced particles in this reaction plane. Now you see there is, because of this asymmetry in the initial spatial anisotropy of this, because it's not a spherical shape, the collision region, correct? There is a azimuthal anisotropy. The particles produced here are distributed asymmetrically, not symmetrically. And because of there is a eccentricity here, as you can see, the x-axis and the y-axis are not equal. And on the top of that, the produced particles, they will not just stand still. They will interact among each other quite frequently and adequately. So because of this frequent interaction, the adequate interaction among these particles, this initial anisotropy, the initial spatial or geometrical anisotropy via this interaction of among the particles, that will transport to a final state momentum anisotropy of the produced particles. So what we measure is the momentum anisotropy of the produced particles, which is related to the geometry of the initial structure. Remember, the initial overlap region. It's not random. Now, if you look at the right side, so what do you expect? For example, the momentum anisotropy, if all the particles produced from these collisions are going in uniform way, all the directions they equally distributed, then what do you expect? It is more like a random, like gas-like behavior. So what do you measure it? You see the x-axis here is phi minus psi r, which I was telling. All the angles, azimuthal angle of the produced particles are now referred with respect to this reaction plane. That is what phi minus psi r. And on the y-axis, you have d and d phi. D and d phi is the number of particles produced per unit azimuthal angle. Now, if you recall what I just said, if you expect all the particles produced after these collisions are uniformly distributed in the momentum space, then you should expect like a uniform flat distribution of d and d phi. But what we rather see is not a flat distribution. It's more like a fluid-like distribution, follows a Fourier decomposition pattern, cos and sine pattern, as you see here, d and d phi, that I am going to discuss right now. Okay, so this is the main story of this discussion. So I hope all of you understood what is going on here. Now, how do we measure that? So without going into the very details of the measurement things, I would like to mention that a couple of techniques are there. But I picked off one technique which is very famous and very popular. This is called two-particle correlation. Okay, now you see the word correlation I am going to use now onwards. So this correlation, what I did, instead of d and d phi, I started from two particles. So this is why you see here d and pair d phi, not just single d and d phi. So d and pair d phi, I expand that. So this is basically n pair by 2 pi, some normalization factor. And then the rest of the thing, as I was telling, I decompose it into a Fourier decomposition, like this part. 1 plus 2, where n goes from 0 to infinity, in fact. Then you have some component called v, cos, and phi. And now also another thing you notice here, I make the reaction plane absolute. What do I mean by absolute? So you see here, I did not mention reaction plane. Rather, I mentioned phi of A, particle A, and phi of particle B, azimuthal angle of particle A and particle B. In fact, what I did, although I have omitted the reaction plane existence is still very much there. Please remember the flow I discussed here. Flow is a multi-particle correlation with respect to the reaction plane. That's the definition of flow. Okay. So what I did is, it is actually like B is correlated with A and C is correlated with A. That means B and C are also correlated. So you make the A absolute. It's exactly I am doing here, similar thing. F of phi of A minus phi of B. This is what is called two-particle correlation. Now, how I am going to calculate that? And by the way, this Vn, red Vn, this is what is going to be the flow coefficient. So the Fourier harmonics will give you flow coefficients. Okay. I don't want to go into detail, but I will be happy to take various questions on this. This is my favorite topic, but right now let's move on. So yeah, so let's go. So what do I mean by two-particle correlation method? So you see here the bottom right side, I have a correlation plot. So what is this correlation plot? So I have these two coordinates. By the way, this is coordinate eta and phi. One is longitudinal coordinate, one is transverse coordinate of the particle. You take it like this way, very easy here, without going into the detail of the definition of eta, phi, etc. Okay, so you see in this cartoon here, this is our detector, this is the longitudinal, this is the phi is the azimuthal angle. So I make, since I have now two particles, I have to go for relative, I call it pseudo-rapidity and relative azimuthal angle, delta phi, delta eta. So I plot this pair of particles or their correlation as a function of this delta eta and delta phi. Now, what I want you to focus here is, forget all these things in the right bottom plot. Just focus yourself on the delta phi axis. Now, what is amazing here is you see a cos modulation as we were discussing earlier here. You see exactly a shape similar to that here, a cos modulation. Just focus on this part. Forget about all this peak and everything. Okay. So this is what is that cos modulation we were talking about some time back. Okay. Let's focus on that, man. So if you try to take a projection of this delta phi axis, it will look like exactly, it will give you something like that. Now, what is this dot, the circle, black circles here? This is the data From this projection, I took, this is the points. And then you see this red solid line. This is the SOM. Now, what is this SOM? SOM is basically, look at this SOM here, this formula. If you see my cursor, this is the formula. So the SOM is the contribution from the different flow harmonics like V1, V2, V3, V4, V5, etc. I stop here at up to V5. As you can see, up to V5 also, the fitting is perfectly fine. It explains all the data points. Very nice. So what does that mean? That means that this cos shape, this cos modulation that you see in this two-particle correlation is actually an artifact. It is actually coming from the various order flow coefficient. So if you take into account this flow coefficients and sum them together, you will explain this two-particle correlation feature. Okay, and that's what we need to focus on. This is the Fourier coefficient, as I was trying to tell you. These are the coefficients: V1 delta, V2 delta, V3 delta, V4 delta, etc. Keep going. But we stop here because we already see that the fitting is perfectly fine up to 5th order or 6th order. So we don't need to, go for any higher stop. So later it was realized that the initial overlap region that I talked about here, this region, is not that simple. It is not just always this elliptic nature or this almond nature. Rather, it's a much complicated lumpy state. Lumpy state means the initial, this geometry will keep fluctuating very frequently. That is what I mean by lumpy initial condition or lumpy geometry. Okay, like you take some lumpy material and make it whatever shape you want to give. It is exactly like that. So it's a very complicated structure rather than the simple structure we were thinking, just like an ellipse. So it can give you a triangular structure, it can give you a quadrupole-like structure, or it can give you a hexapole, octapole, many other. And these are the poles basically that we were talking about in that B1 delta, B2 delta, B3 delta, like that. Okay, so you can see here this elliptic geometry is cos 2 phi, then cos 3 delta phi, cos 4 delta phi, keep going. Now, what is the bottom line here is the initial geometry fluctuates. That's what I want you to remember. The initial geometry is a lumpy initial geometry which fluctuates. It's not just the almond shape. And this fluctuation, which is geometry driven purely, gives rise to this higher order flow coefficients, V3, V4, V5, etc. So if you take this Fourier, the data points that I am showing here on the right side, and if you again feed the Fourier decomposition, you will get these various order flow coefficients very nice. Okay, so what is important is the geometry dependent fluctuation and final state interaction. Okay, so these two things we need to keep on mind while we are discussing this topic. Now, this is the result. I want to show you what is the result we got. So Vn. So on the y-axis, you see this is Vn. Now Vn is, it can be 2, it can be 3, it can be 4, it can be 5 as well. And this is on the x-axis, there is something called centrality. Now, I don't want you to make more complex. I just want to tell you what centrality means directly. Centrality means whether it is a head-on collision or whether it is a glancing collision. Like if it is 100% head-on collision, okay, two cars come and they hit head-on. So it is called central, most central. Now, if two cars come and just their mirror is touching and they go by as usual, this you can call a very glancing collision like this peripheral. So the ordering is reverse here. So you start from 0. 0 is very central collision. And you go to 80% or 90% collision, you refer to as most peripheral collision. Now, what I want you to focus in this plot is, this is experimental plot, by the way, not any theoretical calculation. So the response of the geometry that we want to see, as I explained earlier, these Vn coefficients are directly related to the eccentricity, which tells you about the initial geometry. So now, if you have a very spherical geometry, you should expect because again, remember, in order to have flow, you need two things. Two ingredients is required. Like whenever you want to go for preparing a curry, you need ingredients. Exactly, in order to have flow, you need two ingredients. What are these two ingredients? One is initial spatial anisotropy. That means if the collision is 100% central, you will not get an asymmetric spatial distribution of the particles. Then you will not have flow. But the other requirement is, if you only have particles which are asymmetrically distributed, that's not enough. these particles should also interact. They should also talk to each other. There will be sufficient interaction among these particles, which will give pressure gradient. And the pressure gradient is basically the bursting, the flow. Okay. So you require the spatial anisotropy or the geometry, and the sufficient interaction among the particles. If any of these two quantity will miss, you will have no flow. Okay, remember that. So what you see is, that's why this distribution of the curve is like here as you go from peripheral to central. Okay, the geometry matters basically. And the system size, less interaction, develop less flow. And the geometry fluctuation that I talked about earlier is inversely proportional to the number of participants. Now, what is number of participants? Just I forgot to mention that. The number of participants is these guys, those who are so you see, this is a lead nucleus, let's say lead. Lead is 82 number of protons and something neutron, correct, from both sides. Now, all the 82 protons and all the neutrons are not taking part in the collision. When I am saying this collision, glancing collision, only few portion here and few of the protons and neutrons here, they are taking part in the collision. They are called the N part, number of participant nuclei. The others are called spectator nuclei. They are just a spectator. They will not take part in the collision. Okay. Now, what do we discover? By doing this measurement of flow, what did we learn? What is the message that we want to convey to the society? What is the big deal? And that's the big deal I am going to discuss here. So as I told you earlier, in this plot, I am showing the experimental data on the y-axis. This is V2. And on the x-axis, this is the transverse momentum of the produced particle. Okay. Now, this open circles here are the experimental data from RIC 200 GeV gold collision. Now, what you see here is this figure here is the elliptic flow, by the way, this B2. Okay. So a viscous hydrodynamic model is fed here. Now, why we feed a viscous hydrodynamic model? Because I have already told you that we have a liquid. Now I want to characterize that liquid. Just saying liquid does not make any sense. You have various forms of liquid, as I have in my introduction first slide, title slide. You have water, you have beer, you have honey, you have many other stuff. Okay. What type of liquid? What is the viscosity of this liquid? In order to check that, we use because we need to take the help of models, correct? We use a viscous hydrodynamical model. Now, what you see here is, when we take this viscous hydrodynamical model and we use this eta over S, by the way, what is eta over S? So actually in non-relativistic fluid dynamics, as you all know, the kinematic viscosity is used. This is called eta over the density. But in case of relativistic hydrodynamics, the rho is replaced by this entropy density S. Eta is the shear viscosity, by the way. So shear viscosity to the entropy density. That is what we use. This is a theoretical calculation from string ADS CFT theory. They have this development. Okay. So so in this, to fit this or to explain this data, we use eta over S, as you can see, 10 to the power minus 4, which is already very, very small. But we saw that it is actually underestimating our data. It is going way up. Then we use another value of eta over S in this viscous hydrodynamic model, 0.16. Now, when we use this 0.16, we saw that it is, this guy is overestimating, this guy is underestimating the data. Here it is lying going below. So we could not explain our experimental data. Then what we did? We use eta over S 0.08. Now, what is 0.08? This is the ADS CFT, the theory, lower limit of eta over S, which is 1 by 4 pi, which is 0.08. Now, if you notice carefully, this is matching with this is explaining our data very well. So it's a very low eta over S already, which is touching the lower limit of the theoretical hydrodynamic calculus. So what you can say, it reveals the nature of perfect fluid. Which type of perfect fluid? Of course, not Kingfisher beer, correct? As I tried to discuss in the earlier, it's definitely way different than the beer or any other liquid that we discussed, correct? It's a perfect liquid. And the perfectness comes from this shear viscosity. Then there are other stuff as well. Without again discussing much because of time constraint, I want to show you Now the particle differ. So what we did, we measured the same quantity called V2 using different types of particles. As you can see here, pion, proton, kaon, all these particles are. Now what
But sorry to interrupt, you have 5 minutes more, okay? Just so.
Oh, I have 5 minutes.
Yeah.
Okay, so then what should I? Okay, then I need to jump many things. I have not even come to my main stop.
So you can take 2 minutes more, but not more than that.
Okay, so what to do? Okay, just a minute. Okay, then let me jump a little bit, big jump. So, okay, so sorry for that. My flow is already broke. Yeah, so without mentioning many other details, what I want to tell here is, so the flow that I told you earlier, I discussed it's a two particle correlation, correct? But two particle correlation is not enough to tell that this is really a because I told you the flow is a multi-particle correlation with respect to the reaction plane. Now, if I tell you it is just from two particles, you may immediately start asking that there are many other two particle correlations. For example, which I did not show here, like for example, a flowing resonance, a rho meson in travel will decay to pi plus pi minus. This pi plus pi minus is strongly correlated, but this is also two particle correlation. But the important thing is this type of two particle correlation has nothing to do with the reaction plane. So you should immediately discard this type of correlation when you are looking at real multi-particle flow correlation, which you want to correlate with the hydrodynamics. Okay. So what we learn is it is not just two particle correlation. When we look for multi-particle correlation, we observe that this flow coefficient is explained by this kind of 4, 6, 8 particle correlation. So what I'm trying to say here is this is truly and truly multi-particle correlation. Okay. And this is what I just mentioned without again going into further detail. But now, since we don't have time, I want to pause here for a second and tell you with one of the iconic lines from Game of Thrones, where this lady, this leading actress is saying our favorite Jon Snow, you know nothing. What do I mean by this? Why I quote this? Actually, the puzzle is coming. And I want to discuss, but again, already I have got the warning. I need to skip many, many interesting things. And I want to jump directly if you stop. So what I want to tell you without going now to any of my slides is, what I discussed so far it looks everything was good. Everything was well explained by hydrodynamics. But life is not a bed of roses. And what I mean by that is, there are a lot of puzzles in our way. And unfortunately, I could not discuss all these puzzles. But the hydrodynamics so far, which we thought is coming for our rescue, looks like it is coming for as a spoiler. So what is the spoiler? The spoiler is coming. I need to omit many things. So the spoiler is from the Squid Game. So what is the spoiler? Just without going again in detail, let me tell you what is the spoiler. The hydrodynamics so far explain everything very nicely, failed to explain heavy particles like GEPSI and Upsilon. Now, as you see here, we got our data, which is here. This you see here the circle, black circles are GEPSI, and then the square here are another particle called the D meson. So you have these two particles, GEPSI and D meson. So now what you should expect is, and we all know that the charm quark is very heavy compared to the other light quarks, correct? If that is true, the charm quark, the flow of the charm quark should be less than the flow of the light quark UDF. And that implies the flow of GEPSI should be less than the flow of D0, because GEPSI is heavy mass like 3 GeV around, and D0 is almost 1.8 GeV or so. So what you should expect in the common sense of hydrodynamics, because in the case of hydrodynamics, if you have a heavy particle, it should flow less in the low PT. And that is what our expectation so far from hydrodynamics, which we did not see here. We saw that the JEPSI and D0, they are going hand in hand. But that's not the spoiler. The spoiler is when the people working on theory, hydrodynamics, viscous hydrodynamic model, they told that for heavy particle like CC bar, JEPSI, the flow should be almost close to zero, which you see this red curve here. But our data point lies way above. So what is the conclusion? The conclusion will be very straightforward. Hydrodynamics alone cannot explain the data. And that's what I mean by spoiler. But now the spoiler is actually in small system, which I skipped many of my interesting slides, sorry to say. The spoiler is in the small systems. And the small systems, a lot of interesting things to do, which I skip, and I want to go take you what is the next in LHC. So the future physics opportunities for the high density QCD at the LHC with heavy ion proton beams are round 3 and round 4. The precision era is coming. Proposal for higher, lighter ions like argon, oxygen, all these things are coming. So, and what else? The electron ion collider, study of reach. I did not explain quite properly what is reach because of that time constraint at EIC. At low Q square, photon is vector meson in fact. So energy equivalent to reach. So simpler initial state, one can study very details about the direct link to the initial state. That is the focus of this discussion. The high multiplicity events at REAC and LHC, these are poorly characterized in fact. So mainly because of inclusive or unknown processes to produce events in the tail of distribution, the hadronic collisions. Earlier to get more info, so it is very easier to get more information at the EIC, electron ion collider, like Q square of the event, and many other exclusive process as well. So this is the future that we are looking for. So to wrap up everything, most of the data collected at REAC and LHC seems to favor the final state model. That's the hydrodynamic. Proof of geometry driven flow. Some of the heavy flavor results still don't explain though, okay? LHC is going to offer new opportunity in round 3, round 4, and 5. New detector upgrades are going on, precision measurements are coming. And also in CMS, we are going to have a time scan detector, which will give us different PID. It is called MTD, meaning MIF timing detector. Now the bottom line is if we want to break down the problem in more pieces, we also need new ideas and new instruments. And EIC is going to be a nice playground for us in this sense. Will help to characterize the events we are currently looking at. And we can check the universality that the reach has, like in electron E plus E minus, do we have a reach? Like in proton-proton or proton-lead, which I did not discuss unfortunately. So what I want to say at the end is, must say that this is truly an interdisciplinary area of research. It acts like a bridge between the science of the small, the elementary particle, and the science of the large, cosmology, for example. And the next 10 years is going to be very exciting moment for us in this field. There will be a lot of fun. So all of you are welcome to join the party and we will have a celebration together. Thank you very much. And sorry, actually, I did not cover the main interesting part of my slides. Okay, anyway, thank you.
Thank you, Prabhat, for this very interesting and engaging presentation. So now we can take a few questions. I don't see any raised hands.
Okay, so I think it was.
So
yeah, I don't know what happened. I thought it will.
No, if not, maybe as you mentioned, you had those in your slides. So I would like to ask about these flow measurements in PP collisions.
Yeah.
Okay, where we are not sure. Like rather, I would support there is no medium formed there, so no question about forming a liquid medium or something. But still, we measure the V2 coefficients and all that. So what you have to say about that?
What do you mean by, so in PP you don't have a medium? That's what you are trying to.
Yeah, we are not sure. We are not sure whether we have medium.
No. Actually, we are pretty sure. The problem is following. That is what I did not discuss. Let me try to discuss. So hydrodynamics is applicable to systems where the system size is way bigger than the mean free power. Okay, that's what you see in my cartoon here. But now the problem in small, in the, can I? Yeah, now the problem in small cases, it is very small really, like PP or PLAB and dilute. But thanks to the state-of-the-art instrumentation at the LHC, we have very nice triggering system nowadays. And we can go to the high multiplicity. So what is this high multiplicity thing? In fact, this is small. System is small, but it is very dense. Okay. So as you can see in this cartoon here now, within that size, you have put more stuff. So it's a very high dense system. So what you are looking at, what is the smallest size of a QGP fluid? That is what we are trying to ask, correct? So in the limit of this coupling strength, G goes to the strong coupling limit, the LT will be very greater than 1. And in the limit of G going to very strongly, ultra strong limit, infinity, LT is 1. So the QGP fluid can be also very small in size, does not matter, okay? But what you need is the size can be replaced by multiplicity or entropy. And that's exactly we look for in our experiment. For example, in CMS and Atlas. I don't know about Alice. Alice may not do all these things. About their triggering system, I am not aware to go to such high multiplicity or not. But certainly we are doing in CMS. So that's our high multiplicity event. So what I mean by these high multiplicity events is these events are pretty, not I would say close, but pretty similar to the events that you expect in mid-central, like starting from 30% collision onwards in lead. So these are really, truly high multiplicity events. And when we looked at the Rees in small systems, we have a clear signal. Okay, it's not like this low multiplicity minimum bias Rees where you don't have any Rees in fact. This is NTRAC 50. But when you go to NTRAC, like more than 90 onwards, you see this Rees structure, 110 to 150 NTRAC. You see this structure. And this phenomena is very much explained by this collective flow behavior. So I can show you one slide here. Here, this is PLAD, first slide, PLAD top plot. Okay, you see here V2468. By the way, this is cumulant technique. It is much better in that sense. It will remove all the non-flow. So you see all these things are matching with each other. That's a perfect sign of collectivity. Multi-particle correlation, not just two particles. So V24, V26, V28 goes to infinity. They are similar. That's a very good sign. And also hydrodynamics. Look at the PID flow. Very nicely explained by hydrodynamics, correct? Different. This is Alice, by the way, this flow. Now, if you look at PP also, you have the same thing. PP also tells you that there is multi-particle correlation. And this signal indicates what is going on. Now, the question is, I think if I understood your question, you are trying to ask that whether this physics can be explained by hydrodynamics or not. That's the bread and butter now in this community. So far, the story is many of these observables are very nicely explained by hydrodynamics, except the heavy flavor particle, the flow of Chebyshev, which was expected to be low, but not low. So hydrodynamics alone cannot explain, and that is why the color glass condensate and other models are coming into picture, the gluon saturation stop. But that's not the story. I mean, that's not the entire story. Many things can be explained from this. So I am very optimistic that many signals are really very close to hydrodynamics fluid-like behavior, but whether the QGP size should be small enough and how small, that's still a question in this community, and it is debatable. That I agree.
Yeah, no, it's not only hydrodynamics, there are other models, even Monte Carlo models, which doesn't assume any formation of QGP, they can explain the region and everything.
No, I would not trust Monte Carlo model that much right now. Monte Carlo model.
No, it's not about trusting. What I'm telling, some models can explain the experimental results. So one cannot be very sure that you have to have a QGP fluid in PP collision. That's what I'm telling.
So far, I think that's the best way to describe. But this is not the end of the story.
Yeah, that's certainly.
Many of the, like starting from the spectra to the collective flow, everything is nicely explained by collective hydrodynamics or flow. But as I told, the heavy flavors part are still yet to answer what is going on. So those things are under investigation. And that will be, in that sense, that is why I mentioned the EIC will be very good actually. We will look for E plus, E minus, or electron ion collision and try to see what is the origin of this region.
Yeah, that would be interesting.
The ridge is everywhere, but whether the source, the origin of the ridge is similar for all the systems or not, that's the
yes, that is still under investigation. That's what I'm telling.
Yeah, thank you.
Yes, so if there are no raised hands, then let's thank Prabhat again.
Thank you.
And then we can move to the talks by the students. So the first talk in this series would be from Pankaj Kumar. So Pankaj, are you ready?
Yes, ma'am. Hello.
So he'll be talking about the design and development of compact SC linear electron accelerator to treat wastewater. So it's like the potable water is a global concern. So he would be presenting his ideas on this. So over to Pankaj Kumar.
Hello, everyone. My name is Pankaj Kumar, and I am working under the supervision of Professor Raghav Verma. And my topic is to design and development of compact superconducting linear electron accelerator to treat the wastewater. So as we know, the water is an essential component for the human beings and also for the other species. Now this time the water, basically the overall water on the earth, only 2% water is available as a fresh water. And this fresh water, 87% in the form of ice and 12% in the groundwater, means only 1% flow in rivers and lakes. And now at this situation, overall the world, this water has been polluted. And this is the world map which shows the stress level of water around the world, where India comes under the high stress level. In India, if we talk about the ancient river that is most important was Ganga, we have degrade the water quality of Ganga by domestic and industrial wastage, harmful pesticide and fertilizers, animal carcasses and unburied human corpses, and mass basing and ritualistic practices. So that degrade the water quality. And if we compare the data, so this is the permissible limit for water quality, and these are the water quality parameters: BOD, biological oxygen demand, dissolved oxygen, chemical oxygen demand, and all these things. So if we see the contamination level at Allahabad and Varanasi, we see the BOD and COD value is not so much high, but the fecal coliform, which are way beyond our permissible limit. And the today's conventional treatment process are fail to treat this type of high fecal coliform. And so we have to find a way that can solve this issue. So as I discussed that waste conventional treatment is failed to treat this type of impurity. So let's discuss how conventional treatment works. So basically, conventional treatment have some stages. One is the pre-treatment, one is primary, another is secondary, and last is the disinfection process. So in primary and secondary, mostly the COD value, the chemical oxygen demand, has been reduced up to 75 to 85%. And after that, this COD can't be treated because it has some non-biodegradable and toxic molecules that can't be treated by this aeration and sediment, this type of systems. And the other thing, the disinfection has some also limitation, like chlorination. Means chlorination will add chlorine in water, and that chlorine will be carcinogenic for human being and the environment also. And ozonation has also some limitation because ozonation is dependent of temperature. So it can't be more efficient in every temperature. So we have to find a way that can solve all these modern problem of this wastewater treatment. This is the normal situation, and if we go to the worldwide, we found that there is a new contaminant emerging every day, and these are contaminants is the worldwide problem. The current conventional treatment process is insufficiently, it's not unable to treat those type of impurities. Most of these impurities contains aromatic compounds. It's basically hydroxybenzoate and ibuprofen like this. So we have to find a way that can remove all this type of impurity, or even this type of changes. This type of impurity can be treated. So electron beam, the radiolysis process, is the promising result that can treat with, all type of impurities. So this is the how electron beam interact with the electron beam, or any high energy radiation interact with the water molecules. So when electron hits, it produces these radical species, and these species contains oxidizing and reducing agent. So that's why this process is also known as the advanced oxidizing and reducing process. It contains oxidizing and reducing both agents. And this is these free radicals basically react with the impurities, and they will remove all, they will chemically react with those impurity and remove all those impurity. So G value represents the production of these products with respect to per unit of joule energy. So let's how this these radical species can react with impurities. So let's take an example, which is more, as I have discussed earlier, concern of emerging contaminant of emerging concern, the aromatic ring, because aromatic ring is common in every treatment, every compound that can be treated by this by today's conventional treatment process. So if this benzene ring interact by this type of radicals, these radicals break this benzene ring and convert into aliphatic compound, and those aliphatic compound further oxidize and converted into carbon dioxide and H2O molecules. So this process is known as the mineralization process, in which every carbon atom has been reduced to CO2 gases and H2O molecule. So means that water, without adding any chemical or without adding any other substitute compound, we can convert every organic compounds into, we can remove every organic compound from the water. So this is an example of the paper show the hydroxyl radicals degradation of ibuprofen. So ibuprofen is basically used in the drugs to treat the headache basically, and this ibuprofen is toxic in environment if it go for other species basically. So this data has been shown that the OH radicals can degrade the ibuprofen at various dose. We said 1 kilo dose, there is a largest degradation. This is showing the toxicity, how the toxicity will change. So means we can say directly that any radiation process can treat this type of impurity, although toxicity can also be decreased. So this is the another advantage of electron beam, that electron beam can treat all type of impurities like dyes, halogenated carbon, industrial pollutants, metal ions, pesticide, pharmaceutical, and even coliform, up to 100 to 90% of removal efficiency with varying some doses. So we can now say that electron beam is one treatment that can solve all the issue of emerging of this new world. So basically the treatment plant for any river that contains pre-treatment, primary, secondary, same as I have discussed earlier. So if we applied electron beam here, we don't require the secondary and disinfection process. If we replace it by just electron beam, then it will be very compact, means the size will reduce, and also the treatment process will increase, because as we have seen earlier, the electron beam irradiation time takes around 10 to the minus 16 to 10 to the minus 9 seconds. So that is very low time. So means we can increase, we can fit this our electron beam in flow through system, and this is our conceptual design of electron accelerator, which is basically our task. And one more thing I want to tell, that the size of this electron beam is very low, and we can fit at any position, and we can also fit inside any conventional treatment to enhance their efficiency. I will discuss this later. So this is our conceptual design. So this is our main actually part. So we are going to we have planned to design and development of 40 kilowatt power of electron beam superconducting electron accelerator with of energy 1 MeV. So this is the electron gun, and solenoid is basically used to focus the electron bunch, and this is the cavity which accelerate the particle to required energy, and then the electron will pass through and come out from this window. So our team has worked on this setup, and every person has decided has different part to our simulation. So so our one person has done this gun simulation and on these parameters, and one person has has this solenoidal simulation on these of aspect, and I have done the cavity simulation on these aspect. So these are our final parameter, optimized parameter, which we have simulated in software, and our next plan was to design and fabricate and development of these design in lab, but because of the COVID situation, we couldn't do that. So we have to change our aim. Means the COVID situation can't. It is very serious, so we couldn't go for the fabrication and to go for the Japan to fabricate them. So we have to change our way. So in India, so we have done some we have worked on application of electron beam irradiation here. So let's discuss the two examples. So the treatment of electron beam process is not a new concept. It has been done in several in the whole world. So this is the example of Daegu dyeing industry, which is situated in South Korea. They have used DC accelerator. So in their initially their concern was nickel, that is a non-biodegradable toxic compound, which has of course aromatic rings. So initially they can't treat this type of impurity with their initial wastewater plant. But after adding the electron beam before this first two steps, they found they are able to reduce this type of problem. And moreover, they have reduced the treatment time. Basically the biological, this process takes around 17 hours. But after applying the electron beam, they reduce the 17 hours time to 8 hours. So I mean, there is an advantage by adding this electron beam with this system. Another example is the paper mill. It is also from the South Korea. So in which initially they have 2 stages of chemical treatment and 2 stages of biological treatment, and they were able to recycle only 30 to 40% of wastewater. Oh, sorry, 30 to 40% of water. But after adding after adding this electron beam, after this first stage of chemical and one stage of biological treatment, they were able to reduce 70 to 80% of water with high efficiency. So means you can see here the initially their initial existing technology can remove COD up to this level. By adding electron beam, they have further reduced the COD and TOC value, the total organic compound. So we have done the same thing, and we tried for the pharmaceutical wastewater because it contains large amount of impurities. And,
Ankit, you have 2 minutes, okay? 2-3 minutes.
Okay, ma'am. So we have selected 2 samples from one stream, from here and from here, and from another stream we have selected other sample. So total 3 samples were collected, and this is the initial parameter of these samples. So we have this is our experimental setup. This is linear accelerator, normal conducting linear accelerator, which is situated in Samir. And under this table, we have irradiated setup like this, and we have irradiated wastewater. By this irradiation time, their associated dose is given here. So I'm not going to discuss. We have done lot of work there and tried different type of combination. So I'm not going to explain everything here. So if anybody interested, you can find here my all work. So these are the final results. So we were able to reduce if we apply electron beam here. So we were able to reduce COD up to 43.95% with the combination of coagulation plus electron beam. At this stage, we were able to maximum reduce COD was 65%. That is, the combination was tried as electron beam plus coagulation process. But for sample 3, the COD maximum reduction was 54.7%. That is for just only electron beam irradiation. So this is our result, and this is our visual results. So this is sample 1. This is before irradiation, and this is after irradiation. So after irradiation, the turbidity means the solid particles were formed inside this water, and we have filtered them out, as you can see from above side. And there are other treatment processes. And this is our initial wastewater, which have this type of color. And after the irradiation of 60 seconds and filtration, we have reduced this color as much. So so we have optimized our parameter for different parts of electron beam accelerators in electron gun, solenoid organ cavity. And we have also see the effect of combined effect of coagulation with electron beam, and we found that there is a very good result. And the maximum efficiency of electron beam treatment was found at S2 sample, basically at this position. So we can say that electron beam can be very efficient if it replaced this process, and we situated here electron beam, because there is 65% reduction in COD. And more experiments are yet to perform before establishing this technology here. This is our future plan. So in wastewater treatment, we have to done these type of experiment. We have to see the effect on polycyclic aromatic hydrocompounds and activated pharmaceutical ingredient. These two components are known as CECs. I have discussed earlier. So we are going to see the effect of electron beam in this on this in BRC, and effect of heavy metals also, including arsenic, and effect of coliform, and those measurements we have to done for wastewater treatment. In accelerator designing and development, we have to calculate the tolerance for each design, and beam dynamics, cryogenic load calculation, and fabrication of all component, and assembling and testing further. This is one.
Thank you, Pankaj, for this very nice and clear presentation. So now we can take a couple of questions. Those who have questions can ask Pankaj now, but I don't see any raised hands. Okay, so if we have no more questions, then we can move to the second speaker. Our second speaker is Tulika Tripathi. Tulika, can you share your slides?
Yes, ma'am. No.
So she'll be talking on even by even fluctuations of mean transverse momentum in heavy ion and PP collisions. So over to Tulika.
Can you see the slide?
Yes, I can see the slides.
Okay. Good afternoon, everybody. I'm Tulika. And today I'll be showing the results of my study on mean PT fluctuations in lead-lead and PP collisions at 5.02 TeV and xenon-xenon collision at 5.44 TeV. My slide includes motivation, definition of observable, analysis details, results, and future work. I'll start with the brief motivation behind this measurement. Because of the production of a large number of particles in a single event, an approximate thermodynamic state is produced. So as in heavy ion collisions, typically only a subsystem can be analyzed due to the pseudo-rapidity restriction embedded in the whole system, all in the same heat bath with a temperature T. The energy and the particles can be exchanged. So in this case, we can consider it as grand canonical ensemble, which is characterized by a pressure P as a function of capital like T, V, and mu. That is the temperature, volume, and the chemical potential of the system. event by event fluctuations of the temperature and the conserved charges can reveal properties of strongly interacting matter created in heavy ion collisions. Fluctuations may provide insight into the relevant degrees of freedom within the collision, that is whether the initial state of the collision is compatible with the nucleonic scattering scenario or whether the subsystem patronic structure has to be taken into account. So now I will go to the observables that I'm using in my analysis and the motivation behind using them. So the first one is, as you can see, is the mean PT. So in heavy ion collision, the PT distribution can be explained by an exponential function as shown in this equation, and for low PT, which is for the low PT events, and one can see that the mean of such a distribution is related to the temperature. So so we can take event-wise PT as a proxy for a local temperature of the system. That is why we're taking mean PT. And the second one is the two-particle correlator. So here it is. So I have chosen, so let us consider a Poissonian equation. As you can see on the right-hand side, top right corner of the slide is the Poisson equation. And I have chosen this equation because the variables are discrete and are independent of each other. For a function like this, the expected value is equal to a constant. So when we try to find the covariance of such a function, incorporating the expectation value, it turns out to be 0. So here is a clue for a robust variable, because like the value of the correlator for statistical fluctuation will be 0 and non-zero for dynamical fluctuation. So whatever value we get, it will be solely from the dynamical fluctuations, which consist of mini jets or resonance decays. So in the bottom, we can see a plot. The results of the two-particle transverse momentum correlator relative to the mean PT with respect to the average charge particle multiplicity is found previously for 2.76 TeV center of mass energy. The results in the different systems sizes, say xenon, and a higher energy would be an interesting thing to measure. So now I'll define my observables. So the first one is the mean PT. As you can see, it can be calculated by the summation of all the PTs in the multiplicity class divided by the number of events, number of particles in that event. And the second one is the two-particle correlator. As you see the equation 1, it is described by this, where we can multiply the PT of the PT of the ith particle minus the mean PT of the multiplicity class into the PT of the jth particle minus the mean PT of the multiplicity class, and divided by the number of pairs in that class. So number of pairs can be calculated as the n into n minus 1 by 2. And all the definitions are shown as shown in the slide. So the alternate method to calculate is the method of moments, that you can see delta Pi, delta Pj can be seen as the equation number 2, which is essentially same as the Cm that I explained earlier. And after a theoretical calculation of this equation 2, we get into the equation number 3, which I'm using to produce my results. So here the Qn is equal to the summation of the transverse momentums to the power n. And to produce my results, I'm using root over of the quantity Cm divided by the mean PT to make the quantity dimensionless. Now here are my analysis details. So for lead-lead collision, I'm taking the LHC-18Q data set, which corresponds to the 5 TeV center of mass energy. And the Monte Carlo data period used is LHC-20A, which is anchored to LHC-18Q to obtain the average charge particle multiplicity. Now the event selection criteria is given in the left-hand side, and the track selection criteria is written on the right-hand side. For the vertex determination, I'm using -10 to 10 centimeters for VZ calculation. The VTX endpoint is basically the tracks that only those tracks are those events are taken into consideration that are produced by at least one track. So that should be greater than 0. And the vertex Z difference TPC minus SPD is basically the vertex determination by the global track selection and the SPD track selection. The difference of that should be less than 10 centimeters. And it consists of 80 runs. For pileup removal, I'm using Ali event cuts class with the following flag. For track selection, I'm taking the transverse momentum range from 0.15 to 2 GeV per C. The lower limit is taken to keep an uniform efficiency, and the upper limit is taken because I'm sticking the analysis to the soft and bulk path. The eta range is taken to be 0.8. The filter bit used here is a hybrid filter fit, which is 768. Hello? I'm unable to move the slide. Can you see my slide?
It's not moving.
Yes,
we can see your slides, but it's not moving.
Okay, now it's stopping. Okay, sorry. So these are the external, the pileup cuts which I have used manually. The left-hand side plots is for TPC versus the TPC trackless versus V0, and so you can see there is a lot of outliers. So to remove that, I used some cuts manually to get it clean, and the right-hand plot is a cleaner plot. So after doing incorporating all these things, I finally got my results. Now there is a multiplicity. So there is a multiplicity determination technique also that I'm using in my analysis for the determination of the x-axis. So I get the measured multiplicity and accept it, which is number of tracks in an event K, which survives the track selection criteria. The two particle correlator is calculated in the interval of n accepted. Now afterwards, the multiplicity axis is corrected to obtain dn charge over deta. I have explained it in the next slide. So here the slide 1 is in the y-axis. In the picture 1 and the y-axis, I have dn charge over deta published value that you can see for a corresponding value of centrality that you can see on the extreme right table. So this is a published result which I'm using to get the dn charge over deta. Now in the second plot, I have calculated the number of accepted charge particle in that particular centrality range and corrected it for efficiency. And after doing this, I'm plotting this plot 3, where I plot it for dn charge over deta published versus the n accepted that I calculated, and I get a linear plot, and I fit it to get the dn charge over deta by putting the parameters p0 and p1 that I get from the fit, and finally I get a dn charge over deta value, and I'm using it my results here. So this is my final result, where I'm the left hand side plot is for mean pt versus dn charge over deta. The right hand side is the relative fluctuation of the mean PT versus dn charge over deta. So here in the mean PT, we can see the mean PT increases with the increase in the multiplicity, and the correlator decreases with the increase in the multiplicity. The red square is the published result for 2.76 data, and the blue square is what I have observed for lead-lead analysis. So the values obtained from the 5 TeV agrees with published values. The relative fluctuation decreases with the increase in the multiplicity. I've repeated the analysis for xenon-xenon collision at 4.44 TeV, and the left hand side is again the event selection, right is the track selection using the same pileup removal techniques, and I get this final results where we can see that the values of correlators in both the systems agree with the published result, and the multiplicity is lower in case of xenon-xenon. Now I have tried to also find the correlator and mean PT in the transverse sphericity classes. Like transverse sphericity is basically used to discriminate between the hard and the soft processes. So the first one is the jetty, which are, if you can see the figure, the back-to-back structure is for the jetty-like events, which is an indication of the hard QCD, and the isotropic events are in the circular, you can see a spherical symmetric structure that indicates the underlying events of the soft QCD for the low momentum transfer. Now there are different kinds of event shape variables. So one of them, which I am using, is given in this equation. This is called as the transverse sphericity, represented as 0. And the event, the variables ranges from, this variable ranges from 0 for a pencil-like event to a maximum of 1 for circularly symmetric events. This equation is then evaluated and calculated to be able to use in the analysis. And here is how the calculation is done. After that, I skipped the PP results, but okay, here also we can see that this is found for PP collision that can be taken from the LHC 17P and LHC 17Q data sets. The Monte Carlo periods taken are given here. Here it contains 200 million events. The trigger is Kane 7 for pileup removal. I'm using this flag as shown in the green color. And
Tulika, you have 3 minutes more.
Yeah. Yes, ma'am. It's almost over. So the filter bit that I'm using is 1. So after using these analysis cuts, I'm finding the sphericity for my analysis. So as you can see, this is the sphericity distribution for PT range greater than 0.15 GeV per C. And the first, say 0 to 10% is taken to be the jetty-like events. The values that I've obtained is 0.005 to 0.315. This is for 0 to 20%. And similarly for 80 to 100, which is what corresponds to the isotropic events, the values are 0.795 to 0.985. As you can see, the maximum and the minimum limit for the jetty for the sphericity class is 1 and 0 respectively, and hence we are getting the values within 0 and 1. And for these classes and these values of sphericity, I have calculated my observables here. As you can see, the mean PT versus N accepted is calculated for different sphericity classes. The black pluses are for the integrated class. The red triangle is for the jetty-like events. The blue squares are for isotropic events. And we can see the jetty events have systematically higher mean PT and larger slopes as compared to the isotropic and integrated. And in the right hand side, the more correlation is for we can get a message that more correlation is coming from the isotopic events. So this is all that I've got from the sphericity result, and there's something that I missed probably here. Okay, I missed this slide where I calculated the correlator for me and mean PT for PP collisions, and here are my results. We can see in the from DN charge over data from 40, I've taken high bin width because there was a lot of fluctuation in the end, so the bin width was increased. On the right hand side, you can see the results that I have got and the result that was published. The comparison of it is given in the right hand side plot, and in the left bottom corner, I have got the result for the correlator for different charge pairs. The green dots are for the unlike pair combinations. The blacks are for the all charge pairs. The blue and the red are for the like charge pairs. So the correlation for the positive tracks seem to be slightly higher than the negative tracks. The tracks from the positive and negative signs are in between. So that was something I missed. And yeah, so this was my final result for the transverse sphericity. And so the summary and in the future work, I'd say that the event by event fluctuation of the mean transverse momentum of charged particle in PP and lead collisions at 5 TeV, center of mass energy, is observed for LHC, and LHC in the ALICE detector are presented for the first time. Now the results are also compatible with similar measurements at lower energy. The transverse sphericity dependence of two particle correlator is also observed for the first time. Now in future, I'll try to find the correlator for the like and unlike pairs for all the systems and observe the systematic uncertainties. So thank you. Yes,
thank you, Tulika, for this presentation. So we can take questions. I don't see any raised hands. So we can go to the next talk. The next talk would be, so kindly stop sharing your slides, Sulika.
Yes, ma'am. Yes, ma'am.
So the next talk is by Pankaj Chetri. So Pankaj, can you share your slides?
Yes, ma'am. Am I audible, ma'am?
Yeah, you are very much audible. So Pankaj will be speaking on wide bandgap semiconductor detector for proton beam position monitor. Pankaj, you can start your talk.
Okay, good afternoon, everyone. I'm Pankaj Chetri. Today, I'm going to discuss about development of wide bandgap semiconductor detector for proton beam position monitoring. The basic goal of this project is to develop a wide bandgap semiconductor detector that can be used for intense proton beam monitor in high radiation environment. So that's our main goal of this project. So I presented my seminar in sets of 4 questions, like what are the various charge of particle? I mainly consider like proton into consideration, and how they interact. It means like how they interact with the semiconductor materials, and why we have selected the wide bandgap materials. Like there are already gauge detectors and low bandgap semiconductor detector. Why we have selected the wide bandgap material that I'm going to discuss, and how our detector operates. By this, it means like in what mode of operation a detector operates. There are 2 modes of operation, photovoltaic and photoconductive. So what modes in our detector operates, so that I'm going to discuss, and what is our experimental setup and irradiation response of our preliminary tests. So that I'm going to show during this presentation. Okay, let's start with what are the various elementary charge particle and how do they interact with matter. Like beta, proton, and alpha are commonly known irradiating charge particle, and we focus on their energy loss in matter through Coulombic interaction. So there are very ways in which the particle can lose the interaction, but we are focused on the Coulombic interaction. There are other elementary particles like pions, kaons, hadrons, and are also studied in high energy collider environment. In this presentation, I'm mainly focusing on the proton beam and in its application as for detector application. And the detector design was made using the concept of energy loss of irradiating particles in matter through Coulombic interaction. And this Coulombic interaction is governed by the Bethe-Bloch formula. And let's see how the energy is transferred in a material medium, like semiconductor or any medium, how the energy is transferred. Whenever irradiating particles like this, okay, just a second, like this passes through a semiconductor material, it generates electrons and holes along its path. So which we are going to use for detector application. Like these electrons and holes, we are going to get across the electrodes and get the signal out of it. So how the particles behave in a material medium is a semiconductor or any medium. So let's start. As a statement suggests, as the particle interact with the material medium, it start ionizing the material medium, and hence losing energy, and then the velocity of the particle also decreases. So when the velocity of the particle decreases, so particle decreases, and the Coulombic interaction starts increasing, and hence leading to vast amount of energy loss, and suddenly particle goes to rest. So let's go deeper into it. So what happens initially when a charged particle enters the material medium? It is at very high speed, velocity, and it has a very high energy and moving at very high velocity. Hence, it doesn't interact. It doesn't have enough time to interact with the material medium. So the energy loss is minimum in the initial range. So as the particle starts interacting with the material medium slowly, it starts ionizing the material medium, and hence losing the energy, which results in the decrease in its velocity of the particle. And when the velocity of the charged particle decreases, the Coulombic interaction increases very sharply, and hence the energy loss occurs, and suddenly the particle goes to rest, and we can see the sharp we can see the sharp decrease in the energy loss. So we can see the sharp decrease in the peak. So that's what this shows. In this, the other green and blue slides show the how electrons and photons behave in a material medium. Like electron is already explained by the Pankaj Bhaiya in his electron beam accelerator. And the photon is also, you can see in the proton and electron, you can see there is a decay is very very broad. So it gradually decays. In case of the proton, it's interact with the matter in a little different manner. So let's see how. So let's talk about why bandgap semiconductor material. Like right now, we know that how energy is deposited in semiconductor material, like how how electrons and holes are generated when the particle passes through a medium by the momentum transfer instead of like getting absorbed. Photon, in case of photon, like particle get absorbed and then it generates photons. In case of the in the charged particle, the momentum transfer generates electrons and holes. So we know right now we know that how the charge carriers generated in case of the semiconductor by the irradiating particles. So now the second question is why we have selected the wide bandgap semiconductor material. As I told earlier that there are only gas detectors available, which is very used for the detector application and is widely used also. The problem with the gas detector is like the resolution. Like gas detector is very high amount of energy to generate electrons and holes out of the sample. So, but in the case of like semiconductor detectors, like consider silicon germanium, it has very low band gap. So it needs very lower amount of energy as compared to the gas detector to generate electrons and holes, which helps in increasing the resolution of our detector. Like detector will be able to detect very small change in the energy. So that's the reason that we move to the many of the detectors are made with the semiconductor detector. So if you are having silicon germanium already, why we are looking for the wide band gap like gallium nitride and diamond based detector? Diamond is very widely used as a proton detector. So why we are move to the wide band gap? The reason is radiation tolerance. Like the wide band gap material has a very high radiation tolerance. Like I'm talking about diamond. Diamond very much immune for the radiation tolerance as compared with the silicon and gallium, and it has very high temperature stability. Diamond, because of having its very large band gap across the conduction and band gap, it has very high temperature stability across stability. Whereas in the silicon, because of having low band gap, even the small change in temperature will affect our signal strength, which is very not good. And to use silicon detector, we need to supply an additional cooling setup for the silicon detector to work properly, because continuous irradiation by the proton beam heats up the sample, and the behavior at what you have tuned your amplifier and electronic setup will not behave as you expected. So that's the problem that arises in case of the silicon and germanium based detector, low band gap detector. So that is very much minimized with the large band gap detector. So because of having large band gap, is dark current is very low. So that's also a good point about our wide band gap semiconductor material. And avoid the need for cooling. It's not avoid, like it's reduce the need for cooling. Like it doesn't need that much of it doesn't have that much effect as in the case of the silicon and germanium. So the need for cooling is less as compared to the silicon and germanium based detector. So that are the factors that lead us to select a wide bandgap material for detector application. So let's see. So operation mechanism of the semiconductor ionization radiation detector. So right now we know that how it generates like electrons and holes, how it generates. I've already explained it. So what are the parameters that affect the signal strength across the electrode? So this drift velocity of the particles, like electrons and holes which are generated, how fast it reaches the electrode, that affect the fast response of our detector. So, and the distance between the electrode, that this distance between this electrode also affect the fast timing response. If the distance between the electrode is less, then the generated electrons and holes will reach the electrode very fast. So it will we have a fast response detector. So that also we have to consider while making a detector. Geometry of the detector also plays a major role. Like so, and recombination. If you have generate by radiating particles, it generates electrons and all. But there is large possibility the generated electron cell will recombine itself and it recombine itself. So this we won't get a signal across the electrode if it recombines. So that we need to reduce. So if we increase the charge electric field across the electrode. So what will happen? We'll high intensity of electric field. So generated electrons and hole will be drifted very fast, and they won't get enough time to recombine, and this will increase the signal strength of, across the electrode. And the problem that the semiconductor detector occurs, like the charge trapping, with the continuous use of the irradiating particle continuously, it develops some defects. Like I told you that silicon and germanium are have radiation damage. So because of which it develops defect, which increases the charge trapping, which reduces the charge collection efficiency across the electrode. So that is the problem that arises in the case of semiconductor-based detector. So that also need to be considered while making our semiconductor detectors. So earlier I told that what thermally generated electrons on holes are very less as compared to the signal number of electron holes generated with the radiation particle. So in the case of wide bandgap, like zinc oxide and gallium nitride, the bandgap is very high. And what happens in the case of, like, you will say that the bandgap is suppose diamond is 5 eV, and it the thermally generated may give around 5 eV. But the thing is, it's in the when we move an electron from conduction valence band to conduction band, it in the case of irradiating particle, it needs around 3 times of its band gap. So if you are having a semiconductor metal which have the band gap approximately 3 times 5 eV, then it needs around 15 eV. In the case of diamond, which has the band gap of 5.5 eV, it needs around 16 electron volt energy to be transferred to the electron to generate electrons in a hole pair. So that's also a fact that it suppresses the thermally generated electron source by a large extent. So I told that the electric field across the electrode, that the voltage across the electrode enhances the electric field. So the electric field enhances the signal across the electrode that we get. So we can say that we can make the electric field very large, up to a large extent, but there is a certain limitation of every material itself. Like electric field will enhance the drift velocity up to a certain extent, then it start decreasing. So why it happens? Like so in the valence band, the effective mass, when the electron were when the concentration of the electrons were low in the conduction band, the effective mass was around 0.005 rest mass. But when the number of
Sorry to interrupt, Pankaj, but you have 3 minutes more.
Okay, ma'am, I'll come. Okay, so as the number of electrons get accumulated in the conduction band, the effective mass of the get increases. Like it gives increases up to around 100 times. So which affects the which is one of the factors which affects the decrease in the drift velocity with the increase in the electric field. So that I wanted to emphasize. So how our detector operates? Our detector operates on 2 modes of operation: the photovoltaic and photoconductive mode of operation. Photovoltaic means this, like we haven't supplied external electric field. Like here, this is the inbuilt electric field which is of the semiconductor, like in the intrinsic, not intrinsic, in the doped semiconductor, the barrier which generates the electric field. This is the electric field which is generated by the its internal behavior, not by the external supplied electric field. So whenever the charged particle passes through a material, it generates electron and hole. As it has less electric field, so the number of strength of the output that we get across the electrode is very low, and very slow, as there is no high electric field. So the It is not used for the fast, prefer for high speed application. And is the accuracy is high, but it can be used accuracy high in terms of like to check whether the sample is working as a detector or not. Just for the basic test we can use, but it is not preferred for the main detector application. So in the photovoltaic, like you must have seen the solar cells and those things. It is used for the in the photovoltaic mode. So this is a photoconductive mode of operation. So at the time we supply the voltage, so it enhances the electric field, so which improves the signal across the electrode, and we get the signal. So this prefer for with the biasing, we get higher dark current. Like the dark current increases, but the signal which is increased is very up to by a very large extent as compared to the increase in dark current. So it doesn't count as a demerit. So it is best suited for high speed application. So yeah. This is a photoconductive modes. Like in the this slide, you must have seen there's the load resistance which affect which is there. So the load resistance which we use in the detector affects the sensitivity of our detector. If the load resistance is very high, at the time we will get a highly sensitive detector, but the range of operation up to which it can operate is limited. If you use a small RL, at the time the range of operation it can work, it's large, but the sensitivity is low. So while making the detector amplifier setup and the bias T network detector prototype, we have to consider that value also. So let's go to the what is the experimental setup and what is the preliminary irradiation response of our detector. So this is the PCVD diamond, polycrystalline diamond that we have used for our irradiation test at IGCAR experimental setup. It is used in the photoconductive mode as explained earlier. So this is experimental setup that we had made amplifier and bias to bias the sample and get the signal out of it. So this before we check the response, we should know how does the beam profile like. The beam is a DC beam, fluence of 10 to the power 10 proton per centimeter square area, and the beam energy is maximum it can provide 1.7 MeV, and the diameter of beam is 10 mm, and the beam current is 100 nanoampere. Maximum it can go at to 400 ampere. The beam is a DC beam with a scanning frequency of 1.025 frequency. With the scanning frequency right now, you understand that it is moving in a 45-degree to and fro direction. So that's what is meant by the scanning frequency. So finally it will give like this kind of a shape of the beam. So this is what it will look like. So this is what the beam move in a periodic pattern. So we get a signal of this shape out of our sample of this geometry, metal, semiconductor, metal geometry. So when the beam is in this region, as you can see the peak is very low. When the beam is in very this region, at the time you will see that the peak is very high, and when it is low, it is like. And this is a repetitive pattern. That's why we can see the pattern is being repeated after certain time. And how the small peaks that you say, what is that? This is the, as I told you, there is a scanning frequency 1 kilohertz. So these small peaks, the variation is corresponds to the 1 kilohertz frequency, and it is in the IGCAR setup there is a 3 size beam spot size that we can adjust with the metal block ABC, which defines, like I told you, we did it 100 mm diameter. So diameter is set by ABC, which is a collimeter kind of setup. This is the preliminary results that we got out of the sample, and there is a lot of improvement that need to be made on the sample. And this is switching response, like when the beam is off, what we get, and when the beam is on, what is the get. So what is the signal to noise ratio that we can get out of it? So this is the nature of the beam, and the signal out of our sample. Still there, this is a PCB diamond we are working on, and we are still looking for the very different kind of material apart from the diamond. The diamond is very expensive material, and we are looking for the alternative of the diamond to make a wide bandgap semiconductor detector, which will replace the diamond. As we know, the diamond is very expensive and it cannot be used in the large number and very large size. So we are looking at the different materials which can give a diamond-like response, and we'll get very good signal out of it. So these are the references that I have followed, and thank you for your attention. If you have any question, then feel free to ask.
Okay, thank you, Pankaj, for this nice presentation. So now the talk is open for questions. So I don't see any raised hands, and if we have no questions, let us thank all the speakers of this session. And with this, we also conclude the third session of SYMPHY 2021. Thank you very much.
Thank you, ma'am.
And now we are going to start the session 4, which is the astronomy, cosmology, and gravity. And so I will like to request Professor Archana Pai to chair this session. Over to you, ma'am.
Hello, everybody. Am I audible?
Yes, ma'am, you are audible.
Okay, thanks a lot. Yeah, so let's begin the fourth session of SYMPHY 2021. In this afternoon session, we have one expert talk and then we have 2 students talk. So in this SYMPHY, we are very happy to welcome Professor Somnath Bharadwaj, who is an expert on 21 centimeter observation, physics with 21 centimeter observations. So Somnath has done his PhD in Indian Institute of Science and Raman Research Institute, and subsequently after a postdoc at HRI, he is a faculty at IIT Kharagpur, and for I think past more than 2 decades he has been working on dynamics of large scale structures. So today he will be telling us the story of probing the universe with 21 centimeter observations of to use Somnath. Somnath, can you hear me?
Yeah, I can hear you.
Yeah,
Let me start. Yeah.
Yeah, sure. So it's
thank you.
40 minutes. I will warn you maybe 5 minutes. I mean, after you finish 40 minutes, okay?
Okay, thank you.
Yeah, okay.
So, sorry. Yeah. So, good afternoon, everyone. I'm going to speak. The topic of my talk is probing the universe with the hydrogen 21 centimeter line. And just a minute, let me get the hang of this. I have not. Can all of you see the slides?
Yes.
Yes. Okay. Can you hear me also?
Yes.
Okay. So before starting off, let me just.
Som, I can also see the next slide. So I think you just have to go to the slideshow.
I am in the slideshow.
Yeah, but I can see the next slide as well.
Okay. So, okay, I think the simplest solution will be how does one change this now? Wait.
Yeah, I think this is yes.
Can you, is it better now? Has it changed?
Yes.
Good. Very good.
Yeah. Okay.
Thanks.
Yeah. So, so let me first just mention that there are the work which I'm going to present here, and we have been working on it for nearly 2 decades now, has been done in collaboration with a lot of people. And this is a picture which shows some of them. And okay, there is some difficulty. Has the slide changed?
No, actually it has again gone back to the previous one where we are able to see your next slide. So
I'll just present again.
Full screen.
Can you go to the display settings? Maybe that is where the things are. Can you go on the top? I can see a display settings tab. Oh no, it's gone now.
Okay, let me just start. Is it okay now? Yeah, I think it's okay now. Yeah.
Yeah.
Can you see the slide now?
Yes,
Yeah.
yes. Now
Yeah,
we
yeah.
can see. Yeah.
So this is a picture of some more of the collaborators, and there are this is a relatively old. These are relatively old pictures. So I have there are more people who are participating in this, whose pictures I am unable to show you right now. But the point is that there are a lot of people participating in this in India itself, and so let me start off by doing two things. So I'm going to introduce the two terms which are there in the title of this talk. So one is the universe and other is the 21 centimeter line. So let me first briefly introduce these things. So let me first introduce our current model for the universe. So we have a model for the universe where it is expanding, the expanding universe. And the universe is infinite in most cases. So we have an infinite universe, and the picture on the right, the grid points there, the graph, the small bit of the graph there is a part of the universe. And you can imagine a galaxy sitting at every grid point. And the same bit of the universe at a later time now expands to what you see on the left-hand side. Okay. So you can see that the separation between each galaxy increases. The whole universe is filled with such galaxies. It's an infinite universe, but there is an expansion here. Okay, this is the picture which we have of the expanding universe. And as a consequence of the expanding universe, there is something which happens, which is as follows. If there is a source over here, S, and an observer sitting at a large distance, O, any light emitted from the source with a wavelength lambda emitted, as it propagates through the expanding universe, because of the expansion of the universe, the wavelength of the light also increases, and the observer sees it at a larger wavelength, lambda observed, which is related to the emitted wavelength through this factor 1 plus z. And we shall refer to this z as the redshift. Okay, so the point is, because of the expansion of the universe, the wavelength of light which comes from a distant source, it increases as the light propagates in the universe, and the factor by which it increases is 1 plus z, and we shall refer to this z as the redshift. Okay, so this picture will play a crucial role in what I'm going to talk about in this talk. So let me just explain this picture. So I am the observer sitting here, and as I mentioned, that light gets redshifted. So there's an increase in the wavelength as the light propagates to me from distant sources, and this is quantified by this redshift. So different redshifts essentially mean different distances. So Z1 is a low redshift from where the light comes to me. Z2 is a larger redshift, so a larger distance, so the wavelength increases by a larger factor. And Z3 is an even larger redshift, which comes from an even larger distance. The other point is that light takes a finite time to propagate. So not only do you have redshift being related to distance, but there is also time. So the light which comes from a redshift Z1 was emitted at some time, but the light which comes from redshift Z2 to me now was emitted earlier, because it takes light longer time to come from Z2 to me, and the light which was emitted from Z3 was emitted even earlier, right? So the larger the redshift, the larger the distance, the larger look back time, further back in the past of the universe that we are probing. Okay, so if we can probe light coming at different redshifts to us, we can probe different distances, we can also look back into the history of the universe. Okay. Let me now introduce the 21 centimeter line from hydrogen, which is the other key player in this talk. So this line originates from neutral hydrogen, which in spectroscopic notation, it is denoted by H1, neutral hydrogen, which we use in astronomy also. That's the notation. And the ground state of neutral hydrogen is split into two hyperfine lines. Okay, so there is a hyperfine splitting, and they are related to us through a spin flip transition. So you can roughly think that the spin of the electron flips. So this, the left hand side has a higher energy, the right hand side has a lower energy. These two are coupled through the magnetic moment, and this transition results in the emission of energy, which comes in the form of radiation at 1420 megahertz or wavelength 21 centimeters. So this hyperfine transition causes emission, causes radiation at 21 centimeters. And if the hydrogen is at a cosmological distance, it will be redshifted when it comes to us. And the wavelength at which we will observe it will be 21 into 1 plus z, where z is the redshift. And the frequency will be correspondingly reduced. So it will be 1420 megahertz divided by 1 plus z. Okay. So now I have introduced to some extent the two main players in my talk. One is the universe, which is expanding, which introduces this redshift. And the other is the hydrogen 21 centimeter line. Okay. Now you can ask the question, why are we so bothered with neutral hydrogen, atomic hydrogen? We don't see this in our Earth, for example, right? Well, if you look at the reason why we are concerned with this, has to do with our understanding of the constituents of the universe. If you look at our present understanding of the constituents of the universe, nearly 70% of it is in a form which is referred to as dark energy. You don't see it directly. It is dark. Okay. And it has certain properties which I will not go into in this talk, but we believe that 70% of the universe at present is filled with this mysterious substance, dark energy. And of the remaining 30%, nearly 26% is filled with another thing which we don't see directly, that is dark matter. Okay. None of these do we see directly. Of the remaining approximately 4% that is the baryons, okay, which we are familiar with, protons and neutrons. So only 4% of the present day universe is this familiar matter, which we see around us, kind of 4%. Hydrogen, that is protons and neutrons, okay. Of this baryons, 75% by weight is hydrogen and 25% helium. So in a nutshell, hydrogen is the most abundant known constituent of the universe at present. Okay, most abundant known constituent of the universe at present, which is why we are interested in hydrogen. It is there all over the universe. Okay. Now, so we are dealing with hydrogen, and we are dealing with the hyperfine states of hydrogen. So you have two states, one which is slightly excited relative to this particular one. And the difference, energy difference, corresponds to 1420 megahertz. So now the question is, what decides the number of atoms or the number density of atoms in this excited state of the hyperfine transition as against the ground state of the hyperfine transition? So using N1 to denote the number of atoms in the excited state of this hyperfine transition, and N0, the number density of atoms in the ground state of the hyperfine transition, you can express this in terms of this Boltzmann factor, where G1 and G0 are the degeneracies respectively of the excited and the ground state. And these have values 3 and 1 for neutral hydrogen in this case. And T star is this factor, the Planck constant frequency by kV, which has an extremely small value, 0.068 Kelvin. And Ts is the temperature, which in this case is what we refer to as the spin temperature. So the spin temperature is what decides the ratio of these two states. That is the spin temperature. So this is another important concept in this talk. Okay, that spin temperature, which is a way of quantifying the number density, the ratio of the hyperfine states to the ground states. And if the whole system is in thermal equilibrium, the spin temperature will be exactly the same as the gas temperature. Okay, the ambient temperature of the gas, hydrogen gas. Okay. Let me also quickly introduce another very important constituent of the universe, which also is important for our discussion, which is the cosmic microwave background radiation. So observations from Earth and from satellites, so basically satellite and Earth-based observations from the position of the Earth, they show that that we are receiving a radiation from all directions, which has a spectrum that is a black body at a temperature of 2.73 Kelvin. And this is the measured spectrum of that radiation. It is the most precise black body spectrum that has ever been measured. The error bars here have been enhanced, right, and has been enhanced quite a few times. I think it's 100 times for the plotting. Okay, or 20 times here, 20 times. So this is, so we are receiving, if you take a radio receiver and point it at some direction, you will, at any direction on the sky, you will receive a radiation, which is a black body radiation at a temperature 2.73 Kelvin. We believe that it peaks in the microwave. That is why it is called cosmic microwave background radiation. And we believe that this radiation is cosmological in origin, in the sense that this radiation fills the whole universe. Just like the matter which we talked about, which fills the entire, which we believe fills the entire universe. The entire universe is also filled with a temperature, with a radiation, black body radiation, whose temperature at present is 2.73 Kelvin. Okay, so this is a pictorial representation of that. I am the observer sitting here, and we are receiving this radiation from all directions, whose temperature now is 2.73 Kelvin. But if you go back in the past, that means if you go to higher redshifts, the frequency of this radiation would have been higher, the wavelengths would have been smaller, and the temperature of this radiation would also have been larger. So as you go to higher and higher redshift, as you go further and further away, this radiation which is coming to us, it would have had a higher temperature. And by the time you go to a redshift of 1000, the temperature of this radiation, so the redshift 1000 corresponds to a distance. I have drawn that here. It's a shell around us. By that time, the temperature of this radiation was sufficiently high to have ionized all the hydrogen which was there in the universe at that time. Okay. So the point is that this radiation, if you trace it back, which it is coming to us now from all directions, it has a black body spectrum with temperature 2.73 Kelvin. If you trace it back at a redshift of 1000, its temperature is 1000 times larger. And that is hot enough to have ionized the universe. Once the hydrogen in the universe is ionized, this radiation, the universe becomes opaque. So effectively, you're seeing this radiation from a shell which is coming to which is around us at a redshift of 1000. And this is what the radiation looks like. If you take out the 2.73 Kelvin part, a mean part, then these are the tiny fluctuations which you see in this radiation at this shell here, where it was in equilibrium with matter, roughly speaking. Okay. And this is the WMAP image of the fluctuations in the cosmic microwave background radiation. And effectively, you're seeing a shell here, a sphere here at a redshift of 1000. Okay, where you see these tiny fluctuations of the order of tens of microkelvin. So this radiation has a temperature 2.73 Kelvin with small fluctuations of the order of 10 microkelvin in different directions, which you are seeing here. So the bottom line is that the universe is filled with a radiation like this, which is coming to us from all directions. Okay. So now let us ask the question, what will we observe if we try to observe the 21 centimeter radiation from hydrogen? And in this picture, I have tried to depict what we will observe when we observe this 21 centimeter radiation from cosmological distances. Okay. So the radiation originates at 1420 megahertz. But suppose the hydrogen is at a redshift of 1. Okay. So if the hydrogen is at a redshift of 1, the frequency of the wavelength would have doubled, the frequency would have halved. So the hydrogen from a redshift of 1 will come to me at a frequency of 710 megahertz, right? And redshift 2 will come at 1/3 the frequency. So the higher the redshift, I will observe this radiation from hydrogen. So this is the universe. I'm looking out at the universe, different parts of the universe here. And I'm receiving hydrogen from different distances, the radiation from different distances. Okay, the 21 centimeter line from different distances. And by the time the radiation comes to me, it gets redshifted. The larger the redshift, the further the distance. So the hydrogen, which is very far away, I will observe at a very low frequency. The same line will get redshifted to a low frequency. Hydrogen, which is located at my position, I will observe at 1420. So if I can determine the frequency of the hydrogen line as I measure it here, I can actually tell the distance from where the hydrogen came. The line came, okay, the hydrogen where the radiation came. So I hope that this picture is clear. The lower frequency I observe at, if it is this 21 centimeter radiation, 1420 megahertz radiation, then it tells me that the hydrogen is further away. Okay. And at a redshift of 1000.
Quick question, Somnath.
Yes. Yeah.
What characterizes that I'm seeing the 21 centimeter line?
Yeah, that's a very difficult question to answer.
Okay.
But, suppose you are seeing it. Okay, so now I'm just addressing the question.
You see a spectrum and decide, right? But here you are just seeing.
Here you're not. Here, yeah. So here you really cannot say that what you see is 21 centimeter radiation. But suppose it were 21 centimeter radiation, this would happen.
Okay.
And this would what would happen. And beyond a redshift of 1000, the CMBR is hot enough to have ionized all the hydrogen. So you have a hot plasma. And in the hot plasma, the mean free path is extremely small due to Thomson scattering. So the photons here just keep on getting scattered. They cannot come to us. Okay, so this part of the universe, the photon doesn't come to us. It keeps on getting scattered. I have shown a picture here. I have shown a picture of a photon trajectory schematically. It will not come to me. It will get scattered. And then at a redshift of 1000, the universe becomes neutral. Once the universe is neutral, the photon is now free to propagate. And it will come to me straight through this neutral hydrogen. So when the universe is ionized, it is like an opaque medium. The photon just gets kicked around. And once the universe is neutral at a redshift of 1000, the photon comes straight to me like this. Okay. And the point is that it will come to me through this neutral hydrogen. And so there is a possibility that there will be some imprint of this hydrogen on this CMBR photons. And that is the main issue. Okay. You may think of it as the main issue. And this imprint will be at low frequencies. Okay. So what is it that is going to happen? You have the CMBR photons coming to us, and it is coming to this so it has the CMBR has a temperature of T gamma. It is coming to us through the hydrogen, and the hydrogen has these two states, hyperfine transition states, and the ratio of these two states is characterized by a spin temperature. So the photon is coming to us through this hydrogen. If the spin temperature is less than the CMB temperature, T gamma, then the hydrogen will be absorbed. Whereas if the spin temperature is more than the CMB temperature, the hydrogen will be seen in emission against the CMBR. Okay, that is the main thing. So I hope this is clear. So the spin temperature is what decides what will happen as the hydrogen, as the CMBR comes to us through the hydrogen. If the spin temperature and the CMB temperature are equal, then nothing will happen. It will just come through. There will be no signature of the hydrogen. Okay. So it is the spin temperature which is crucial, basically. Okay. So what is it that you measure? What you measure is something called the brightness temperature of the radiation coming to you. It effectively quantifies the amount of light in the Rayleigh-Jeans limit. And if it's a black body, it is exactly the same as the black body temperature, if it has a black body spectrum. And what you measure is the difference between the brightness temperature of this radiation and the CMB temperature, T gamma. So what you can measure is the brightness temperature fluctuations. You see, the brightness temperature will differ from direction and frequency, because the radiation can interact with the hydrogen, and the hydrogen can change the nature of the light. Okay, so if it emits, the brightness temperature will go up. You will have an excess. If it absorbs, the brightness temperature will come down relative to the background CMBR. And this is what you will see in the sky roughly. And it will be a function of frequency, because depending on where the hydrogen is located. Okay. And these fluctuations can be calculated analytically, and this is the prediction. I will not go into the details of this, but this prediction, this part is due to the fluctuations in the hydrogen density and the velocity of the hydrogen density, and this part is due to the fluctuations in the spin temperature of the hydrogen. And the bottom line is that there will be absorption, the brightness temperature will increase, and there will be an absorption, will decrease rather, there will be absorption if the spin temperature is less than the CMBR temperature, and you will see the hydrogen in emission if it will produce an emission feature if the spin temperature is greater than the CMBR temperature. Okay, and all these features will be seen at very low frequencies or very large wavelengths, right? Hydrogen 1420 megahertz. So it is in this part of the CMBR spectrum which is not included in this curve here at all. Okay, so this part of the spectrum falls in the regime of low frequency radio astronomy. So this is basically what at very low frequencies or large wavelengths. Okay, all these effects will occur over here in this small part of the spectrum.
Sorry, Somnath, one question.
Yes,
Can
please.
I ask now? Yeah, so this T gamma, that depends on where the photons were created, right?
That not created. So as the photon propagates, the T gamma keeps on changing.
Okay.
Okay, at the position of the hydrogen. So where it interacts with the hydrogen, it depends on the spin temperature at that point and the T gamma at that point.
Okay, and the TS is decided by what?
I have not got. Okay, so that is there are three processes.
Meaning what I am puzzled is that this N1 by N2, is that a observable or is that what you infer given TS?
There are three physical processes which decide it. I mean, but right. So those are, I mean, those people know. So there can be collisions between the hydrogen atoms, and the CMBR itself can stimulate this, or there is another mechanism called the Woodesen field effect, where the Lyman alpha transition can cause this to change. Okay, you don't observe it directly. There's no other independent observation.
Okay.
Okay.
Thank you.
But we know the physics of it is known. Okay. So now with this background, let me now try to explain to you what we believe is the evolution of the hydrogen. Okay. So how does the hydrogen evolve? So I told you that the hydrogen first became neutral at a redshift of 1000. Okay. Now, at a redshift of 1000, which is a large distance from us, gigaparsecs, okay, so what happens there? There are no stars or galaxies. There are no luminous sources. Okay, it is dark. The universe is absolutely dark. And you have this hydrogen. And the universe is expanding, so the hydrogen is cooling. Okay, that is all that you have in the universe from a redshift of 1000 till a redshift of around 30. There were no stars, no galaxies, nothing there. Okay. And here you can see the hydrogen in absorption against the CMBR. So let me explain this. So there are no luminous sources in hydrogen, And the hydrogen here basically traces the dark matter. So the dark matter has some fluctuations, a point which I will come to. And if you follow the spin temperature, and there is also this hydrogen gas, kinetic temperature of the hydrogen gas, and there is the CMBR. So this is where the question you were asking comes in, that how does what decides the spin temperature? So the physics of this is known. So in some regime, it will follow the gas, the gas temperature itself will follow the CMB temperature, but the gas cools faster than the CMBR. And for some part of the evolution, the spin temperature follows the gas temperature, but then it shifts over to the CMBR temperature. So this is basically the collision. And here it is the radiation which makes it follow the CMB temperature. But the point is that there is a range of redshifts here where the CMBR can be observed in hydrogen in absorption. We expect the CMBR to be observed in hydrogen. The redshift range is around 200 to 30. Okay, and this is called the dark ages, and this is the only, possibly the only probe of the dark ages of that part of the universe. Okay, so if you can observe the CMBR, the hydrogen in absorption against the CMBR, you can possibly observe the universe in this part, in this redshift range, between the redshift 30 to 200. Okay. Now, so the hydrogen is expanding, and there are these, then after a redshift of 30, something very interesting happens, and you have what is called the epoch of reionization, where the hydrogen can be seen in emission. Okay, so let me explain this now. So you see, I have already told you about the cosmic microwave background radiation, which we are seeing which comes to us from a redshift of around 1000, and it has tiny fluctuations. I also told you that. So this is a pictorial representation of that, tiny fluctuations, very small, 10 microkelvin. So the fluctuations are of the order of 10 to the power minus 5. Right, 273 and 10 microkelvin. But if you look at the universe around us, you will see that this picture here shows you the distribution of galaxies. Okay, it's a galaxy redshift survey. Each point here is a galaxy. You can see that the universe around us has got tremendous amount of structures. The galaxies are distributed, they seem to be distributed in this web-like structure, the cosmic web. And not only that, but each galaxy itself is a very large overdensity. So a point which I have not made, our model for the universe is that it is homogeneous and isotropic, quite smooth. Okay. So the question then arises, how do you get these fluctuations which you see here? Right. It doesn't appear to be very homogeneous, very smooth. There are all these fluctuations. So what we believe is true is that there were these tiny fluctuations in the universe when at a redshift of 1000, and these fluctuations grow by a process of gravitational instability. So where there is an overdensity, it attracts matter from elsewhere. Where there is an underdensity, the matter flows out, and you get these the observed large-scale structures of the universe. You get galaxies all by this process of gravitational instability. And the whole thing is dominated by the dark matter, which is the dominant the dynamical component of the universe over a large range of its evolution. Okay, so the fluctuations in the dark matter are what give rise to the observed structure of the universe at present. Okay. Further, we believe that this structure formation occurs in a hierarchical pattern. So you first form very small structures like this. These small structures merge to give you bigger structures, which again merge to give you bigger structures. So we have this hierarchical clustering going on. And that is how everything that we see, like our galaxy, was formed. Okay. So how does our galaxy form? You first have a dark matter halo forming, and then the baryons, the gas which you have, the hydrogen, it collapses within the halos. And once the dark matter halos form and you have gas collapsing, then you will form quasars, which are basically accreting black holes. You will form stars. And once these objects form, they will emit ultraviolet radiation at energies more than 13.6 electron volts. Once such radiation comes out from stars and quasars, this radiation will ionize the neutral hydrogen. You will get H2, which is ionized hydrogen. So you will see that slowly, once you have the first stars forming, the first quasars forming, they will emit radiation which will ionize the universe. And this ionized radiation from different galaxies will overlap. And we believe that the universe, there are observations which tell us that the universe is completely ionized by a redshift of 6. So somewhere between a redshift of 15 to 6, this whole process occurred. Okay, this is the process of reionization. So let me show you a video, simulation which we have done. A lot of people do this, so we have also done some simulations. So you see that there are these are the halos where the ionizing radiation, where the galaxies form, and they emit the ionizing radiation, and the hydrogen here on the left hand side is getting ionized. You're getting holes, and as more and more of these structures form, more and more galaxies form, and they emit more ultraviolet radiation. The whole universe is ionized by a redshift of 6. Okay. So this is the epoch of ionization. And here the hydrogen also gets heated by the radiation that comes out. And the hydrogen is seen in emission in this during this epoch of the universe, epoch of reionization. Okay. Now by a redshift of 6, all the diffuse hydrogen is ionized. So do you have a signal at redshifts below 6? Okay. Now at redshifts below 6, all the diffuse hydrogen is ionized, but you do have hydrogen, and they are in these clumps, small clumps, which are galaxies. Okay, basically. And the hydrogen is seen in absorption against quasars, even at high redshifts up to 6. So these are small pockets, basically, pockets of hydrogen, self-shielded pockets of hydrogen. And they are observed in absorption lines against quasars, and we know the density of this hydrogen. So basically at a redshift below 6, there are isolated pockets of hydrogen, most probably inside galaxies. And here also the radiation is in emission. So let me show you. So the galaxies are inside dark matter halos. So this is what the dark matter distribution looks like. This is what the halos look like. And this is what the neutral hydrogen is expected to look like. Okay, so we cannot make out the individual halos or the individual galaxies at high redshifts. What you will see is basically the diffuse radiation coming from the collection of all these clumps of hydrogen. This is called intensity mapping. And let me again show you a video where we have simulated what you expect to see. So you will see the structures in the universe. You will see the cosmic web, you will basically see a coarse grained distribution of how the galaxies are distributed. Okay.
Somnath, one more question.
Yes, please.
So since this is the dark matter.
So it is not the dark matter. This traces the dark matter.
Okay, so this is the visible matter.
This is what we expect the visible. The simulations have dark matter, but we identify the halos where the galaxies reside. And we use some prescription. One can do hydrodynamics also. Okay. But we use some prescription that given the galaxy mass, given the halo mass, we expect how much hydrogen we expect it to contain. We use that in the simulation.
And what initial condition do you use? Completely random?
Not completely. It is random. It's a Gaussian random field, but the power spectrum is given. Okay.
Okay. And the simulation leads to this filamentous wave kind of thing.
Right.
And these are the 3 different regimes, sort of, is it?
No. This is the entire dark matter, which you don't see. We believe that the bulk of the universe is dark matter during this epoch. The dark matter is what clusters. So this is the dark matter. Now inside the dark matter, you have clumps, which we call halos. Okay. And the galaxies reside in the halos. Okay. So you have to identify the clumps in this dark matter which are halos, and the gas resides in those halos. So the stars form in those halos, and this is what the hydrogen distribution is expected to look like. Okay.
Thank you.
So just a question.
Please.
Hi, Shanki here. So what happens if you have if the property of the dark matter is modified, in the sense if it starts, it will change drastically, right? So all these simulations have to be worried about, right? Okay. Okay. Thanks.
Yeah. So question is, what do we expect? What do we expect to see? So we will see the 21 centimeter brightness temperature fluctuations with frequency and angle on the sky. We will see something like this. Okay, it varies. So the brightness temperature will vary with frequency and angle in the sky. And the way we analyze it is that we do a Fourier transform and look at the Fourier modes and the mod square of the Fourier amplitudes divided by the volume. This is the power spectrum. And this is what we use to quantify the fluctuations in this 21 centimeter brightness temperature. Okay, roughly speaking, the power spectrum is basically the amplitude of the mode K. Okay, the value of the power spectrum is the value of the amplitude of the mode K. So we decompose the fluctuations into Fourier modes and use the amplitude of these Fourier modes to quantify the fluctuations in the brightness temperature. And this is the kind of power spectrum you expect to see during the epoch of reionization. The quantity I have plotted here is not exactly the power spectrum. It is the power spectrum with these factors k cube by 2 pi square. This is the brightness temperature fluctuation at a particular length scale. So this has a dimension of Kelvin, millikelvin square straight away.
So sorry, Sumran. So this is a Fourier transform of what? The density distribution
of the brightness temperature,
which is proportional to density.
In a way, yeah. One of the things it is proportional to is the density. There is a I had shown you an right in the beginning. I did not discuss it. So there is a velocity term. There is also a spin temperature fluctuation. 3 terms.
Okay.
But you may think of it roughly as the density.
Okay.
Okay, that's correct. Right. So this is the kind of, and the value which you expect to get is roughly around of the order of 10 millikelvin squared. Okay, 10 millikelvin squared. So of the order of few millikelvin is the brightness temperature fluctuation. It is a very small signal which we are trying to measure. Okay, and the power spectrum is something of great interest. So this is a picture of the dark matter power spectrum. It's a pretty old one, but it shows you all kinds of a variety of observations which have been used to measure the dark matter power spectrum at various length scales. And we are basically, you may say that we are trying to use 21 centimeter observations to also measure the power spectrum. Okay, now what is the advantage? Let me again highlight this. So you see there are observations of the fluctuations in the cosmic microwave background radiation, which probe the universe at a redshift of 1000. Right, these are the CMBR observations. And we have a very good observations of the universe at a redshift of 1000. And then there are galaxy surveys which probe the nearby universe. It is very difficult to carry out galaxy surveys at high redshifts because it is difficult to identify galaxies and then survey them over a huge volume over here. Now this redshifted 21 centimeter radiation has this good feature that it allows you to probe a large part of the universe. It allows you to probe this entire part of the universe depending at what frequency you do the observation. Okay, so it has the potential of allowing you to probe a huge part of the universe which is not probed by galaxy surveys directly, neither is it probed by the cosmic microwave background radiation. Okay, this is the right. So let me give you a mini summary. How much time do I have left, by the way?
So you have 5 minutes.
Okay, thanks. So let me give a mini summary. So the mini summary here is that that redshift 21 centimeter fluctuations, they are there, and you hope to see them with the frequency and angle in the sky, and they are unique probes of the dark age and also of the epoch of reionization and even the low redshift universe. And there are a variety of very interesting questions one can address. I have listed some of them here, like dark energy. What is the form of dark energy? You can measure the baryon acoustic oscillations, right? How the universe got ionized. You can even probe the inflationary scales. I mean, not directly the inflationary scales, but the imprint of the inflationary scales if you go to the dark ages. Okay, so a variety of things which can be done with such observations. Okay, and we started working on this nearly 2 decades ago, 2001. This was our first paper on this, We were motivated by the fact that the GMRT was coming up it had just started functioning at that time. And there are several observational efforts which have got, which are currently underway. So there is this LOFAR, then the MWA in Australia. This is in Netherlands. These are all in South Africa, most of them. SK is a future instrument which is India is participating in. So all of them hope to target the epoch of reionization amongst other things. Okay. Now let me just, so I'm going to just tell you briefly about certain observational things. So there is this tentative detection of a absorption profile centered at 78 megahertz, which corresponds to a redshift of around 17. This is a global signal. Okay, so they have this is averaged over the all sky, and they find a dip at 78 megahertz, which they believe is due to the absorption by neutral hydrogen against the CMBR. And this they believe, interpret as a signature of the first stars that formed. It is a tentative detection because still there are issues which are still unresolved. And this is not, I mean, not consistent with, not exactly consistent with theoretical predictions. So it is still a tentative detection, but it has ignited a lot of activity in this area. And this is an all sky observation, a global signal. Okay. What we are interested in is not the global signal, and we are interested in is the fluctuations in that. And I'm going to briefly mention two of the things which we are involved in. So first one, let me just tell you briefly that there is a radio telescope in Ooty, which is a parabolic reflector, 530 meters long and 30 meters wide. It operates at 326.5 megahertz. Okay. So it is like this, it's a parabolic reflector. It's basically a wire mesh, and you have electric dipoles over here, dipole antennas over here along the length of the parabola, which capture the radio signal. Okay. Now this is being converted into a interferometric array. So what you have now is small antennas. So the signal from small parts of this will be taken, and this whole thing will become a radio interferometric array, an array of small antennas like this. An array of small antennas like this basically works like the Young's double slit experiment. Any pair of antennas, it will measure, it will produce a sinusoidal pattern on the sky. So it will also measure a sinusoidal pattern. So you can basically directly measure the Fourier modes using such radio interferometric antennas. And this is a pictorial representation of the volume of space and the depth that such the OFA will be able to target in future observations. It is the work is still underway. So it's run by TIFR, NCRA, this telescope. And this is the part of the power spectrum which it can target, and these are the predictions for 1000 hours of observation. The baryon acoustic oscillation lie in this K range, but the sensitivity is not adequate to pick out those oscillations, but it can make a detection in 1000 hours of the power spectrum. And the detection of the signal is predicted in a few hundred hours of observation of 5 sigma detection. So this is still coming up in Ooty. And I'll just highlight some work which we did recently with the GMRT. The GMRT is not very well suited for this kind of measurements. There are too few antennas in the central square. But we have but anyway, we have developed an estimator for this the redshift at 21 centimeter signal, which we are trying out on the GMRT. We could make we could put some limits. The limits are not very, I mean, they're quite large, so they're not even close to the expected values, but it's a kind of proof of concept of our estimator. So there's what is the main constraint? It is a question that was asked right in the beginning of the talk. How do we know that what we are observing is the 21 centimeter line? I observe something at 150 megahertz. Right. How do I know that it is the 21 centimeter line? I don't know, because there are other sources in the sky also which emit at the same frequency. Right. So these are what we refer to as foregrounds. And our galaxy itself, we are observing everything, the whole universe through our galaxy. That looks like this. It's a large, it's a very powerful foreground. And then there are discrete point sources also on the sky. So separating the 21 centimeter signal from these foregrounds is a big challenge. And it is not that it is a hopeless case. There are methods, there are ideas which people have. The statistics of these things and the 21 centimeter signal are different. So their efforts are underway how to separate out the foregrounds from the 21 centimeter signal. So let me now conclude. So I have tried to tell you that there is this very interesting way of probing the universe through the redshifted 21 centimeter line. And I tried to give you a picture of the various stages of the evolution of hydrogen from where this radiation originates. So you have the dark ages, and that is the very high redshift universe, around 30 to 200. And the redshifted 21 centimeter line is possibly the only way you can observe this part of the evolution of the universe. But these observations are very difficult because the radiation is attenuated by the Earth's ionosphere. So there are talks of putting up an observatory on the moon and or putting up robotic telescopes on the moon, but maybe not in the near future, but in the distant future. So but this is the only way you can ever hope to probe the dark ages of the universe before any structures, visible structures, were formed. And then you have the first stars coming into the play, and the universe gets reionized subsequent to that. Very interesting physics going on over there, how the universe, the first galaxies formed in the universe, how the radiation from there ionized the whole universe. Once the universe is ionized, you have these small clumps of hydrogen, and the collective radiation from that can be measured. And you can measure a variety of things there. You can observe the structure formation taking place, galaxy formation, galaxy assembly. You can observe the cosmic web. And you can also observe the baryon acoustic oscillations and try to get a handle on the expansion history of the universe, and thereby try to get some handle on the dark energy. And I also tried to tell you a little bit about this upcoming telescope OFA, which will operate in at the low redshift part of the spectrum. And then I also mentioned briefly that foreground removal is the biggest challenge in this field. So I have finished my talk. Thank you very much.
Thank you, Somnath, for this wonderful talk. I think we have had enough discussion during the talk, but if there is a quick question, we can take it.
I just have a question about the last part.
Yeah.
So what is the amount of data you expect to get for all these foreground removal? How much is the data? Petabytes, terabytes? What is the data stuff here?
It depends. Yeah. So see, this work which we did with the GMRT, for example, it was a very small amount of data that we had. Okay. Because GMRT is a competitive telescope, you have to write a proposal and all that. So our limits are also very poor. But if, for example, OFA will be expected to generate a large amount of data, there are 204 antennas, in that when it comes up. Okay, so it's a pretty big amount. Even this UGMRT, upgraded GMRT, which we have now, so the GMRT has been upgraded, and if you observe in the upgraded GMRT for a few tens of hours, you are left with some terabytes of data, which you have to transport to your computer. So it's quite large. And with the bigger telescopes, it is even larger. LOFAR, right? GMRT has only 30 antennas, but telescopes with hundreds of antennas, it will be in petabytes, I think. Okay, it's a big challenge. Yeah.
Okay.
The data volume.
Okay. Yeah, that's it. Thanks.
Thanks.
Okay, thanks a lot, Somnath. So let me thank Somnath on behalf of everybody. And now we will move to the two students' talks. I think the first talk is by Semen Xavier and then by Mahesh Chandran. So we will have back-to-back two talks, each of 15 minutes. So after 12 minutes, I will give you a warning. Semen, can you share?
Yes. Is this fine?
Yeah, it's fine. Yeah, you can start.
Okay, I will just press. Is this
Archana, is the 15 minutes expected to include Q&A?
Yes.
Program is 15 minutes. Yeah.
Okay.
But I think since there are only 2 talks, it can go a little. There are only 2 talks in the session. There are not 3 talks. Usually 3 talks.
Okay, thanks. So can I start?
Yes.
Good evening all. I'm Semin Xavier. I'm going to present on an exact model for evaporating primordial black hole in cosmological spacetime, which is the work that I have done with Alan Sunny and Shankar Narayanan. In general relativity, we all heard about black holes. A static, spherically symmetric black hole in a vacuum spacetime is represented by Schwarzschild metric, which is represented by equation number 1, where g is the gravitational constant and c represents the velocity of light, and the mass of the black hole is represented by m. And interestingly, a Schwarzschild metric has an event horizon at r is equal to 2gm by c square, and also it has a singularity at origin. So, but when we consider quantum fluctuations around the black hole, then it emits thermal radiation. That is, we can associate a temperature as well as an entropy with the black hole. But when we analyze that the temperature of the black hole is inversely proportional to the mass of the black hole, while entropy is proportional to the area formed by the event horizon. So when we consider the radiation from the black hole, then its mass will get changed. So such a lycometry can be represented using Vaidyametry. That is, a evaporating black hole can be represented by a Vaidyametry as of in equation number 2, where the mass of the black hole is represented in terms of ingoing null coordinates b. From here onwards, I'll be using geometric units as like g equal to c equal to 1 for simplicity. But when we analyze the decay of Schwarzschild black hole, we will get the decay rate or the Schwarzschild black hole is inversely proportional to mass square, which is I have graphically represented in the figure. It should be noted that the y-axis is from 0 to -8. So when we analyze the figure, we see that when the mass of the black hole decreases, its decay rate is larger. It suggests that the smaller black holes would have been evaporated fastly. And when we consider it for the primordial black hole, that is the black holes which formed in the early universe, our results suggest that the black holes having mass less than 10 to the power 15 gram would have been evaporated out for the current epoch. And various observations also it suggests. In this figure, I have represented various constraints on the primordial black hole from various observations. It considers the mass range between 10 to the power 15 gram to around 10 to the power 50 grams. That is, the way observations also neglects the mass range less than 10 to the power 15 grams. So in my work, we would like to see how these analyses will change for a black hole which is surrounded by some cosmological fluid, for which I am considering the action of the form and equation number 4, where R is the Ricci scalar and L fluid represents a combination of non-interacting two fluids, that is particularly null dust and a massive dust. And I'm considering metric of the form in equation number 5, where the mass of the black hole, the m of eta, is a function of conformal time eta, and a is a conformal parameter, conformal factor, when in which eta naught is a constant. And we will get two exact solution in which I have represented a most physically relevant one by equation number 6, in which m of eta takes a particular form, as you can see, where eta decay is a constant which sets the decay rate for the black hole. So when we analyze the properties of this black hole, our cosmological black hole, we can see that as like in the Schwarzschild black hole, we have singularity at origin, and we consider m of eta is greater than 0, which implies that there is a upper bound for eta in terms of the constant eta decay. And we have an apparent horizon in our black hole solution. That is, it is the more general notion of event horizon in the case of a dynamical black hole. And interestingly, we can see that when eta tends to eta decay, m of eta will be a vanishing quantity, which represents Einstein de Sitter universe. And in our work, we have studied the properties of apparent horizon using Mishner-Sharp-Hernandez energy and Kodama vector as well as Kodama current. And also we have studied using Ricci and Riemannian invariance. It also suggests it has a singularity at r is equal to 0. So as you have seen that our black hole represent a evaporating black hole in a cosmological space-time, we can compare it with that of a Schwarzschild black hole. So as in the initial slides, I have represented how the decay rate for the Schwarzschild black hole varies. It is inversely proportional to mass square, from which we can get how the mass decays with the parameter tau. I have, as you can see from equation number 7, where tau is a dimensionless parameter. But in the case of our black hole, our cosmological black hole, we will have the mass varies with the tau as in equation number 8, where the m is calligraphic md represents the rescaled mass. Then from equation number 8, we will get how the decay rate for our black hole, which is represented by equation number 9. And for understanding, we have plotted them together. In the left panel, we have plotted the decay rate versus mass for Schwarzschild black hole, which is represented in the blue color, Schwarzschild black hole in the blue color, and the cosmological black hole by orange color, and how the mass decays with the dimensionless parameter tau is represented in the red panel. As mentioned in the previous slides, I have this. It should be noted that y-axis varies from 0 to -8. So first we will look at the figure in the left panel. We will see that when the mass of the black hole increases, the decay rate for the Schwarzschild black hole is decreasing. But when we see it for the cosmological black hole, we can see that when mass becomes larger, the decay rate is increasing. And when we analyze the mass decay with the parameter tau, we will see that initially, when the black hole has a larger mass, the cosmological black hole decays fastly. But as time progresses, then its mass decreasing. At the time, we can see that the decay rate for the Schwarzschild black hole overtakes the cosmological black hole. So once again, from the previous analysis on the figure, we have seen that the decay rate for the cosmological black hole and Schwarzschild black hole is much different. When the mass is large, cosmological black hole decays fastly, and initially when the evaporation starts, when the black hole has a larger mass, it decays fastly. We have seen that as mass decreases, the mass decay for cosmological black hole, the Schwarzschild black hole overtakes the cosmological black hole. So as from our analysis, we have seen that the decay rate of cosmological black hole as well as Schwarzschild black hole is much different. It put a different constraints on the primordial black hole. So hence we can say that it put a different mass constraint on a primordial black hole to consider it as a dark matter candidate. And currently we are working on it. So thank you. Hello.
Thank you, Samin. Any questions for Samin? We have 2 minutes.
So I have a question. You go to slide 11 where you mentioned solar mass black holes all of a sudden, which is
Yes.
much heavier than the scales that you've been talking about in previous slides. Right? So usually you were talking about 10 raised to minus 15 and so on. So can you explain this a little bit? Why are we suddenly talking? Do you expect solar mass black holes to evaporate, for example?
I mean to say that the larger masses. So here I represented in terms of here in the grams, but here I have represented in terms of solar masses. So I consider for the larger masses. That's what I mean to say.
Okay.
In this graph, you can see it's a larger masses. That's what I mean to say. Hello.
Okay.
Okay.
So I didn't quite catch the model that you used. What is the decay model?
Okay.
And the little first.
This one.
Before this. So how did you arrive at this solution?
We'll be considering as this model.
Model.
No. I think it's action 4. I think what Urjit is interested in is action 4.
Action. Yeah.
For the L fluid.
L fluid. Yes.
What is L fluid?
It's a combination of two non-interacting fluids. One is the null test, and another one is a massive.
So those
test.
you have not displayed.
No, I have not. Basically, it physically means they won't exert any pressure. So.
But what are the parameters that enter these, and how do they enter your eta 0 finally?
Basically it enters in basically at this choice. These choices we will give, it will be 0 for the pressure contribution will be 0 in the Einstein tensor.
What will be the energy density of those fluids? Let's say rho.
Rho.
Does that matter to your answer?
It has a matter contribution along the radial direction as well as in the null direction.
What is the magnitude compared to m?
Okay. I have not represented it specifically.
Okay, Urjit, just to m is the unknown parameter of this model, right? M is decided by the energy density of the fluid.
Okay.
The m is his unknown parameter, which is given by the energy density of the fluid.
Okay, we'll follow it up later. Okay.
Okay, so I think maybe we can move to the next speaker, Mahesh Chandran.
Yeah.
Mahesh,
Just a
you're
minute.
ready? Yeah.
Yes. Is it visible?
Yes. You can start, Mahesh.
Okay, sure. So welcome all. My talk here will be based on a work that was published last December, which focuses on how one can derive black hole thermodynamics from entanglement mechanics. So in order to give a brief introduction, let me start with the first law of black hole thermodynamics. So black holes, as we know, are fascinating objects that exert a very strong gravitational pull. But what we also know about black holes is that it can quite simply be described by just a handful of parameters, such as mass, charge, or angular momentum. So for very small perturbations to the mass, the resulting equation that we see here is, in fact, it's quite similar to what we recognize as the first law of thermodynamics. And this analogy requires this temperature to be related to the surface gravity and entropy to be related to the area of the horizon. So now in literature, there is also an integral form of this first law, and that is specified by Komar relation, which is given here in blue. So the Komar energy that is written over here on the left-hand side is basically a conserved charge at the black hole horizon. And you can consider it to be some sort of an effective mass, except that it does not only take into consideration mass of the black hole, but also other parameters that describe the space-time. So once you substitute those values and rearrange it, you can in fact obtain the SMAR formula, which is given on the right-hand side. As you can see, it seems to be an integral version of the first law, except on the left-hand side and on the right-hand side, you have absolute values of the parameters that describe the space-time. And from Hawking's calculations, what we arrive at is a final expression for entropy and temperature that is consistent with the analogy that we mentioned for the first law. And at the same time, we also see that these quantities are of quantum origin. In fact, the fluctuations that we considered here are basically quantum fluctuations. And the next question is to ask, what is the underlying microstructure that gives rise to black hole entropy, the quantities that we mentioned earlier? So here we run into another problem, which is basically labeled as the universality problem of black hole entropy. The problem suggests that there is an abundance of theories which gives rise to the area law behavior of entropy. So it is quite difficult to distinguish the merits and demerits of all these theories just on the basis of looking at black hole entropy. So in this talk, what we'll be doing is we'll take the entanglement approach towards calculating black hole entropy. And there are a couple of reasons why. So one reason is that entanglement itself is a fundamental feature of quantum mechanics. So any consistent theory of quantum gravity, any candidate should in principle reproduce these results in some limit. At the same time, the advantage of entropy, the advantage of entanglement over here, as we will see in this talk, is that it is not just capable of reproducing just black hole entropy, it is also capable of reproducing the first law. And that is something that we'll be looking into in this talk. So let me start with a simple system of a couple harmonic oscillator and see what entanglement really is and how we can quantify it. So here, basically, we have a system of two oscillators, X1 and X2, which is coupled together because of this term determined by a coupling strength of alpha. Now, to solve the system, we usually go to a normal coordinate system where we can decouple the Hamiltonian and write down the wave function. So in the ground state, this wave function is a Gaussian. Now, what happens is when we go back to the original physical coordinates of X1 and X2, we see that this wave function cannot be separated into functions of X1 and X2 anymore. Now, this leads to some interesting consequences. First is that the X1 and X2 oscillators are now highly correlated. And any measurements you perform on X1 that will, in fact, directly influence any measurement that you perform on X2. And therefore, you cannot describe one system without also describing the other system. And this idea is what is known as entanglement. So once this criterion is satisfied, the next question is how can we measure how entangled the system is? And for that, we introduce a standard measure, which is known as entanglement entropy. And in order to calculate this, what we do first is write down the reduced density matrix of the system given by ρ1, which is obtained by tracing out one of these oscillators. Here I have traced out the second oscillator from the density matrix. From the density matrix. And once you find out the reduced density matrix, you can solve for the eigenvalues and plug it into the expression for entropy and obtain a closed form expression. And it is especially easy to find out the expression for entropy in the case of coupled harmonic oscillator. I have plotted the behavior over here. So you can see that the entropy behavior is monotonic and it has two distinct limits. In one limit, this entropy seems to diverge. And then in the other limit, the entropy seems to be vanishing. So let us look at what these limits exactly are. So the limit in which the entropy diverges is basically the limit alpha going to infinity, or basically where this coupling between X1 and X2 is infinite, and therefore X1 and X2 are infinitely correlated. On the other hand, entropy vanishes in this limit, which corresponds to alpha equal to 0, where you can see that there is no coupling between X1 and X2, and therefore they are now basically independent, and there are no correlations between them. So having seen what this looks like in a simple system such as this, we will look at the model that we actually are interested in. So the model that we are interested in is a spherically symmetric spacetime with horizons, with one or more horizons. So typically we describe the line element in terms of radial coordinate system, where in terms of dr theta phi. But the problem with using that coordinate system is that exactly at the horizon, where f of r goes to 0, the entire metric diverges. So it is therefore presents us with a coordinate singularity. So what we can do to counter this is to go to a different coordinate system where this singularity is non-existent. So here we have chosen one such coordinate system known as a proper length coordinate system, where we are able to remove the this particular divergence at the horizon, but at the same time, we are also now at a disadvantage. We are also now at a disadvantage because we are only able to probe this region of the spacetime where f of r is positive. And therefore, that actually means that anything beyond the event horizon or anything outside the event horizon is the only region that we can access once we shift to the proper length coordinate system. Now, the next step is to introduce this field that occupies this spacetime. And this field is a massless scalar field whose action is given here. And the next procedure is to find out the Hamiltonian of the system. Basically, we want to simplify this problem such that we can simulate the entanglement mechanics for such systems. And and for that, there are two basic steps we follow. The first step is to perform a partial wave expansion. So this basically exploits the spherical symmetry of phi in order to reduce the dimensions of the problem from 3+1 to an effective 1+1 dimensional problem. On the other hand, we also perform lattice regularization, which in principle means that you are placing the degrees of freedom of the field on a lattice. And this lattice has a spacing A. And when you put A going to 0, you will get back the original field result that you're interested in. And the main reason why we are doing this is to, in fact, get rid of certain divergences, such as UV divergence of the system, which you will run into when you put A going to 0 limit. So once we perform this procedure, what we end up with is a Hamiltonian that has a form given in equation 4. So this might look complicated, but is actually quite simple. It is basically a chain of harmonic oscillators that are coupled together. Maybe in the next equation, this analogy is quite clear. I have rewritten the same Hamiltonian such that you can see the harmonic oscillator form. So once I have described the Hamiltonian, I want to define what is the entanglement mechanics of the field. So first of all, I want to calculate the first quantity known as the entanglement entropy, which we already discussed early on for the case of coupled harmonic oscillator. The only difference here is that we will be collecting contributions from all the angular momentum modes. And at the same time, instead of tracing out just one oscillator from the system, we will in principle be tracing out, say, n oscillators of the system. And this partition I've done here for the Hamiltonian basically captures that. This Hn corresponds to the degrees of freedom we are tracing out. And as you can see in this diagram, phi in and phi out represents the region being traced out and region remaining after tracing out respectively. The second quantity that we'll be introducing is entanglement energy, which is basically an average of the normal ordered Hamiltonian corresponding to the degrees of freedom that we are tracing out. So in order to get a physical understanding of what these quantities actually mean, let us go back to this diagram. So as you can see, we have bipartitioned the system into two. So the correlations that exist between phi in and phi out is what leads to a non-zero entanglement entropy when we calculate for phi in, when we calculate the change in the information content for phi in. At the same time, when we consider entanglement energy, we are basically looking at the disturbance in the vacuum energy of phi in the presence of this bipartition. So in both cases, if there were no correlations between phi in and phi out, both entropy and entanglement energy will lead to 0. Now, having established this, we will look at the simulations that we have carried out for a variety of spacetimes. Starting with the simplest one, Schwarzschild black hole, as Semin has already introduced in his talk. We only have a mass over here that describes the spacetime. And we will vary this mass of the black hole and see how entanglement entropy and energy behave. And from the results, we see that entropy follows an area law behavior. Entanglement energy follows a linear relation with respect to mass of the black hole. And this result might be unsurprising. And at the same time, we also see that the ratio of energy to entropy is in fact proportional to Hawking temperature. So keeping this in mind, let us move on to a slightly more complicated system where we have both a mass and charge in the system. and this is known as the Rice-Nordstrom black hole. So here we have two horizons, R minus and R plus, and here I have basically depicted the results for just one horizon, R plus. So what we observe here is that the entanglement entropy follows a similar area law relation, and entanglement energy, on the other hand, has this behavior of root of m square minus q square, which I will come to in a few minutes. So E by 2s, on the other hand, will give us the same relation to Hawking temperature of the event horizon as we observed for the case of Schwarzschild. Now, we went ahead and simulated the entanglement mechanics for a variety of spacetimes, which also includes a static patch of de Sitter, a Schwarzschild black hole in an anti-de Sitter spacetime, and a Schwarzschild black hole in a de Sitter spacetime. And these cases are considered mainly because of the fact that these spacetimes are asymptotically non-flat. So what we observed some very interesting results from these simulations. The first result is that the constants of proportionality that we can fix from the plots, that is basically CE and CS, are exactly the same for all the black holes considered. The second thing is that the quantities we simulated for black hole for entanglement mechanics have a one-to-one correspondence with the quantities that are associated with black hole thermodynamics. So basically, this Komar energy that you saw here is what was popping up here in the case of Rice-Nordstrom event horizon, and it will also pop up for all these other cases that we have considered. So the third result is that these quantities by themselves are also dependent on each other through this particular relation, which is reminiscent of what we introduced in the first slide as the Komar relation. But then what is even more interesting is that when we substitute the values of E and S over here in this relation, all the other constants cancel out in such a way that we get the Komar energy of black hole thermodynamics. And from here, it is quite straightforward to see how it can be rearranged to obtain the SMAR formula of black hole thermodynamics. So here I have obtained the results, written down the results for the other spacetimes I considered, and I've only included the event horizons here. And as it turns out, we have also calculated the entanglement mechanics for other types of horizons, such as cosmological horizons, and we were able to get a similar thermodynamic structure and SMAR formula for the same. So in order to conclude, let me say that what we observe here is a one-to-one correspondence between quantities ES and black hole thermodynamics quantities E, Komar, and SPH. So this is quite profound in the sense that our technique did not explicitly use Einstein's equations anywhere. But what we did is we basically used a test scalar field in a background spacetime to capture that spacetime's dynamical properties. Now, and also, as I mentioned earlier, we were able to observe or reproduce the Komar relation and SMAR formula exactly. And at the same time, this basically means that we were able to derive the integral form of the first law by just looking at entanglement. So this gives us a powerful tool in working out the results for complicated cases for which we already do not know how the thermodynamics works. And this gives us a handy technique to probe cases such as modified theories and higher dimensions. But of course, our technique has limitations in the sense that it does not apply to Kerr black holes yet, which are axisymmetric instead of spherically symmetric. And at the same time, any non-diagonal metric is also out of our reach at the moment. And it will be interesting to see how, if we can extend that, what the results will seem like. So here I would like to end the talk by thanking the organizers for giving me this opportunity, and thank you all for listening. Yeah. Are there any questions?
Thanks a lot, Mahesh. Any questions for Mahesh?
If nobody's asking, I can ask. So you had to use the coupled scalar and gravity equations or not to get the scalar?
No, I just used a test scalar field in a background spacetime. This is the only action I consider.
Okay, but the G mu nu is not black hole G mu nu?
Yeah, it is. It's a minimally coupled scalar field.
It is a minimally to Einstein gravity.
Yeah.
Because that G mu nu is a background solution of Einstein gravity.
Yes, yes.
Okay. Okay, thanks.
Okay.
Okay, thanks a lot, Mahesh and Semin. So I think let's thank everybody and we conclude this session 4 of ACG, and I hand over to the organizers. Thanks a lot.
And thanks to the speakers and chair, Professor Archana Pai and evaluator, Professor Arun Valero. And I would like to request everyone, if possible, to turn on your camera to take some pictures or screenshot. So yeah, I have taken some couple of pictures. So we will be having one hour break, and at 6:30 we will join again for lecture of Professor B.S. Satyaprakash, and we will be talking on unveiling the universe using the gravitational wave. So
Hello.
I am.
Yeah, Mukesh, since this presence in this group is so small, I suggest you try to take a group picture again after Satyaprakash's.
Yes, sir. Yes, sir.
Yeah, you can just request quickly people to turn on the camera and take time. That will be better.
Okay, sir. So yeah, so on this we are okay. So you can join again at 6:30. Thank you.
Oh.
Thank you.
Thank you.
Raghu, has he joined?
No, he hasn't joined. Should we call him?
Yeah, it would be better. He said 20 minutes in his email.
He did that, yeah. Do you want to call him, Shanki?
No. You can talk to him. It's okay.
Okay, so I'll try. So he has given this number.
That's a WhatsApp number, right?
I hope so. Yeah.
So that then 6:30 there won't be any delay.
Yeah. Let me call him then. Yeah.
Sure. Otherwise, if you want, I can do it also. It's better. Maybe I'll do it. I'll just do it.
Because you know him, right? So maybe it's better.
Yes, I will do it. Can you just repeat the number so that I will just, instead of searching my mail, I'll just add it.
Mukesh, can you type the number or like give? Mukesh, are you there?
Yes, I don't think so. Okay,
he's here. I'll send you on WhatsApp. I have
number.
Yes, sir. I'm just sending in the chat.
No, it's okay. No, otherwise I'll just.
No, don't send in the chat. No, I'll send you.
+1. What is it? You just repeat now instead of sending it.
Yeah. I'm just
type it. +1.
+1. 814.
Okay. 814 441 7448. No.
Right.
Okay, just.
Yes, sir.
Thanks. Okay.
Yes, sir.
I'll just do it. Just a minute. Huh?
Hello, Professor Satyaprakash.
Hello, how are you?
Hey.
Hello, Satya.
Hi, Shanki, how are you?
How are you? I'm fine. How are things with you?
Yeah, things are good.
You are now where? You are now in Europe or you're in
I came back. I came back to State College at the end of October.
Okay.
In fact, my son also joined us just last week.
Oh, okay. He's doing fine now. He's doing fine, much better.
He's okay. I mean, it takes a little while. I'm trying to connect also with another machine. So initially they might, I will just mute myself on this.
Sure. I understand. Okay.
Give me a second. Yeah. I just want to make sure that we have two connections in case one drops out.
All right. Do you hear any?
Good. Okay. I can.
This?
No echo. No echo. Satya.
Yeah.
Yeah. Very good.
Okay.
I think the previous one was better than this.
Oh, is that right? Okay, I can switch over to that. It's no problem. Give me a second. I will turn off the mic here. Turn it off.
Can you speak once more just to be sure?
So you think this is better?
Yeah, this is okay. I think it's fine.
Okay.
I think it's
all
okay.
right.
Okay. And then can you share the screen so that then we are sure that everything is okay?
I'm just changing to my laptop. The desktop will still be the one that will share the screen.
Sure.
Okay.
Yeah, good. Very good. Okay.
Let's play it a little and
sure. Yes.
It's yeah. I can also watch it another one. That's the reason why I do that. Okay.
Sure. Thanks.
I'm gonna go get myself a cup of coffee.
Sure. Yes. We have 10 minutes, right? We are still 10 minutes.
Yeah, 2 minutes. Okay. Fine. I'll stop.
Sure, no problem. We have 10 minutes. We have 10 minutes, Satya. So no issue.
All right. No problem. Thank you.
Thanks. Is there? No, no.
Okay, I'm back. So how are things in Mumbai? Are you in person teaching? How is it going? I'm not able to hear you. You are muted.
Yes, yeah, I'm teaching the first year. It's online. The first year has been shifted by 3 months actually. Usually it used to be in July, but now we are teaching. We started teaching in end of November.
So everything was closed until then?
No, it was not closed. Everything. No, but the thing is, the JEE entrance exam, JEE mains, JEE entrance, everything was shifted, right, because of the second wave.
Right.
So got shifted to September, October. So then all the exams got over, and then this thing. By the time by end of, so we started classes for the first years on in 1.5 weeks back.
Okay.
So yeah, so it's online only. So I don't think so now with this Omicron variant, we don't know whether we thought maybe for the second year and third year we will have in person, but I think maybe that is not going to happen.
What do you do with the labs? Those
labs, I don't know. I have not actually. That is going to be a bit of a problem. Yeah, I agree.
Yeah, that has always been the challenge. It's okay to do the theory courses online.
Sure.
But there is some kind of innovation that people are trying to do, but it's not easy. I think you can do some demonstrations. One person can go to the lab and set up the experiment.
Correct. That's what they're doing. Yes, that is what they're doing here. But I think that is not exactly the kind of stuff we want to do for the experiment. Yeah, I don't know. So the LIGO is on. The LIGO site is on.
They are proceeding with the so-called A+ installation. It's not clear what's going to happen with the new variant, but so far they have been trying to install the some of the new components. It's not clear how long they can go on. But the plan currently is to really restart as soon as end of next year.
Right.
That's the current plan.
That's end of next year.
I don't know whether I don't know whether that's going to happen or not. But yeah.
Okay. You can see Archana, Satya.
Hi Archana, how are you?
Hey, hi Satya, how are you?
I'm good. How are you?
I'm fine.
Yeah, so you're staying in different offices inside the house, right?
No, actually,
home office.
right now.
Home office,
yeah,
yes,
yeah,
that is what it is.
we are at home right now.
Yeah. Different home office.
Yeah. How are things?
Things are good. I haven't really been going to my office at all. I go once in a while, but we go out until the new variant came. We used to have at least a drink once in a week, just to chat and so on. But
right.
I think we even stopped that. From 2 weeks ago, we are not even having that. So it's really difficult. I think for students it might be much harder, especially because of loneliness and not being able to meet anyone and not being able, not talking to other people. It's really not good at all. So
no, that's true.
That is a challenge.
That's quite true. I mean, I think it's been quite a long, right? It's almost like 2 years. I mean, we are filling our campus is still not full. So I mean, there are batches. Like for example, I know our master's batch. They have not seen the campus, and they are already in their final semester. So it's it's a it's very it's quite bad.
That's right.
Yeah.
In Penn State, of course, it's in-person teaching. I'm not teaching this semester because I spent almost 3 months in the first 3 months of the semester in Barcelona. So I'm not teaching this semester, but next semester, I don't know what the plan is. Currently, we have to do in-person teaching. So we start in the first week of January.
Oh, okay. Oh, that is.
I see.
That is not very far. So
it's not very far. So I'm prepared for it. We'll see. I also had my booster. So
you had your booster also? Okay.
Yeah, as soon as I came back from
Barcelona,
I had my booster.
Sure. Okay. Okay. I think we are waiting for Urjit.
Okay.
Urjit is the chair. So.
Okay. Okay, I'm going to start sharing now.
Yeah.
Sure. Yeah.
1 second. I'm assuming the audience is mostly MSc and PhD students, correct?
Yeah, that's right. But yeah, and also some BTechs maybe.
Okay.
Yeah.
I see Urjit. Urjit?
Hi.
Hi, yes, Urjit. Yes, I think, Yes.
Yeah. Hi.
Hi, Urjit. How are you?
Hi, Satyaprakash. How are you?
Yeah, I'm good. Thank you.
Good to see you here.
Yeah, absolutely the same. Your video is still coming along. Yeah, there you are. Okay. Good to see you.
Remember me?
Of course. Somebody was mentioning you the other day. I just forgot the context.
Not Nitin, not Ashtek, not Abhay.
Abhay, of course, he did. I mean, I'm not a member of the. Oh, what happened here?
Yeah, we don't have your video, but I mean, your presentation is very much here. That's good. No, I've been teaching advanced GR course, and Abhay was nice to get in touch with me and shared some notes and stuff.
Okay. Yeah, he gave a wonderful seminar yesterday on quasi-local horizons.
I see.
Especially in the context of quantum version of it, and how it helps to resolve the so-called information paradox.
Really? Okay.
He would like to call it the twin paradox. It's really not a paradox. The information paradox. So,
wow,
although I'll briefly mention it, it's really not a paradox as far as he's concerned, and people who work on loop quantum gravity are concerned. It's really not a paradox. Anyway, we'll talk about that later.
Yeah, we'll talk later. Will be great to have more of that. Okay, so
you can start.
Yeah, what's happening here? Okay, great. So there are participants who gathered. So let me begin by introducing Professor Satyaprakash, who is our invited colloquium speaker, distinguished physicist here. And his name carries the name of the city, Bangalore, and he has had much to do with it. So it should be inspiration to all our students and young colleagues. He got his PhD from IISc Bangalore, and before that, master's from IIT Madras, and earlier, of course, Bangalore University. And currently, he is a named chair professor, Bert Elsbach Professor in the Department of Astronomy and Astrophysics, Physics and Astronomy at the Penn State University. And he is Associate Director of the Institute for Gravitation and Cosmos at Penn State, which incidentally has 3 sub-institutes. I was really amazed to see. One of them, of course, has Abhay Ashtekar in it, and Sir Roger Penrose, no less. Satyaprakash continues to be also affiliated with where he kind of made his mark, I think, in early days, well, between IUCAA and Cardiff. So he was a postdoc at IUCAA and at ICTP, and then briefly a faculty at IUCAA, and then he was at Cardiff for some time. And he continues to be a member of the School of Gravity Exploration, the Gravity Exploration Institute of that university. He's pioneer of the match filtering search algorithm, which has eventually led to the discovery of all the gravitational mergers that we are seeing now, and which has now become a bread and butter technique, but he was one of the pioneers. He is, among many other things, member of the LIGO Governing Council and on the IUPAP's roadmap for gravitational wave astronomy for the next 30-year horizon committee. And he also says conceptualization of the Einstein telescope that will look far deeper and into primordial black hole mergers. So I will not say more. I will let Professor Satyaprakash speak.
Thank you, Urjit, for that very generous introduction. I'm really very happy to be here to share some of the exciting discoveries that gravitational wave detectors have been making and the road ahead. What is it that we can expect in the coming years and decade in this new window, observational window of gravitational waves. So let me begin. This is going to be an elementary talk to give you an exposition of gravitational waves. So I apologize to experts who might be looking for something new. There will be something new, but at least the first part will not contain anything that they have not seen. So about 5 years ago, 6 years ago, there was a landmark discovery now. And that is related to the fact that until 2015, the only fundamental wave phenomena, a wave phenomena that's caused by fundamental forces that we could detect were electromagnetic waves. And this forms the basis of all classical astronomy as we know, right from gamma rays to all the way to radio waves, including optical, UV, infrared. This is forms the basis for all of the facts that we knew about the universe until 2015. But all of this changed in 2015, September 14th, when gravitational waves were discovered. They were predicted by Einstein roughly 100 years before, and they are the only other fundamental wave phenomena that we know of, that we are able to detect as well. And with that discovery, just as Galileo's optical telescope, gravitational wave observations will usher in a new era in astronomy, fundamental physics, and cosmology. And I would like to take you through this journey of what that is going to be like. So let's begin with the first discovery. These are gravitational waves observed on 14th of September 2015, and that is what is in the name. GW stands for gravitational waves. 15 is 2015, 09 is September, and 14.
I do not see the slide changing.
Oh, you don't see the slide changing? Oh, you're right. I don't know what happened there. Yeah, that's very okay.
Okay, yes.
Let me try again.
Okay.
No, I don't. Again, they don't seem to change for some reason. Why is that? Okay, maybe I will
use the down key or something like that.
No. It's changing for me. Just that this happens. I'm going to share the whole screen.
Okay.
And that way there shouldn't be any problem. Okay. Now you see these.
Yes.
I guess. Yeah.
The landmark discovery page. Yeah.
Yes. Okay. This is what I was talking about earlier. Let me just go through the slide without saying anything. So this is what I initially said about the discovery. So with this, I want to start with the first detection of gravitational waves. GW stands for gravitational waves. 15 is 2015, 09 is September, 14 is 14th of September. You will see this kind of nomenclature, and I just wanted to explain that that's what it stands for. So here are two black holes with their, in the background, there are stars from the galaxy where the merger occurred. As the two black holes go around each other, the light rays that pass nearby will get gravitationally deflected. As a result, when the two black holes go around, they not only emitting gravitational waves, but an observer that is close by might see that the stars are changing their positions. It's only an apparent thing because of gravitational lensing. So here is the actual animation that's taking place. I'm sorry, this is probably coming along very, very slowly. It's a very beautiful animation that was carried out by the SXS collaboration. But if you have a chance, I suggest you go online and look at it. But here, it's really not doing great justice. I know that the video does not come along very nicely. So the two black holes come together, they merge, and when they merge, they form a new black hole, and that new black hole will also emit gravitational waves, which is very characteristic of the mass and spin angular momentum of the final black hole. Now, this discovery was in 2015, but soon it was followed by another monumental discovery of the collision of two neutron stars, and that's called GW170817. So the highlights from the first discoveries were the following. So 150914 was the first time humankind ever saw detection of black hole binaries. Until then, we didn't know whether black hole binaries existed. We knew of black hole candidates. We never had direct evidence for a black hole either. So this was also the first evidence direct evidence for the existence of black holes as predicted by general relativity. We do not even today have 100% proof or even 99% proof that they are black holes, but the challenge in the coming years will be to make that more and more solid, that what we are seeing are indeed black holes. The masses of the black holes that we detected, about 29 solar mass and 36 solar mass, were far larger than expected. And this is a challenge to astrophysics, because astrophysical models predicted black hole masses to be between something like 5 to 15 solar masses. These were at least a factor of 2 larger, and it was a challenge, but nowadays there are many models that can incorporate masses as heavy as that. In the process of this merger, the system converted something like 3 solar masses into pure energy in gravitational waves. And that's really remarkable, because the initial mass was about 65 solar mass, but it converted 3 solar masses into pure waves in space-time. Together, the first 2 observing runs saw about 10 binary black holes in total, a population unlike anything that we know in astronomy. But I think an even bigger discovery was with GW170817, which was actually not a pair of black holes, but instead a pair of neutron stars. 2 neutron stars, masses about 1.5 times the mass of the sun, but the size of only about 10 to 15 kilometers. They came rushing towards each other in this binary system, collided, and in the process, not only emitted gravitational waves, but they emitted also electromagnetic radiation in the entire electromagnetic window, from radio waves all the way to gamma rays, and they were all detected. I'll say a bit more little later about this. This confirmed that the speed of gravitational waves is essentially the same, because you could see both light and gravitational waves, and the 2 were delayed by only 1.5, about 2 seconds, a little over 1.5 seconds. And that helped to rule out many cosmological models that were earlier invoked to explain what is called dark energy. We may have time to say a little bit more about that. Not only that, it turned out that this event happened to be a site where heavy elements like gold, platinum, and general lanthanides form. There is no way to form these heavy elements in sun. If you have gone through elementary nuclear physics course, you would know that beyond iron, in order to form elements, it's very difficult, and it has been a challenge to fundamental physics. How do you form these things? And people thought that maybe they form in the aftermath of supernovae, explosions of stars. But it turns out that binary neutron star collisions are even more efficient factories where these heavy elements can be cooked, as it were. Moreover, it turns out that this is a new tool for accurately measuring distances, and therefore it provides a new approach to precision cosmology. Not today, but in the coming years, when we are able to build better detectors, it will be an excellent tool for understanding cosmology. And finally, this discovery helped us understand the equation of state of ultra-dense nuclear matter, matter that has density even 2 times the density that you would see at the nucleus of heavy elements. I'll walk you through many of these things, but I want to go back, all the way back, and try to explain what gravitational waves are. But before that, a short description that this discovery in 2017 earned Nobel Prize for my colleagues Rainer Weiss, Kip Thorne, and Barry Barish. They were very instrumental in the construction and realization of gravitational wave detectors. But please believe me when I say the discovery is thanks to hundreds of graduate students and postdocs who not only helped build and commission the gravitational wave detector, but were instrumental in carrying out the data analysis. So the discovery, as acknowledged by my colleagues, Nobel laureates, is the result of really almost 1,000 scientists working together for several decades. So what are gravitational waves? So in Einstein's theory of gravity, space-time is curved and it is dynamical, not just curved, it's dynamical in the sense that it can not only warp due to the presence of matter, it's not a Minkowski space anymore, or the spatial part is not Euclidean anymore, it can be curved, but that curvature can change. Therefore, you can have a vibrating space-time curvature. And this vibration can travel out from the source, and it does, at the speed of light, and that's what we call gravitational waves. So gravitational waves are literally oscillations in the space-time itself or space-time curvature. So these were already, there was the indirect evidence of the existence of these gravitational waves when Hulse and Taylor discovered a pair of neutron stars going around each other. And what happens in this case is that we can very precisely time the orbit. Now, gravitational waves, if they are emitted, they are sucking out the energy from the system, making the orbit smaller and smaller, and therefore the orbital period, is shrinking, and this shrinkage, the decrease in period, is about 76 microseconds per year. It's because this is a dimensionless number, it's something like 10 to the minus 12 or 10 to the minus 13, but it can be measured because the orbit can be timed very, very precisely. And for this indirect evidence of the existence of gravitational waves, Hulse and Taylor were already awarded Nobel Prize. So the reason why LIGO discovery is important is because we are now able to directly observe gravitational waves. So gravitational waves, what do? They stretch and squeeze space-time, and they alter the rate at which clocks tick. And we can make use of this in order to make discoveries. Now, but that's not easy because space-time is very, very stiff. And here I have given you some idea of what the stiffness is of various things that we come across in life. Rubber, for instance, has an elastic modulus of 0.1 gigapascal. Wood is about 100 times stiffer. Steel, still higher stiffness. And diamond is one of the stiffest things that we know of. And it still has about 1200 gigapascal. That's already pretty stiff. However, space-time at frequencies that we observe them, these are audio frequencies, something like 100 hertz to a kilohertz. Space-time is 10 to the 24 gigapascal stiff. It's not really going to be easy to stretch and squeeze space-time by simply waving my hand. I'm not really doing much. I'm probably causing more heat than ripples in space-time. So what does it take to then make this? So I'm going to make a simple calculation to illustrate what can bend space-time by appreciable amounts. So here we go. This is the only equation I'm going to show in this talk, and these are Einstein's equations. On the left-hand side, it is a function of the metric and its derivative, so it represents space-time. So the left-hand side is the space-time, and the right-hand side is the stress energy tensor, so that is the matter part. And as John Wheeler famously said, the matter, which is the right-hand side, tells the space-time how to curve, so that's the left-hand side. But in turn, because of conservation of energy momentum tensor, it turns out the space-time actually tells matter how to curve, because it turns out that the divergence of this capital G alpha beta is 0, and therefore T alpha beta has to obey the same thing, and it gives you equations of motion. So matter tells space-time how to curve, and space-time tells matter how to move, the matter how to move. But the coupling constant is the important thing here, and it has the value 8 pi g upon c to the 4. Now, what is important is to take this 8 pi g over c to the 4 to the other side and write it as c to the 4 by 8 pi g, or c to the power of c to the 4 by g, and that has a quantitative measure of something like 10 to the 44 newtons. So it's some kind of a fundamental force, because it is constructed, this quantity, this force has constructed out of simply fundamental constants, speed of light and Newton's constant. And it has an enormously large value. It's nothing that we experience in life, but because it has units, it really does not have any, you don't have to think about it as being too large or too small, because if I use a unit, some 10 to the 15 newtons as my unit, then in that unit will be only 10 to the minus 6. So what does it mean? When can we experience a force like this? Under what circumstances can such a force be felt? So I'm going to consider the usual thing that we do, which is consider force on an orbiting body. So we know that if the orbital speed is v and the mass of the body is m, and its orbital radius is r, then the force is mv square upon r. Now, we know Kepler's law. If this force is caused by gravity, we can replace m by r by v square upon g. This is really, believe me, nothing but Kepler's law. So I'm just going to replace m upon r with v square upon g, and you get v to the 4 upon g. And I can do the usual trick of dividing and multiplying by c, and I get now c to the 4 upon g. Voila, that's the force that we had seen is the coupling constant in Einstein's equation, multiplied by v by c to the power of 4. Now, normally when, for instance, Earth is going around the sun, this v is about 10,000 the speed of light. So that's 10 to the minus 4, that v by c, and that is raised to the power of 4. So it's really the force experienced by Earth as it goes around sun is tiny. There's nothing. It's actually even smaller. I think I'm quoting the number for neutron star binary. So black holes in a binary can reach velocities that are close to the speed of light, and therefore they are the ones that can experience this force gf, and therefore they can alter the space-time in turn to the greatest extent. And it's really the binary black hole merger that can give you the greatest power or luminosity in gravitational waves. In fact, when a binary black hole merger takes place, the radiation that comes out can briefly outshine the entire universe in light. Okay, all of the light from all the stars is not enough to match the luminosity in gravitational waves from a binary black hole merger. Now, the reason why it is difficult to detect them is because gravitational interaction is very weak. So how can we detect gravitational waves in that case? Here's a diagram that shows you what gravitational waves do. So the green ring is a ring of particles, And as gravitational waves pass by, though that ring gets deformed into this ellipse in the first 1/4 of the period, back to that circle, and then to this ellipse orthogonal to the first configuration, back to the circle in one full gravitational wave cycle. That's if the gravitational waves are less polarized, and the name is derived from the shape of the ellipses. The two ellipses look like less. There is only one other polarization of gravitational waves, and they cause the pattern as shown on the right-hand diagram. The circle gets again deformed into an ellipse, but inclined by pi/4 relative to the first configuration. Pi/4 is important because in electromagnetic radiation, the oscillations, they are inclined by pi/2. That's a spin 1 field. But because this is a spin 2 field, it turns out the oscillations are separated by pi/4, and the full cycle takes them through the two ellipses. Now, if you remember, the effect of gravity is nothing but to cause tides. So this is nothing but a tidal effect of gravitational waves as they pass by. So the effect of gravitational waves is nothing but mimicking changing gravity. If you take a mass and then pull it farther and closer to another object, such as Earth and Moon, Moon can come closer or farther, and that causes tides, as we know. As it goes around, it's equivalent to making it go closer and farther. It's not the change in distance, but the fact that it is going around causes tides. And the effect of gravitational waves is similar. It causes tides, and this tidal force is what we are trying to detect. However, the problem is, even the most catastrophic collisions of black holes that we are talking about causes change in length compared to original length. That's what I call delta L upon L. Or L is the original length, and delta L is what is caused by a pair of black holes colliding at 1.3 billion light years, as it happened in the GW 150914, and that's only about 10 to the minus 21. Therefore, the change in length is 10 to the minus 18 if the separation between the two bodies is about 1 kilometer. So we are talking about measuring change in distance, which is 1/1000th the size of the atomic nucleus, not even the atom, atomic nucleus, which is already 10,000 times smaller than the size of the atom, and then 1,000 times smaller than that is what we are challenged here. LIGO was built precisely to make that measurement, and let me walk you through the detectors that currently exist. The LIGO stands for Laser Interferometer Gravitational Wave Observatory. In the US, there are 2 of them, and they are separated by something like 10 milliseconds in light travel time, 3,000 kilometers. They are operational now together with Virgo. I should not have used this slide. Virgo is also operational now. This is a slightly older one, and Geo 600, which is 600 meter, and CAGRA also began taking data recently. And of course, LIGO India is not planned anymore. It was approved just about a week after we made the first discovery announcement in February 2016. So here is an aerial picture of the LIGO Livingston Observatory. It's in the state of Louisiana in south, whereas the LIGO Hanford Observatory is in the north in the state of Washington, and these are 4-kilometer size detector. As you saw, even a kilometer size detector will only cause, will feel change in length of order 1/1000th the size of the atomic nucleus, but precision engineering is what finally allowed making such measurements possible. This is an aerial picture of Virgo detector at Kashina. This is about 3 kilometers. The reason why you need longer arms, as I said, is delta L. The change in length is proportional to L. Larger L that you make, the bigger will be the effect of gravitational waves. That's why you try to make them as large as possible. And in this case, these are kilometer-sized detectors. In addition to that, as I said, it's the effect of gravity and gravitational waves is similar. And therefore, cars passing by, the changing density of air close to the mirrors in these interferometric detectors can cause or can mimic a passing gravitational wave. So the Japanese scientists are building a detector underground in Kamioka mines, and this is called the Kagra Observatory. It is deep underground, and it's a 3-kilometer detector. But in addition to that, in order to stop the mirrors from vibrating due to non-zero temperature, they are cooling. They're cooling down to the initial aim was really at the level of Kelvin, 5 or 6 Kelvin. But I think the plans have changed in the recent time because it's much more difficult to do that. So, as I said, 1509-14 was our first discovery. Detection of these uses and also characterizing the signals uses pattern matching technique called match filtering. This is extremely well known in radar communication and sonar to detect submarines in underwater. They can not only locate where they are, but they can also look at the shapes by using sonar, and that's a similar technology that we use to detect these gravitational waves. But the thing is that we need to know exactly what is the shape that we are looking for. If you want, you need to match the waveform to the signal that might be present in the data. And it took several decades to work out what the numerical, what the waveforms are by using numerical relativity, because you cannot analytically solve Einstein's equations exactly, but there are approximate techniques and they have been used. Anyway, here is the anatomy of a binary black hole signal. So it's a, for all said and done, it's a very straightforward waveform. There are two black holes that are going around each other. When the orbital separation is large, the orbital frequency is small and the gravitational frequency is small. When the two black holes come closer towards each other, the orbital frequency is larger, and the gravitational waves are also larger. And in fact, they're just twice the orbital frequency. When the two black holes come together and merge, you cannot describe them anymore by using orbital orbits anymore. So you have an long adiabatic spiral and a short merger, which in the case of stellar mass black holes will take only a few milliseconds to merge. And then finally, the highly deformed black hole settles down. Initially, it is highly perturbed. It's what we would call a dynamical horizon. And that dynamical horizon, it settles down by getting rid of its deformity. And that is what we call the quasi-normal mode, or a ring down signal. Now, the important thing is that the shape of the signal, the duration for which it lasts, and the rate at which the frequency changes, all of this contains information about what are the masses of the system, where does it come from, how far is it located. But also, if you have a number of detectors that are available, you can triangulate the source on the sky, just as GPS is used in order to tell you where your car is located. We can use 3 or more detectors in order to localize where the signal is coming from. Anyway, so that's what was used. And we already talked about 1509-14. And I'm going to tell a little bit more about 1708-17, which is the first discovery of inspiring binary neutron stars. So in this case, not only was the gravitational wave identified, but its distance was measured to be about 38 megaparsec, plus or minus about 5 or 10 megaparsec, depending on the credible interval. And then it was localized to within 16 square degrees on the sky. That helped astronomers to point their telescopes in the right direction. As you know, telescopes don't have all sky sensitivity, whereas gravitational wave detectors do. And when astronomers looked in that direction, they were able to detect a source that was initially very bright. Remember, this was discovered on 1708-17, August 17th of 2017. On August 22nd, it looked like this. August 22nd, and 4 days later, fainter. Another 2 days later, even fainter. And after that, at least in infrared, it was completely gone. It's still visible in radio very faintly. At least the last time I spoke to my colleagues in radio observers, but it's slowly fading away completely in all of the electromagnetic spectrum. But because we were able to measure the distance from gravitational wave observations to this object and redshift from electromagnetic observations, these are the two ingredients that go into measuring the rate at which the universe is expanding. And that gives us the so-called the Hubble parameter. And what is shown here in this orange curve is the probability distribution of the measurement of Hubble constant. It's not super well measured. Maybe it is somewhere between 60 km/s per megaparsec, all the way to maybe 110 km/s per megaparsec. The measurements by the Planck mission is shown in kind of red, and by using supernovae as indicators of distance is shown in blue. The thing is, the Planck measurement and the so-called Shoes measurement are in disagreement with each other. And that disagreement is already close to 5 sigma.
Excuse me, the dark bands represent the 2 sigma or 3 sigma.
Yeah, 50. No, the first one is 50%.
Mm-hmm.
Yeah, and the other one is I think 2 sigma.
Okay. Okay.
Yeah.
Thank you.
Yeah, and the total is really something like 4.5 sigma, different from center to center. So this is a tension in cosmology. Why this discrepancy occurs from different measurements? We will have an opportunity to discuss that anymore, some more, a little bit more. We not only observed gravitational waves from this, but the gamma ray detectors, in particular the Fermi Gamma Ray Observatory and also the Integral Observatory, measured gamma rays from this. So here is an animation. So as you oh, there it is. Okay, sorry, I was too quick to put it off. So here is the gravitational wave shown in the time frequency diagram. Initially, this gamma ray observatory, it is just noise. Here is the merger. This is frequency, which is increasing as a function of time. And after the two neutron stars merge, about 2 seconds later, more precisely 1.7 seconds, there is an excess in the gamma ray observatory, and that's really what one got very excited about, because this indicated that after nearly 4 decades, the puzzle as to what so-called short gamma ray bursts that last for less than 2 seconds are originating from, and it finally resolved decades-old problem as to origin of gamma ray bursts. Not only that, the fireball that was created due to the merger was because of the fact that there were lots of neutrons available, which are heavy, extremely energetic neutrons. These neutrons then can collide with each other, producing heavier and heavier nuclei, and those nuclei can then decay, radioactively decay, and produce this fireball. And that fireball is normally called a kilonova. It is 10 to the 3 times more brighter than an ordinary nova. And this was observed. This kilonova was observed. And we now know that the merging neutron stars are responsible for producing these lanthanides, to which gold and platinum and other elements belong, and very nicely explains the abundance of heavy elements in the solar neighborhood and extrasolar neighborhood. There is no other way to produce these apart from exploding stars, but Big Bang and early universe couldn't have produced these, or even stars cannot cook these elements. So that's one of the biggest discoveries as well. But in addition to that, these binary neutron star collisions will help resolve one of the biggest puzzles in fundamental physics. You know, at the center of atomic nuclei, the density is extremely large, about 2 times 10 to the 17 kilograms per meter cube. That's a massive density. But at centers of neutron stars, especially when 2 neutron stars merge, as shown in this simulation on the left-hand side, the densities can grow 2 times larger than the densities at atomic nuclei. Now, we don't really know what happens to matter at such densities. We know that at ordinary densities, neutrons are composed of quarks, an up quark, a down quark, and a strange quark. An up quark and a down quark, 2 down quarks in the case of neutron stars, and 1 up quark, whereas in the case of protons, it is 2 up quarks and 1 down quark. Matter is mostly neutral, so at the centers of neutron stars, it's mostly neutrons, but they exist, whether they exist in the form of confined quarks or deconfined quarks, we do not know. But this is something that can be explored from looking at the mass radius relationship in neutron stars. Currently, all these curves that you see are different models as to what the equation of state is. And there are literally millions of these models that are currently available. There are some examples given here. If it consists of strange quark at the core, then it would be some, one type of mass radiation relationship. If it is nucleonic matter, there's another kind of relationship. It is nucleonic plus exotic matter, a third kind of relationship, and so on. We don't know which one of these is really what is contained, especially when you have a hypermassive neutron star that is formed when 2 light neutron stars merge. Hopefully, we can do this measurement, but current measurement of the radius inferred from binary neutron star mergers is that the radius is between 9 to 12 or 13 kilometers for the 2 neutron stars that we have discovered. And it depends on what kind of technique that you use. But it turns out that the data favors what are called softer equations of state over stiffer equations of state. But in order to really make an impact in this field, we need to measure neutron star radii to something like 100 meters over a kilometer, or 10 kilometers or so, 1%, at the level of 1%. We are nowhere close to that with the current observations, and hopefully future observations can do that. So in addition to those 2 very special events, there have been other exceptional events that LIGO has discovered. And here is a sample of them. And I probably am running out of time. How much time do I have? Another 5-10 minutes, I guess?
No, yeah, easily. Yes.
Yeah. So these are the various special events that have been discovered. They all have this telephone number, GW, followed by a number, and that number is getting longer for reasons that I won't go into. But I will touch upon a few of them. GW 190412 was a signal that was observed in all the 3 detectors, LIGO Hanford, LIGO Livingston, and Virgo. That's what HLV stands for, with signal to noise ratios about 8.6, 15.6, and 3.7. This is the first binary black hole with definitively unequal masses. Most of the systems that all the systems that we discovered before this event were kind of equal masses. In this case, the mass ratio M2 upon M1 is about 1/3 or so. So it is significant. There is a significant.
Sorry, we seem to have lost the voice.
Satya, I think you muted yourself. Satya, you muted yourself.
No. I got disconnected from the one where I had my microphone. Hopefully you can hear me.
Yeah.
It's not so good, but okay. Anyway, let's quickly go through some of the other events. 1904-25 was our second binary neutron star merger. There was no electromagnetic afterglow detected in this case because the neutron star merger took place a little farther, and also we couldn't localize this well enough. It must have produced a black hole, and that might have resulted in a black hole in what is called the lower mass cap. The heaviest neutron stars might be as heavy as something like 2.5 solar masses, and the lightest black holes might be produced by stellar evolution might be about 5 solar masses. So there might be black holes that are produced by mergers, neutron star mergers, that are populating the so-called mass cap, and this system might have produced one such mass cap black hole. The next in my list is 1908-14. This is one of my most favorite systems. It consists of a 2.6 solar mass black hole, which is almost already in the so-called mass cap, merging with 23.2 solar mass black hole. It turns out that the secondary, that is the lighter object here, we don't know really whether it's a black hole or a neutron star. So it's a mystery. It could be one of those, or it could be something else. We don't know. And we don't really know the origin of this. Did it really form from a previous merger of two neutron stars? Because the problem is, how will it find another black hole to merge with? So it poses a real challenge to astronomers as to how one can produce a system like this, the lighter companion of this. Moreover, the spin of the heavy black hole here is almost close to 0, and it is 23 solar masses. And how could it, could nature produce a black hole that's almost perfectly Schwarzschild is not clear. Moreover, in this system, as in 1904-12, we discovered not only the quadrupole radiation, but also higher harmonics. And in this particular case, the evidence for octupole radiation is really very solid. The final in my list of special events is GW 1905-21. In this case, the original black holes, the progenitor black holes, had 85 and 66 solar masses, and they combined together and produced a 142 solar mass object. If you are careful and you're following the talk, you will see that 85 plus 66 is 151 solar masses. But I'm saying, did I make a mistake? 142 solar masses? No, the answer is that something like 10 solar mass, 9 solar mass of energy was converted into gravitational waves in this case. So this binary black holes and binary neutron stars are wonderful factories of converting energy into waves. This doesn't happen so efficiently in the case of electromagnetic interaction, but gravitational wave interaction can convert mass into energy without any problem, and a very efficient conversion. Anyway, so this is also a mystery object because astronomers, until the discovery of this, thought that you really cannot produce a black hole by stellar processes, masses larger than about 50 solar masses. And this comes from really fundamental physics. And if there are black holes that are produced by stellar processes in excess of 50 solar masses, that could have implications in fundamental physics itself, namely nuclear interactions. It produces what are called pair instability supernova if the masses are very large, and leads to explosion of stars and never allows the formation of very heavy stars. So this is another puzzling object. It's possible that the heavier black hole here is produced by previous mergers, but the probability of such mergers happening is 1 in 100 or 1 in 1,000. And we had until then discovered only about 50 objects, and something like this happening is really pretty puzzling to astronomy. But astronomers always come up with some models. Okay, in all, we now have the third gravitational wave catalog. Depending on how you count, this has about 90 binary coincidences. In my next slide, when you add them all up, you will not see 90, and that's because I have chosen to show only those that are really truly, we believe, are gravitational waves. So the population properties based on 76 events with what is called false alarm rate of less than 1 per year is what we have here. So there are 76 confident binary black hole events. 2 of them are definitely binary neutron stars. 2 of them are neutron star black hole events, and 1 of them is a candidate, most likely. It's probably not a neutron star black hole. It's most likely a false event. Nevertheless, we now have measured not only black hole binary events, but we know the rate at which the merger is happening in the local universe. It may be something like 20 to 40 or 50 per year per gigaparsec cube. Neutron star binaries are probably merging at a higher rate, something like 300, but the rate is uncertain. It could be anywhere between 13 to 1900 per year per gigaparsec cube. And neutron star black hole mergers might be somewhere in between those two. I won't go into the details of what that is, but I want to talk a little bit about what the future holds before concluding. So the LIGO detectors are currently down, and they are expected to come back, contrary to what this graph shows, maybe by the end of next year, 2022 December. And when they come back, their reach will increase from something like 150 megaparsec to 180 megaparsec. That's for the LIGO observatories. The Virgo observatory, it might be more like 125 megaparsec. Kagra, I don't think they will reach 140 megaparsec. It's a wishful thinking, and I don't think they will reach even 40 megaparsec. They did not. Their reach when they were taking data in 2020 was more like 1 megaparsec. But we are not stopping there. There are going to be improvements beyond this to what is called A+, advanced plus sensitivity. And beyond that, we are also thinking about building detectors that are 10 times bigger than current detectors. And there are 2 such projects that are currently being thought about. This is the Cosmic Explorer plan. We have completed what is called the Horizon Study of Cosmic Explorer. So I'll talk a little bit more about these future detectors. So this is the plan for gravitational wave observatories in the future. What you have heard so far, the LIGO Virgo detection of black holes and neutron stars, the frequency of observation is what is called audio frequency. I refer to this as the high frequency regime. These are like the gamma rays of electromagnetism, but the larger the system, the lower the frequencies. So there is a plan to build detectors in the mid frequency called MAGIS or ION. These are atomic interferometers, and DESIGO, which is a laser interferometer in space. That's a Japanese detector. And then if you go still lower in frequencies, about millihertz frequencies. You have laser interferometer space antenna, or LISA. A picture of that is shown on the top left. And that might come in mid-2013s. And Chinese are also planning to put maybe 1 or 2 detectors in space, and one of them is called Tianping, and that might also come around the same time. If you go to even lower frequencies, something like nanohertz, where in the lifetime of an astronomer, one might see only 1 gravitational wave cycle from a source. These are nanohertz gravitational waves, ultra low frequency, and pulsars are used in order to detect them. What I'm going to tell a little bit more are about Cosmic Explorer on the top right, and Einstein telescope in the bottom right. So the reason why we need to build these detectors is because there are several puzzles in physics. There is the so-called black hole information paradox, which is really not a paradox, but if it is true, as some physicists would like to believe, then we should be able to resolve it by looking at the structure of black holes. Black hole singularity is a real problem, no matter how you look at it. Maybe quantum gravity will offer a solution to the black hole singularity, but there are today no viable theories of quantum gravity. And all quantum gravity theories predict violation of general relativity one way or the other. Therefore, finding out what those violations are important, and gravitational wave observations might help do that. Furthermore, today we see an accelerated expansion of the universe in the late stages of the history of the universe. And this acceleration could be caused either by a cosmological constant, which is a vacuum energy, unchanging, and it has problems in particle physics as to its origin. But more importantly, whether or not it is a constant is still a puzzle, and that could be resolved by future detectors. We don't know the nature of dark energy in the sense that whether it's truly a cosmological constant, and we don't know what dark energy is, dark matter is, and what is its origin. Does it consist of primordial black holes, or is it bosonic or axionic particles? These are puzzles that we don't know. And we also mentioned to you about the Hubble tension. The Hubble tension comes from the fact that the Planck, which can not only measure dark energy and dark matter, but also it can measure the Hubble constant, and the value measured by Hubble, Planck is indicated here, which is about 67.66 plus minus 0.42, one of the most precisely measured ones. LIGO and Virgo, as you can see, has a lot of error bars today, but the Planck measurement is really in sharp contrast with those concluded from supernovae, and that's really more like 73 plus minus 1.74. But with future gravitational wave observatories, we might be able to shrink this error bar down to 1%. And whether it goes in the direction of Planck or it goes in the direction of the Shoes measurement is something that we need to see. Finally, almost every galaxy that we see today, this is the Milky Way seen from the Mauna Kea in Hawaii. And if you look at the center of Milky Way, it seems to harbor a supermassive black hole. In this particular case, it's about 4 million solar masses. But 4 million, how did it arise? As I said, we can't really form stellar mass black holes from stellar processes more than about 50 solar masses. So did these black holes form by other processes in the early universe? Or is it repeated mergers of small black holes, and a hierarchical growth is something that we don't understand? And hopefully future gravitational wave detectors like Cosmic Explorer and Einstein telescope might be able to resolve. What I've shown here on the left, two graphs, are really the sensitivity and the distance reach. But I think the right-hand donut plot is more impressive. What that shows, we imagine we are at the center of this donut. As you go outwards, you see more and more stars and black holes and neutron star mergers and black hole mergers. So the current sensitivity is shown in this light blue curve. And as you can see, for binary neutron stars, really we're not sensitive to many of them. For binary black holes, yes, we are sensitive. That's the third observing run sensitivity. And we discovered roughly totally 90 binary black holes. Not quite, but about that. With future improvements, we will begin to see a slightly larger number of binary neutron stars, maybe with this dark blue curve and orange curve. These are the upgrades of LIGO. However, this is nowhere close to observing the full population of black holes, which exist out to redshift of something like 10. And it's really with third generation detectors, we are able to reach that distance. But with binary black holes, we will not only cover the entire universe, but even beyond, detecting things at redshifts of something like 100, where stellar processes could not have produced these systems, but maybe there are other mechanisms, like primordial black holes. So the future looks extremely exciting. Also, discovering phase transitions in the early universe, because of lack of time, I won't go into this. But it's really fantastic opportunity going forward. So I want to just not only mention the fundamental physics opportunities here that can help us explore black hole horizons, tests of general relativity, probing dark matter, and so on. But I want to tell the younger colleagues here that gravitational wave astronomy is a frontier subject in physics and also engineering. We use quantum sensors and quantum optics to make these detectors. The precision engineering required in order to make these detectors work. And we use very sophisticated techniques to make detections and inferences. The future of gravitational wave astronomy is truly bright. With that, let me finish, and thank you very much for giving me this opportunity to share this exciting field with you all today. Thank you.
Okay, so thanks a lot. Let me clap on behalf of everyone. Are there any questions? You can please raise your hand or unmute yourself. Yeah.
Can I ask? Yeah, Satya, thanks for the exciting talk. So I want to know one thing. So when you say this, that it can go up to the Cosmic Explorer and Einstein telescope can go up to redshift of 100. So are you this is also for 30 solar mass? That's what I'm confused. So how are you going to get this 30 solar mass at redshift of 100? In the sense, this cannot be astrophysical, right? They have to be cosmological.
Yeah, if you are talking about beyond redshift of something like 50, they are probably not astronomical binaries. They are primordial black holes that might have produced. The building these detectors naturally gives you that range, but in order to the goal is to really make the detector more sensitive, so that for nearby sources you can have greater signal to noise ratio. That's the way you're going to measure all these, make all these tests of general relativity, measure neutron star equation of state, and so on. But as an additional thing, you really are able to explore the entire universe for binary black holes. This, by the way, is unprecedented in astronomy. In astronomy, the progress has been something like a factor of 2 every 40 years. So to be where gravitational waves will be, it took about 200, 300 years in classical astronomy. And that we can do with gravitational wave astronomy in a matter of just 30, 40 years because of the way gravitational wave detectors work. It's really unprecedented, there's no doubt.
Just a quick question. In this donut plot, This is the anticipated merger rates, right? How are they estimated?
That's correct. That's correct. So we know what is the local rate, and then you assume a certain star formation history, and that the mergers will be proportional to star formation.
Okay.
Almost everything beyond redshift of even 1 is really something that is extrapolated from what astronomers see. And it's from gravitational wave observations are required in order to learn what the universe is composed of beyond redshift of something like 2 or 3. We don't really know. So this is the expectation, and therefore gravitational wave observations are really needed to learn what's the composition of the universe beyond those redshifts. You're right.
Okay. Any other questions, please, from the audience?
Satya, I have a question.
Yes.
Hello, am I audible?
Yes.
Yeah.
Hi, Satya. It was very nice talk. I have question regarding this different detectors which you showed. So this mid-frequency detector. So this, can you tell us more about this MAGIS and ion? I mean, what is the status of this, and is it?
So the atomic interferometers today are at the same stage as interferometers were, the laser interferometers were about 50 years ago. So they have a lot of technology development. The only reason for putting them there is because they target this mid frequency between 1/10 of a hertz and about 10 hertz. And they are similar to DECIGO in that sense. DECIGO, which stands for Dechi-Hertz Gravitational Wave Observatory, is a Japanese concept, as you know. I'm just mentioning it for the sake of the others in the audience. So that is, there is a Pathfinder in Japan that is targeting that. I don't think it has been funded yet. They were hoping to get funds, but that didn't happen. But if that comes, that might be at the same time as Cosmic Explorer, 2040s also. But the atomic interferometers, I don't see them reaching astronomical sensitivities any earlier than the next 30 years. But they are required in order to make progress in the field. Other ways of detecting things.
Yes, so that
okay, fine. So basically, this DECIGO, I mean, we expect if everything works fine, then that would come in 40s, and something like that. And LISA should come before that, right?
LISA would be more like 2034. That's the current expectation, but we'll see. Yeah.
Okay, thanks.
Good. So there's good news for all the young people in the audience because it's within their horizon, their light cone. Any other questions from?
Can I ask a more kind of a basic?
Please, yes, more important, yes.
Thank you very much for the very nice talk. So my question is that you mentioned about the detection of these extreme events through gravitational waves, and are there any? Could we have observed this through other means if we didn't have gravitational wave observatory? I mean, you already mentioned this Fermi, where you observed this gamma ray detection coincides with the gravitational wave. So is there anything that makes gravitational wave detection in unique way, so that the other methods will not work?
Yeah, the Fermi gamma ray observatory cannot localize binary neutron stars very well. In fact, the sky localization provided by gravitational waves was crucial for other electromagnetic telescopes to point in the right direction. But more than that, I think the information that you can extract from gravitational wave observations is complementary to the one that comes from GRBs. In the case of gravitational wave observations, we can measure the distance. You cannot do that with GRBs. We can measure the masses of the companion stars. Therefore, we can do a population study of these objects. We can measure the equation of state of neutron stars. And there are many other applications from gravitational waves. I gave you about 2 or 3, but these are complementary. And more critically, the distance measurement helps you a new tool for precision cosmology. Today, it's not precision cosmology. This is just the very first measurement, but in future, that should be possible. Electromagnetic telescopes cannot really locate these things in the sky because they're not all sky. Things like LSST might be able to do it, but they are only surveying a part of the sky maybe for about few minutes every night, because they have to survey the entire sky many times. So the only way to say, not only will we be able to tell you where in the thing it occurred, but it might even be possible to tell this in advance. With these future detectors, you can tell 5 to 10 minutes in advance, hey, there is going to be a merger there in 5 minutes. Point your telescopes. The telescopes currently observe them something like a few hours after the event occurred. Whereas with future detectors, we will be able to issue advance warning. There are many advantages. I'm happy to discuss more if you're interested.
Great.
Thank you.
Yeah.
Yes.
Satya, I have one more question. So you talked about the low frequency. So there are also efforts, I believe, the high frequency beyond 10,000.
True. Yes.
So there are also advantages, right? Or what is your take on them?
No, it becomes harder and harder as you make, in order to detect things at lower frequencies, you have to fundamentally make your detectors smaller within quotes, and therefore the sensitivity is required is really not so great. I have myself computed some numbers as to what kind of, for instance, stochastic backgrounds might be produced. The problem is we don't have, if you want to talk about binary systems, we need binaries with even smaller masses. And nature doesn't know how to produce, black holes less than about 5 solar masses, maybe 3 solar masses. They might have come from primordial black holes, but even that, we don't know whether they exist. But the problem is the amplitude goes down as a function of mass. And if you build, higher and higher frequencies, the sensitivity challenges are enormous. I think it is very hard, even beyond a kilohertz, to build these detectors, but I'd be happy to be proved wrong. I mean, there are other ways of building detectors like electromagnetic cavities, but I don't think they have any chance, of having good sensitivity. I think there's a hand up by
Kaustubh Chandra.
Yes, Satya, I have just a stupid question. So there has been ideas about the lunar-based observatories, right? And are they going to target the mid-frequency range, or are they going to still target the high-frequency ranges?
You can do whatever you want depending on the money available on Moon. Hopefully, it's very easy to build detectors. You don't, it's already pretty good vacuum, so you don't need vacuum tubes. You probably need just mirrors or maybe a very low vacuum. I don't know what kind of technology would be required. I don't mean it's completely empty. You can't do it in empty space, unlike in laser interferometer space antenna. However, the length is not a problem. You can build maybe 100 kilometers, 200 kilometers. I think those things are possible, but the curvature of Moon will be even larger because it's a smaller body. And so there'll be other kinds of challenges. But the current ones that I've seen are still kilometer-sized detectors. So they may be targeting still audio frequency as we are talking about,
Any other questions? Well, if not, then I hand over back to the organizers. Would you like to take a group photo while everyone is here, maybe?
Yes, sir. So I would like to request everybody, if possible, turn on your camera.
Just give a few seconds for people to turn it on.
Uma is okay. Harsh and Sagar is still. Harsh is not around.
Good to see all young faces. Wonderful. Thank you.
Yeah, I think.
Yes, sir. I have taken a couple of them.
Thank you.
Thanks.
Thank you very
Thanks
much.
a lot.
Thank you very much.
Okay.
Thank you. Bye.
Okay.
See you,
Goodbye,
Satya
Satya.
Prakash.
Bye.
Yeah,
Bye.
thanks a lot. Bye. Bye.
Thanks a lot, Satya. Thanks a lot,
Yeah,
Satya.
absolutely. Thank you. Bye.
Thanks. Okay.
Okay.
See you. Bye. 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 Bye.
Bye.
Okay. That should be fine.
Okay.
Okay.
Okay,
Vijit.
then. Bye.
See you then.
Bye.
See you.
Yeah.
Bye. Bye.
Okay.
Bye.
Bye, sir.
Bye. Bye. Bye.
Thanks.
Sir, again, we can end the meeting, right?